Thank you, Mr. Burgess, for that great beginning. Very good morning to you all. On behalf of BITS Pilani KK Billagua campus, I extend a warm welcome to each of you who are present here and who are on their way. It's my pleasure, privilege, and joy to welcome Professor Umesh Wagmare, Professor Ram Gopal Rao, our Vice Chancellor, Dr. Rahul Mohan, who is representing NCPOR, the Director of NCPOR, Dr. Thamban Meloth, could not make it today, Professor Ram Ramaswamy, Professor Partha Majumdar, Professor Rini Burgess, Professor Vijay Mohan Pillai, who could not make it, Professor Raghunathan, Professor Minal Kaushik, our Dean Admin, and Professor Mainak Banerjee, who is the convener of this meeting. We welcome all our esteemed fellows and associates to this sprawling and aesthetically beautiful campus of BITS Goa. We actually are extremely delighted and honored to have you all with us. We are happy that you have set footsteps on our soil, on our campus. Your august presence, your good wishes for us, your advice, your suggestions, your mentorship will go a long way for us as we look to expand, grow, and excel in all facets of education, which is our forte. The good wishes have already started bringing good news for us. We have, at BITS Goa, our Department of Mechanical Engineering has just received a grant of 1.2 crores through DST FIST. So it augurs well for us. And just last night, I got the good news of acceptance of one of my publications, which is rare these days with so much of administrative load. So it's working well for us. BITS Pilani, as you know, with 60 years of legacy, is a unique model of education. And I have been discussing, along with our Vice Chancellor, with the President of the Society last night, and I would implore you to discuss with us, to give us an opportunity to talk about this unique model of education. And I'm sure you'll be amazed and happy that how we have been progressing over the last 60 years. Many of our goals, objectives, vision align also with the academy, in terms of science education that the academy promotes, the summer programs that the academy promotes, and we are coming up with our own to add to all of that, the community outreach programs, and so much more. Our society is also at the brink of a landmark, reaching its 90th year, and we have reached our 20th year. So it's of 2 decades of excellence in Goa campus. And over the years, we have grown. We started with less than 30 faculties and about 562 students. As of today, we have more than 4,500 students on campus and about 220 faculties on campus. In addition to regular faculties, we have adjunct faculties, we have visiting faculties, chairs, professor of practice, guest faculties, and we also have on our rolls now a Russian and an Australian. Our funds, 2 faculties have grown from a mere 2 lakhs to about 40 lakhs as of today. We appreciate their work through various awards. We have 4 engineering departments, 4 science departments, and humanities, social sciences, and economic departments on campus. They are doing well. Computer science department, for example, is ranked 16th. The BITS Goa Computer Science Department. Overall, our pharmacy is ranked third, and life sciences also is ranked very highly. The intake of students have grown from 600 to 1,000 over the years. The number of courses that we provided in 2004 was about 10 to 15, which is over 600 now. The PhD students, which was 13 in 2005-06, is now about 434. So we are growing. Over 255 of them have already graduated. Last year, we received grants to the tune of 20 crores, which is already 15 crores now in this year. The publications have grown, the H-index have grown. So we have done well in terms of research, but there's a lot more to be done, and we look forward to doing more. And in that regard, your mentorship will be very important to us. There are various new courses we are coming up with, and some of these, BITS Goa is taking a lead on some of this, for example, like maths and computation, engineering, physics, pharmaceutical engineering, artificial intelligence for chemical engineers, our data science for climate and health, which already received funding from Rockefeller Foundation and data.org, environmental engineering, tissue engineering, minor in tissue engineering, nanoscience and nanotechnology. We have innovators on campus, at least 2 of them, and several of our graduates do very well in setting up and being entrepreneurs in the long run. As a campus, we take care of all various SDG goals, and our goal is to be a green campus. We have a team which looks after energy, environment, and green. Wastewater, which is solid waste, we treat on campus, and there's exceptional research that is going on, and we go to the community with those prototypes as well. So we are expanding, and I'm very happy that we could associate with Indian Academy of Sciences. They provided so much support, and we're also thankful to NCPOR Goa for that generous endowment. And a glimpse of what we do has been provided to you in terms of a short booklet. I explore you to look at it. The bottle that has been provided to you, it also is with a vision that we don't want plastic around, so please use those, and various community programs, various outreach programs that we fulfill on our campus over time. One of them is happening on Monday, which is part of our 20-year celebration, is something we call an open day, where all our departments, divisions, our student clubs is open to the entire state of Goa to come and visit us, see our prototypes, designs, experiments, laboratories, to motivate everyone into higher education. And before I close, I must thank Mr. Mahesh Chandra, who took a lot of pains and efforts to help us in organizing this annual meeting here. Professor Minal Kaushik, Dean Administration, who is on the dais, she led the efforts from the forefront. Professor Mainak Banerjee, who is the convener, and a team of young faculties. I'm not reading out their names because of shortage of time. And I wanted that team to work with us. Some of them are very new, with a vision that they are motivated and inspired by our esteemed fellows and associates, and one day they become fellows of this very society, which is an aspiration for all of us who work in the area of research. A wonderful program has been put together. Along with all the sessions, we have public lectures, 2 of them, and we want everyone to be part of it. And today, at the end of the day, a cultural program has been organized, and 60 of our students are involved in it. I have not seen what they're going to do, but I'm sure it would be magical. Your presence there would help them to inspire and do well in academics as well. And we have also put together a wonderful spouse program so that, they feel a sense of belonging with us all. And again, it's my pleasure to welcome you all. Enjoy the 2 days of academic feast. Hopefully we have taken care of most of the necessities. If there are some errors, come and talk to me, blame it on me. And if good things happen, if this is successful, all the appreciation goes to our committee members who have done it. Thank you very much for being with us, and I wish the meeting a grand success. Thank you.
Thank you, Professor Kundu. We'll now have some remarks from Professor Ramgopal Rao. Before that, I just want to ask, is the audience getting an echo? Because we get an echo at the stage. Is the audience getting an echo? Okay, great, thank you. Professor Ramgopal?
Good morning. We realized that we can't hear very well on the stage, so no, that's something we need to fix. And anyway, Professor Kundu has already welcomed all of you on behalf of BITS. I don't have much to add. And in the last council meeting, when the discussion came up about the venue for this event, I offered BITS Goa, and there was immediate kind of an acceptance. And I think that's what Goa does. Whether you do something here or not, you all want to come to Goa. But I hope, since you are here anyway, you get to go around and see the beaches and the nice restaurants, and if you are a non-vegetarian, the seafood. I think Goa has a lot of attraction. So I am also exploring that. I have been in the BIT system for about 8 months now, and this is one of our most beautiful campuses. As you can see, it's a 20-year-old campus. We're actually celebrating our 20th year now. And BITS, as you know, is 5 campuses now. It all started in Pilani 60 years ago. We will be celebrating our Diamond Jubilee celebrations next year. And then came Dubai, that was our second campus. Then Goa, this is our third campus. Then came Hyderabad, the fourth campus. And the most recent campus is in Mumbai, where there are 2 schools, BITS School of Management and BITS School of Law. Both have come up very well. The BITS SOM has already graduated 1 batch of students and all of that. And I would, now that you know the campus, now that you can associate faces with the campus, you will be meeting a lot of faculty and of course Professor Kundu and I think you should all consider coming back to this campus, visit us whenever you can, and we will be very happy to host you. And even if you are organizing any conferences and other things, now that you have seen the infrastructure, I think here is an open welcome to all of you. Open offer to all of you to come and organize events here, connect with the campus, and I think consider BITS as your own when it comes to doing any activity in India. Thank you very much.
Thank you very much, Professor Ramgopal Rao. We'll now have a few remarks by Dr. Rahul Mohan from NCPOR.
A very good morning to all of you and a very warm namaskar to all the Academy Fellows who have gathered here and invited guests attending the 89th annual meeting of the Indian Academy of Sciences, Bangalore. The National Center for Polar and Ocean Research, as a co-host of this meeting, feels privileged to be associated with this meeting. Just to give you a very brief of what NCPOR is to people who would not know us, NCPOR was established as an attached office of the then Department of Ocean Development, now the Ministry of Earth Sciences. It was in the year 1998, it was called as the Antarctic Study Center. In the year 2000, it was dedicated to the nation as the National Center for Antarctic and Ocean Research, and with the founder director, Dr. Premchand Pandey, sitting on the august audience here. So a big round of applause for him as well. Yeah. In 2018, there was a need felt by the ministry to rename NCPOR as NCPOR, which means that the polar world encompasses both the north and the south. So NCPOR is truly a trans-hemispheric center. When I say trans-hemispheric, it means that we transcend the hemispheres and we work in Antarctica, the Southern Ocean, which surrounds Antarctica, Arctic, Himalaya, and we have been bestowed with the geoscience projects of the ministry, including a component of the Deep Ocean Mission, which is Prime Minister's pet project these days. And we are proud to call ourselves as the gateway to the polar regions, because we provide you a pedestal to go through those places and execute the scientific projects. Just to inform the august audience that we operate 2 research bases in Antarctica currently, that is Maitri and Bharati, although they are 3,000 kilometers apart in East Antarctica. And probably those of you who are, just to add an information that it was 34 million years ago when the first ice sheets formed in East Antarctica. So these 2 research bases operate 365 days. The first Antarctic expedition sailed from Goa in December 1981. That was with the help of the National Institute of Oceanography and then the director and then Secretary of Department of Ocean Development, Dr. S.Z. Qasim, who is no more with us now. But India's attempts on explaining Antarctica goes back to 1956, when it raised Antarctica for peaceful purposes at the UN General Assembly, way back immediately after independence. The first research station, Dakshin Gangotri, came up in Antarctica in 1983, which is now buried under snow and ice since 1989 and is now a historical monument as per the Antarctic Treaty rules. We operate a research base in the Arctic. We call it Himadri, and from this year, we are going to operate it 365 days. We carry out multidisciplinary research, because polar research is like, it contains everything from the upper atmosphere to liquid, all states of matter, in fact, for that. We also have a small research base in Lahaul Spiti Himalaya, that is Himanch, because we feel that working in the Himalaya is critical, being the water tower of Asia, and it's important to monitor Himalaya along with the polar regions. And all of you would agree that after all, ice is just storehouse of fresh water. The polar program is indeed a multidisciplinary and interinstitutional, and through this platform and the podium that I have got today, I'd like to invite all of you from different domains to be part of the Indian Polar Program. The reason for this statement is we need a lot of synergy between academia and the research organizations in a bigger way for various reasons. Currently, there are man-to-man projects that are there, but academia and research institutions have a long way to go ahead if they want the country to reach the pinnacle of science. Of course, we need dedicated science to decipher mechanisms and linkages with signals from polar regions as we pass through a critical phase of intense climate variability and extreme weather conditions. What we do here affects our poles as well. So I once again thank the Academy for giving NCPOR a chance to be a co-host. Thank you so much. And thank you all for listening to me patiently. But I'll also suggest that you have a very busy schedule ahead of you, but do enjoy Goa, which is a small and lovely state of sun and the sand. Thank you so much once again.
Thank you very much, Dr. Rahul Mohan. I hope many of us will be able to come on your ships either north or south. I now hand over to the president of the Academy for the introduction of fellows and associates, Professor Wagmari.
Thank you, Renee. Good morning, all. We are absolutely delighted to have a tremendous response from fellows and associates and others to be present here for this annual meeting of the Academy. It's my pleasant job now to introduce the fellows, associates, and other invitees who are present at this meeting today. I'll call upon name of each of you and request you to stand up in your position so that others can see you and get introduced. So I'll first introduce the delegates on the stage. Professor Ram Gopal Rao, Professor Renee Burgess, you all have seen her already. Professor V.A. Raghunathan, Professor Partha Majumdar, the past president, and Professor Ram Ramaswamy, the past president. I'll now call upon names of the local fellows and associates. Professor A.C. Anil, National Institute of Oceanography, Goa. Professor Samit Chattopadhyay, BITS Pilani. He's also our local fellow who has been involved in advising the local organizing committee in planning of this meeting. Professor V.V. S.S. Sharma, NIO, Goa. Professor D. Shankar from NIO, Goa. Professor Sunil K. Singh, NIO, Goa. Dr. Vikash Kumar from NCPOR, Goa. I'll now call upon the names of people involved in local organization of this annual meeting. Professor Suman Kundu, you have heard him already, the director of BITS Pilani. Dr. Rahul Mohan from NCPOR, who you listened to just last. Professor Mainak Banerjee, the convener of the LOC. Mr. Arjun Halarankar, he's in the audience. He must, some of these may be busy attending to the course in organization now. Professor Anshuman Sarkar. Professor Sarang Dhongdi. Professor Saurabh Patankar. Yeah, most of them are busy attending to various things. Professor Sudipta Chatterjee. Professor Arnab K. Paul. Professor Indrakshi Rai Chaudhuri. Professor Vaibhav Joshi. Professor Gunja Sachdeva. Professor Ram Shankar Patel. Professor Rajiv K. Chaturvedi. Professor Anil Kumar. All of these people from the local organization committee have put in a huge amount of effort, and I appreciate their work at this moment. I move on now to the outstation fellows who have come to this meeting. Professor Javed Agrewala from IIT Rupanagar. Professor G.V. Anand, Dayananda Sagar University, Bangalore. Professor S.K. Apte from University of Mumbai. Professor Hemalata Balram from JNCSR, Bangalore. Dr. Anirban Basu from NBRC, Manesar. Professor K. Bhanu Shankar Rao, University of Hyderabad. Professor S.V. Bhatt from IISc, Bangalore. Professor Arup Bose from ISI, Kolkata. Professor Sujit K. Bose, Kolkata. Professor Praveen Chadda from Gurgaon. Professor Subhash Chaturvedi from ICER Bhopal, Professor Devashish Chowdhury from Dehradun, Professor P.K. Das from IISc Bangalore. He is the chairman of our science education panel as well. Professor Debabrata Dash, Varanasi. Professor Basudev Datta, Kolkata. Professor B.S. Dayasagar, ISI, Bangalore. Professor Sridhar Gadre from Savitribai Phule University, Pune. Professor Ashutosh Ghosh from the University of Kolkata. Professor Ashwini Ghosh from IACS, Kolkata. Professor Subrata Ghosh from IACS, Kolkata. Professor Swapan K. Ghosh from the University of Mumbai. Professor L.C. Gupta from New Delhi. Professor Achyutan Jayaraman from Bangalore. Professor Dilip Kanere from Savitribai Phule University, Pune. Professor E. Krishna Kumar from the Raman Research Institute, Bangalore. Professor Meena Mahajan from the Institute of Mathematical Sciences, Chennai. Professor Govinda Majumdar from TIFR, Mumbai. Professor K.C. Malhotra from Noida. Professor Manoj Kumar from Guru Nanak Dev University, Amritsar. Professor G. Marimuthu from Madurai Kamraj University. Professor Manoj K. Mishra from Mumbai. Professor J.P. Mittal from Navi Mumbai. Professor Sunil Mukhi from ICER Pune. Professor Parthasarthi Mukhopadhyay from IITM Pune. Professor T.G.K. Murthy, Bangalore. Professor Devendra Oza from TIFR, Mumbai. Professor Dr. Premchand Pandey from Ahmedabad. Professor Dayashankar Pandey from Banaras Hindu University, Varanasi. Dr. Pramod A. Paranjape from Pune. Professor Tanmay Pathak from IIT Kharagpur. Professor Rajiv Patnaik from Punjab University, Chandigarh. Professor Apparao Podile from the University of Hyderabad. Professor K.N. Raghavan from the Institute of Mathematical Sciences, Chennai. Professor A.S. Raghavendra from the University of Hyderabad. Professor D. Ramaiah from BITS Pilani, Hyderabad. Professor R. Ramaraj from Madurai. Professor P. Balarama Rao, Hyderabad. Professor A. Pramesh Rao, Pune. Dr. Raghavendra R. Rao from Bangalore. Professor Samit Kumar Ray from IIT Kharagpur. Professor Kirti Chandra Sahu from IIT Hyderabad. Professor M. Sanjappa from Bangalore. Professor Manmohan Sareen from PRL Ahmedabad. Professor K.D. Sen from the University of Hyderabad. Professor K.P. Singh from ICER Mohali. Professor Meva Singh from the University of Mysore. Professor Somadatta Sinha from ICER Kolkata. Professor Binod Srinivasan from IISc Bangalore. Professor Rajesh Srivastava from Banaras Hindu University. Professor Sham N. Tandon from Pune. Professor Y.V. Venkatesh from Bangalore. I will now call upon the outstation associates. Dr. Ajit C. Balaram from Institute of Mathematical Sciences, Dr. Shubham Banerjee from NIPER Guwahati, Dr. Arpan Bhattacharya from IIT Gandhinagar, Dr. Indranath Chakraborty from IIT Kharagpur, Dr. Nitin Singh Chauhan from TIFR Mumbai, Dr. Kubendran Amos Prince Gideon from NIT Tiruchirappalli, Dr. Tarak Karmakar from IIT Delhi, Dr. Bhavya B. Krishna from IIP Dehradun, Dr. Monalisa Pal from the Banaras Hindu University, Dr. Saurav Pal from IIT Mumbai, Dr. Emiya K. Samal from Banaras Hindu University, Dr. Anand N. Sharma from IISER Tiruvananthapuram, Dr. Gaurav Sharma from IIT Hyderabad, Dr. Vinay Sharma from IIT Jammu, Dr. Akshay Singh from IISc Bangalore, Dr. Jogender Singh from IISER Mohali, Dr. Duvuri Subramanyam from IISc Bangalore, Dr. Umakanta Subuddhi from IMMT Bhubaneswar, Dr. Vishwanath Tiwari, Central University of Rajasthan, Ajmer, Dr. Sriram Varahan from CCMB, Hyderabad. That completes the list of associates, and I'm pleased to share with you the diversity in backgrounds of the associates we see in this list. And I'm glad that many of them have come for this meeting. I'll now call upon names of the speakers who are fellows and associates. Dr. G. Bipin Anand from SRM IST Kathanakulatu, Professor Bijnan Bandyopadhyay from IIT Jodhpur, Dr. Anindita Das from IACS Kolkata, Dr. Uttam Ghurai from Ramakrishna Mission, Howrah, Dr. Sundar Gopal Ghosh from IIT Chennai, Professor Vijay Kodiyalam from the Institute of Mathematical Sciences, Professor Swadhin K. Mandal from IISER Kolkata, Professor Bishwarup Mukhopadhyay from IISER Kolkata, Professor Ganesh Nagaraju from IISc Bangalore, Professor Maumanti Poddar from IISER Pune, Dr. Haripada Sau from IISER Pune, Professor Rajiv Sinha from IIT Kanpur, Dr. Aishwarya Venkatesh from CCMB Hyderabad. Now I'll call upon names of non-fellow speakers and science education panel members. Dr. M.A. Atmanand, IIT Chennai, Professor Ekambaram Balaraman, IISER Tirupati, Professor Suchitra Banerjee from CIMAP Lucknow, Dr. Dean D. Cruz from Goa Foundation, he is the speaker of the public lecture today, Professor Matthias Dries from Berlin, Dr. Y.C. Kamala from National College, Bengaluru, Professor Sebastian C. Peter from JNCSR, Bangalore, Professor Neelam Sangwan from the Central University of Haryana, Mahendragarh, Professor V. Sunil, NCPOR, Goa. Yeah. That completes the introductions that I have in this list today. I may have missed someone, and I apologize if I did, and I hope we will have a chance to connect during this next week. Oh, I'm sorry, Professor Ishwar Reddy from IIA Bangalore. Thank you. And I apologize that there was a miss. Okay.
Thank you very much, Umesh, for those introductions. I think now it's time for the presidential address by Professor Wagmare. So I would request the delegates, people on the dais to make their way down and leave the stage for Umesh Wagmare. Thank you all very much for participating. I'd just like to make an announcement before Umesh begins his presidential address. So after the address, immediately after, there will be a group photograph just upstairs in the B dome, the entrance to this building. There are a set of steps. So please, immediately after the presidential address, this is a group photograph for fellows, associates, local organizing committee members, and for the invited teachers who have participated in this event. Tea will be served just near your where the group photograph happens, and we come back after the tea break. So I hand it over now with great pleasure to the President, Umesh Wagmare.
Yeah, good. Thank you. Thank you. Good morning, all, and it's my pleasure once again to join the office bearers in welcoming you to the annual meeting, the 89th annual meeting of the Academy. And I'm really delighted that so many of you have come for this meeting and present in this session. The Academy depends very greatly on the contributions of each of you to various activities, and it's becoming even more important as the scientific ecosystem in the country is evolving to somewhat new structures. So the Academy will now be envisaging connecting stronger with the local institutions, regional places, and involve our fellowship even more intimately in connecting with the society, contributing, upholding the cause of science, and promoting science in smaller universities, state universities, and institutions. So I look forward to working with you all in the years to come. The next year is the 90th year of the Indian Academy of Sciences, and we do plan to have some special events and as well as possibly new initiatives. And any ideas you have to offer for us to consider, please do share with us by email or talk to some of us during this meeting as well. So traditionally, the address of the president in this inaugural session is a technical talk, and I'll be talking about some very interesting work we did. It's a nice example of interdisciplinary science on a material, class of materials called group 4 chalcogenides. For example, a compound made up of lead and tellurium, or germanium and tellurium. And it's an example of work where one past president of the academy is involved along with me, which is Professor C.N.R. Rao, who all of you know is a chemist, and he posed this problem to us. It's a problem which has been around for nearly 50 years, which involves chemical concepts about bonding in certain class of materials. And these materials are of remarkable importance and relevance to technologies, which I'll convince you in the next few slides. And there is very fundamental science which is involved, which we look at through the lens of a physicist, okay? So the work was done by my student, Ragya Arora. Sorry, the pointer is not working.
Pointer, you just show it, it is coming.
Okay, I see. All right, yeah, thank you. All right. So the work was done by my PhD student, Ragya Arora, who is now moved on to physics department at Harvard. And as I said, the problem was suggested by Professor C.N.R. Rao, and we interacted with him quite a lot in the last 5 years on these issues. So let me get started. This is a very basic slide, particularly for chemists, about fundamental bonding mechanisms. There are different types of bonding possible in molecules and materials. The first one is ionic bonding, where an electron is donated from a positive ion to a negative ion, and that gives electrostatic binding. The second is covalent bonding, where an electron is shared between two neighboring atoms. The third one is metallic bonding, where electrons are shared with many atoms in a material, and as a result, the electrons are highly delocalized. And lastly, one also can have weaker type of bonding, like hydrogen or van der Waals type of interactions between the atoms. Now, energy scales involved here go from about tens of eV in the ionic bonding to milli-eV in hydrogen and van der Waals type weak bonding. So energy scales are about 3 decades, 3 orders of magnitude. But the key aspect is, for a given type of bonding, the properties of a material are very specifically determined. Ionic bonds, for example, sodium chloride, exhibits a very large sort of gap separating the occupied states from the unoccupied states. As a result, the light it can absorb has a very high energy. It has very low electrical conductivity, generally. On the other hand, covalent bonds, which are present in, for instance, semiconducting silicon, exhibit smaller gaps. The bonding is very different. The coordination number is typically smaller, up to 4. And these materials have basically very sort of moderate band gaps with fairly high electrical conductivity, but not as comparable to metals, where the electrons are highly delocalized, which have no band gap at all. Yeah? So the kind of bonding has spectacular signatures to the physical properties of a system, and the weakly bonded materials are of course very soft. Soft materials, biological systems often belong to the last category. I don't know some. I don't think yeah, I was given a different pointer to begin with. I would rather use that. This is not the one I tried beforehand, so, and this is not working either, the slide for. What is the next slide? Okay, now it's, but okay.
This is for the next, sir. This is for the previous.
It's not working, that's why I'm telling you. Hey, does it?
Yeah, it's working.
Okay, all right, I'll try 1 second, but if not, I'll switch on. Okay, so the materials that I'm going to talk about, I think the problem is you are changing slides from there, and that's not what I requested. I want to use the slides from this screen, please. And that's why I'm seeing that it's not working, right? He won't know when I'm changing.
No, sir. This is the thing which is changing from
I want to use this, right? Otherwise, there's no meaning to having it here. See, what we tried before the talk is what I will like to use. Yeah. Yeah, please connect that. Yeah. Sure. Yes, that's right. Yeah. Thank you. Sorry about this interruption. I do feel comfortable using the system. I'll try it out before the presentation, but apologize for the delay. Yeah. Okay, so the specific materials I'm going to tell you about are these group 4 chalcogenides. And example of it is germanium antimony telluride called GST, a fascinating class of materials which show a transformation from amorphous phase, which is like a glassy structure, totally disordered in the spatial arrangement of atoms, to crystalline phase, which is, this is by the way, sodium chloride structure, the rock salt structure which all of us are familiar with. Yeah? And this occurs at a time scale of 100 nanoseconds or even faster as the system is heated to few hundred centimeters. Thank you. Okay, so it's a very interesting phenomenon, and the reason why it is interesting and useful in technologies is the properties of this phase are totally different from the properties of this phase. Yeah? This is a covalently bonded system which exhibits a different band gap and hence optical properties, whereas this one has a rather different optical spectrum contrasting with the amorphous phase. As a result, this material can be used in making optical memories or flash memories, because the electrical conductivity here is very low, here it is very high. Yeah? So as I told you in the last slide, that chemical bonding is relevant to the properties. Here you are talking about the same set of atoms, different spatial arrangements, very comparable density, but the properties of technological importance are very contrasting with each other. And it's reasonably fast that you can use it in fast access memory applications. Yeah? So question mark is here. The bonding in this phase is not understood, the crystalline phase. One would think that amorphous phases are typically harder to understand, but in this case, the simple crystal structure, which is what rock salt structure is, taken by sodium chloride, is not understood. Yeah? So this is what is the goal of our talk, and Professor Rao basically posed it to us that the nature of chemical bonding here seems very intriguing and different from the fundamental bonding mechanisms that are known to us, that are introduced on the first slide. So let me first convince you that they are really interesting materials. Thank you. So let me first convince you that these materials are very interesting and important for technologies. The first property is called ferroelectricity. In this case, the germanium atom or tin atom can off-center from its position to give you electric dipole moment. Yeah? And that can also be used in non-volatile computer memory applications. The second is, I'll elaborate on this little more, the thermoelectric property. These materials, when they sandwich a heat source, with a sandwich between a heat source and a cold heat sink or a cold material, they generate electric current and can generate electricity. Of course, all materials are thermoelectric. There's no symmetry restrictions on the material from being thermoelectric. But these are special because they're highly efficient thermoelectric materials. And you will see that's not so simple on the next slide. The third very unusual property they exhibit is called electronic topology. These materials are very close to being a non-trivial topological insulator. And again, not many materials exhibit that behavior. This is a class of properties, topological electronic structure, has been realized only in the last decade or 15 years. And these materials are some of the most promising materials in that domain of properties. So thermoelectric figure of merit, why these materials are so unusual and hence good thermoelectric. For a thermoelectric material to generate electricity efficiently, it should have few properties which are desirable. The first is Seebeck coefficient, which tells you for a given temperature gradient how much electrical voltage is generated. So naturally, S should be as high as possible. Second is electrical conductivity, which means the material should carry current efficiently to generate adequate electric power. In fact, the numerator here is called thermopower, which is electric power generated from the temperature gradient. In the denominator is thermal conductivity, which means the material should not carry heat fast. Otherwise, what's the point? It will just take away the heat from hot sink to the hot source of the heat to the heat sink. So this should be as low as possible. Already you can see that it's a challenging proposition. If you increase Seebeck coefficient, you see it depends on two quantities. One is the mass of electron carriers or hole carriers and the number density of carriers in this manner. Whereas electrical conductivity depends inversely on that. It increases with higher carrier concentration. So if you want to increase S, electrical conductivity decreases. So these are like contradictory requirements on a material. The next is thermal conductivity. If electrical conductivity has to go up, you will see S comes down and thermal conductivity goes up too, because you will expect by Lindemann-Franz law, if a material is a good conductor of electricity, it's likely to be a good conductor of heat as well. And as a result, this is called as a thermoelectric figure of merit challenge. And in a real material, as you look at function of carrier density, which carry electrical current, the Seebeck coefficient is large for semiconductors. Electrical conductivity is large for metallic systems. And in between, you get thermal conductivity like a glass, which is giving you a peak in the figure of merit of thermoelectric materials. So for a material to be efficient for thermoelectric, it needs to function like a metal, it needs to function like a semiconductor, and it needs to function like a glass as far as thermal conductivity is concerned. And that's a challenge, right? You can't have everything in the same material. Of course, there are many thermoelectric materials developed which are little complicated. They involve nanoprecipitates, composites, which are combination of many materials which can give you high thermoelectric performance. That's not too surprising. But in this case, we are saying a single phase crystal gives you high thermoelectric performance with no disorder, with no other complications. And that was the stage which we started with. So the first aspect of these materials relevant to chemical bonding is the violation of octet rule, something we study in high school chemistry, that whenever an atom is in the vicinity of other atoms, it likes to bond with other atoms to either gain or lose electrons or share electrons with the neighboring atoms to complete a shell, an octet shell, meaning complete outer shell of electrons to have 8 electrons. Yeah? A very simple rule. And silicon is a very good example. Each silicon atom has 4 valence electrons. It can form 4 bonds, each of which has 2 electrons shared between 2 neighboring silicon atoms. Yeah, so it's a beautiful example. Of course, nothing unusual. The bonding in silicon is fairly well understood, being simple. Here, you have, if you look at the number of electrons in each atom, you will get 8 minus 5 coordination of 3. It should have 3 covalent type bonds. Unfortunately, it has 6 nearest neighbors. Yeah? So you have more number of bonds than the electrons available to support those bonds, either through sharing, and they can't be too ionic either. Yeah? Which is what makes them very interesting. There are some molecular analogs of it, basically Xeon F2, where 8 minus n rule is violated by sort of what is called as hypervalent or hypovalent type of electronic bonding. So chemists used to think that maybe this is similar, this is an inorganic analog, extended crystalline analog of this, But you will see soon that it's not quite so, because in this set of materials, they are electron deficient. They have fewer electrons and higher coordination number. Am I losing my voice? Okay, yeah, it's back. Okay, so violation of octet rule is the first important aspect of this metavalent bonding, which I'll come to. So people believed that maybe it is analogous to something called resonance bonding, again something we have studied from high school days. And a classic example is benzene molecule, which has two configurations shown here. Basically, double bond is slightly shorter than the single bond, and the idea is one can have a resonance between these two equivalent structures, and then we get a benzene ring. So switching between these structures can give you delocalization of pi electrons as shown here, and people believe that maybe this is the kind of bonding which is present in these compounds. So in inorganic chalcogenides, you will see you have 2p electrons of lead and 4p electrons of tellurium, about 6p electrons per atom pair. So you have 3 electrons bonds forming 6 bonds, and there are 6 available covalent bonds. So bond occupation in this sense is not unique. You will see this is one configuration, this is another configuration, and if you take average of these, you will get this single electron bonded configuration. Yeah? So people believed in 2008. You see the work started in 70s, and this picture was appreciated in 2008 in this Nature Materials paper by Wuttig, saying that maybe this is like resonant bonding, and that should explain many things. Yeah? Of course, in this case, the choices of bond occupation is not unique. In fact, there are infinitely many choices, and in that sense, it's a highly degenerate type of a system. So later, a physicist also looked at it, a reasonably well-known physicist, Peter Littlewood. This was his PhD thesis at Cavendish Lab. And he basically proposed that if you have a single chain like this, with half the number of electrons that are necessary for all the bonds to be supported, you basically have chiral instability. All of you know, in one dimension, chiral instability basically is a special case of a generic principle that if any system has a degenerate ground state, it is not stable. It will lower its symmetry and split the degeneracy of its ground state. And this is an example of it. In the undistorted structure, it looks like this, but by dimerization between the neighboring atoms by forming short and long bonds, it gives you a distorted structure, and in this case, electrons can migrate from one to another reasonably efficiently. So this was the explanation given by Peter Littlewood in late 70s. And he explained specifically the large dipole which arises from such electron motion. I will convince you by the end of this lecture that this picture is right in spirit, but wrong in actually precise technical detail. Yeah? So the electronic mechanisms to explain these unusual properties are still to be discovered. So this resonant bonding, which people talked about in before 2000, they cannot explain this set of properties. I'll explain to you what they are. If you have a resonant bond like benzene, you have bond order which is non-integral but greater than unity. Bond order is basically the number of pairs of electrons shared between two atoms in a bond. And benzene and graphene are good examples of this. They have very high vibrational frequencies, whereas these chalcogenides have very soft bonds and very low vibrational frequencies. Optical polarizability of these chalcogenides is very high in comparison with these systems, and they are almost comparable to metallic like electron delocalization as shown here. The middle parameter is called Gruneisen parameter. It says how vibrations of a crystal are sensitive to the volume of the crystal unit cell. And here also, they are very anomalous. They are very large for this rock salt structure as opposed to the resonantly bonded crystals or systems. Yeah? So the key point is, if I assume the resonant bonding picture, which was sort of believed to be relevant in 80s, we cannot explain these properties. And that's what was realized in 2018, again by the same group, Matthias Wuttig's group. And they proposed that we should call this bonding as metavalent bonding. I'll explain to you the term metavalent. It comes from the fact that it has commonality with metals as well as commonality with covalent systems. So it's metavalent bonding system. That's the logic behind this term. And these have bond order of half as opposed to the bond order of resonantly bonded systems. So that's what was the background. Let me now explain to you what is very unusual about these properties. The first is Born effective charge, named after Max Born. And it's a very interesting property, so just watch it. If you haven't seen it before, I'll explain to you what it is. It's called dynamical charge. It gives you change in dipole moment or polarization of a molecule or a crystal created by displacement of an atom or an ion, right? So the bond charge, Z star, is first derivative of dipole moment with respect to atomic positions. It can also relate to the force on the ion created by electric field. So if you have a purely ionic crystal like sodium chloride, the bond charge is same as the nominal charge, +1 or -1 for sodium chloride. And it's a measure of long-range Coulomb interactions in a given system. These are important in ferroelectric materials, which I told you is one of the interesting properties of these materials. The second is Gruneisen parameter, which tells you how vibrational frequency omega I varies with respect to the volume of the cell. And this characterizes the lattice unharmonicity, and which is responsible for the low thermal conductivity, as I explained, relevant to the thermoelectric materials. So this is crucial in thermoelectric applications. So these two properties we would really like to explain if you have a correct picture of chemical bonding in these systems. So let me move on. Let me tell you what is bond charge is. Very interesting, simple concept. If I have germanium telluride in the rock salt phase, I'm showing you only the local environment of germanium, which is surrounded by 6 tellurium atoms. I'm showing you only 4 here. It has a 0 dipole moment by symmetry because germanium sits at the center of inversion. But if I move this germanium atom to the right, it moves by distance u. You will expect that the dipole moment induced should be Z star times u, right? If you look at the nominal charges of germanium telluride, these are +2 and -2. But if you look at real values of these charges, it is 10. It's 5 times bigger than nominal charge. Yeah, and this is a puzzle. This is a puzzle which my group itself was involved in early 2000s to explain, but we now have a picture which explains all the anomalous properties. Yeah? So how do we explain this dynamical charge of 10 of germanium? Now you will say, well, is it a theoretical concept? No, it's measurable. This is essentially telling you how strongly this crystal couples with electromagnetic wave. In this context, the infrared radiation. So these are called as infrared oscillator strains relevant to the crystals. Yeah. Okay, so let me now summarize to you the physical properties which are fingerprints of materials which are proposed to be metavalently bonded. Electronic conductivity, which is very high for metals, and it's moderate for metavalent between the covalent and metals. Effective coordination rule is violated, 8-n rule is violated. Optical dielectric constant, which is essentially the refractive index, squared, it's much higher than 15 for these and much lower for these other systems. For metals, this is not defined. Bond charges are very anomalous, 4 to 6, where they should be 2 in the nominal ionic state. And the Mode-Gruneisen parameter, which are the measure of lattice nonlinearity, are much higher in the chalcogenides. Lastly, it was also shown experimentally that the bonds in these systems break in a very unique way as opposed to the bonding in covalent or ionic crystals. Okay, so these are the properties which are relevant. I won't be able to cover each one of them in the time available to me, but I'll quickly go now through the mechanism that we want to resolve. So the work done by Wuttig, which called them metavalent, I will tell you the background to it. What they looked at is a map of electrons transferred from germanium or cation to an ion, and on the y-axis is the number of electrons shared between the two atoms forming a bond. You will see the resonant bonding falls in the upper corner here. Covalent bonds are over here, where the number of electrons shared is close to 2. Ionic ones, the number of electrons transferred is close to 1. These are ionic. And metallic ones fall in this corner, where the number of electrons shared or donated are close to 0, or very small number. And the metavalent systems fall here, in between these 3. Not only that, they all are circled by this yellow circle, which means the thermoelectric figure of merit for all of these compounds is greater than 1/4, which is typically smaller than even 0.1 for most of these other systems. Yeah? So this is to make a case why by Wutig et al. Called it as the metavalent systems and why they are special and distinct from the other bonded systems. Okay, so let me explain now. The background was this: the metavalent bonding remained defined essentially based on properties rather than electronic mechanisms. They were shown to be belonging to a special region in that map, but mechanism is unclear what governs this bonding, and that was the goal we set out with. Okay, so I'll take a little time to explain the philosophy with which we looked at it. In physics, one of the new recent areas introduced is called topological insulators. So the concept is like this: if I have an insulating material, imagine that I continuously change it. You can deform it or you can apply other external fields and ask a question: how does that insulator evolve in its properties as I changed it or like deform it? In topology, you ask a question: can I deform a sphere and make a torus out of it? In this case, I'm evolving an insulator continuously from one state to another and ask a question: does it ever pass through a metallic state? If it passes through a metallic state, it changes its topology generally. I mean, that has been established. So we are going to use those ideas here. What we will say is, we want to understand metavalent bonding, but we want to understand by continuously evolving it from a well-known bonding like metallic bonding, covalent bonding, and ionic bonding. And then ask a question: how does it change, when does it change, and what are its consequences? To establish, first of all, whether it's different, because I admit to you that this is topic which has stayed on for 50 years, occupied physicists and chemists, and it still is a little controversial. So I don't mean to give you a message that we have resolved it fully. People are still questioning some of these things. But idea is, I think we do provide answers to some of these interesting questions in this area. Okay, so what do we do? To go from metallic state to metavalently bonded state, the first step is to identify which is the relevant metallic state that I can start with. And the answer is, if you have this rock salt, beautiful rock salt structure of lead and tellurium, the simplest metal that I can derive from it is by replacing each of these atoms, lead and tellurium, by antimony or something like average of lead and tellurium. Antimony atom, you can imagine, is close to being average of, chemical average of lead and tellurium. So you get a cubic structure. So from FCC rock salt structure, one gets a simple cubic lattice with just one atom per unit cell. Okay? So why do we say this is a very relevant metal structure? Parent, it has a symmetry higher than the symmetry of this lattice. Its coordination number is the same as the crystal we are interested in. Its number of valence electrons is the same. Not only number of valence electrons, even the character of those electrons, p orbital character, is the same. And they are sort of chemical average of the two. And we expect this structure to be metallic. And indeed, if you compare this is, by the way, on the bottom, I'm showing electronic structure. For those who haven't seen it before, it just says it's the electronic spectrum of a crystal. On y-axis, we plot energy as a function of inverse wavelength, and these labels are basically points in the reciprocal space with certain symmetry properties. So if there is a gap, it's a semiconductor, and as you see, it's a very small band gap in lead telluride. And this is the parent structure we identify is metallic. So our first point in the trajectory is clear. Now we want to say, we want to adiabatically evolve this structure into this structure. Yeah? Of course, experimentalists will immediately laugh and say, well, you are being an alchemist there. In theory, it's possible. In theory, it just means that I have a Hamiltonian of this, and I can continuously find a trajectory to go from one to another. And that's what we do. We start with a very simple p electron model of orbitals of neighboring atoms interacting with each other. And I just want to tell you one very interesting feature of this cubic simple metal. So this is a simple cubic crystal of a metal like antimony. It's a half-filled p state. So this line basically is the Fermi energy. Above that are the electronic states with energies which are higher and unoccupied. And the lower than that, all are these are occupied electronic states called valence band, valence and conduction band. So the beauty of this system is you have a perfectly symmetric electronic structure. It's reflected in this, in the energy axis. And more importantly, even the bonding, anti-bonding character is reflected. Yeah, so it has electron-hole symmetry and it has bonding, anti-bonding symmetry, which is very exciting for a physicist. Of course, in a real material, you also have s electrons, which are occupied, and that they do change some of these important features, but not qualitatively. So half-filled p-bands is the first important aspect of the systems that we highlight, and you will see how it is relevant. The next thing of a metal, which is a very fundamental aspect of a metal, which we look at, is called Fermi surface. In fact, Fermi surface is an aspect which defines whether a system is metallic or not. If a system is not metallic, you don't have Fermi surface. Fermi surface is a surface in reciprocal space which separates occupied and unoccupied states. And what you find in the Fermi surface of cubic antimony is there is a nesting, meaning this pink red color box can be rigidly shifted to another box in this Fermi surface, which is given in blue. And when this happens, it means that large number of electrons on this packet of Fermi surface can be scattered to this packet of Fermi surface, and that means the system is unstable. This is a three-dimensional analog of Peierls instability. You have a degenerate metal. Not only degenerate metal, there is one particular perturbation which corresponds to this wave vector half-half-half, which can scatter electrons very effectively. And if, once you predict that the structure is unstable, we can calculate the vibrational spectrum of this system and demonstrate that it's unstable at our point. Our point is the point which is nesting vector. Yeah? So we confirm that Peierls picture is right, which is what Littlewood had proposed in '79. But then we take it forward. So whenever you have this instability, you can lower the symmetry of the crystal, and that can stabilize a lower symmetry structure. And in this case, the first thing is we try structural distortion, where the two sublattices of antimony move closer towards each other. So you get a shorter and longer bonds, like Peierls system. And then you can see the system opens up a band gap, and it stabilizes. So indeed, the picture of Peierls instability is beautifully verified. You can also break the translational symmetry by chemical field, where you replace average antimony by bismuth antimony or lead telluride, and then also you see the gap is opened up. Yeah? So you can lower symmetry either using chemistry or by using structure. The mechanism is still the same Peierls type mechanism, which opens up a gap. So this part we verified beautifully. We showed that you break translational symmetry, you can derive metavalent bonding, provided the symmetry breaking is relatively weak. Weak symmetry breaking is very critical. Now what I will show you is, if you break this symmetry strongly, you evolve to covalent bond. If it's structural evolution, if it's chemical evolution, it goes to ionic bond. Yeah? So chemical bonding now has been shown in this work as a consequence of broken symmetry states of the parent metallic state. Okay? So this is the basically structural evolution. On one point is this zinc blende structure. It's covalent, four-fold coordination. On the right-hand side is rock salt. And you will see the anomalous property bond charges on right and dielectric constant on the left. They are highly anomalous for the rock salt structure, and they are relatively boring for the zinc blende structure. So this identifies that the descriptor of fingerprint property of metavalent bonding actually evolves discontinuously from this curve as you go from covalent state to metavalent state. But the theory is really beautiful. It allows us to make a new prediction, right? I told you 6 properties which are fingerprint properties of metavalent bonding. Here we propose that, look at the curvature here, it's a very shallow curve. Here it looks almost linear, but it's actually quadratic. Symmetry forces it to be quadratic. And the curvature here is 9 times bigger than the curvature here, which means the metavalently bonded states will show very anomalous Raman properties. It has stronger second order Raman than the first order Raman response. Yeah? So indeed, this is something which we are hoping people will verify. In fact, we already have some confirmation of it, because if you go by the cubic symmetry of a crystal, there is no Raman active spectrum possible. But these systems are known to exhibit Raman spectra, and we feel one of the explanations possible is the fact that they are second order Raman frequencies, and we are quantitatively comparing them. If you look at energetics and structural evolution from covalent to metavalent state, other systems which are known to be covalent or not half-filled, they go through a smooth energy curve, except for these guys, the two of them, which are metavalent, exhibit a sharp cusp. So we demonstrate that there is a discontinuous phase transition as you go from covalent state to metavalent state, indeed. We can also break symmetry using chemical field. This is like an alchemical perturbation. So we evolve average lead telluride from half to 1 using this alchemical perturbation. As you will see, this end is metallic, this end is ionic, and in between, with a weaker symmetry breaking, we develop a metavalent state. Yeah? So this is also shown as a discontinuous phase transition. So this picture we use to adiabatically evolve one type of system to another allows us to come up with a phase diagram now in the composition and structural space. You have 4-fold coordination here, 6-fold coordination on this lower side, and chemically this is ionic end and this is metallic end. You will see that weakly symmetry broken states are typically the metavalently bonded states, and if you go up, you develop covalency. If you go to the right, you develop ionicity depending on stronger symmetry breaking. Yeah? So very nice, simple picture in the language of physicists based on broken symmetry to explain this bonding. Still, you will say, what is the electronic mechanism, finally, which is what chemists would like to know. And that's the fundamental issue. So here I wish to share with you and invite interactions with chemists or others here. Analysis of chemical bonding is invariably means you need to partition the electron charge, which is a continuous function, into discrete entities to identify the chemical bonding. And this is highly non-unique, okay? Spatial partitioning of charge density is highly non-unique, and what we use is called one-year functions, which are also non-unique, I admit to you, but we have a way to fix them for a crystal, and these are called as molecular orbitals of a crystal. I have a few minutes till yeah, thank you. Okay, so one-year functions, by the way, are very interesting. Those of you who are interested, I'll be happy to tell you more about. They are also very relevant to electronic topology, which is very fashionable in physics today, and they're of course relevant to chemical bonding as well. Okay, so one-year functions here look like this. This is the px orbital of tellurium. You see this is green atom is tellurium, and it's interacting with the neighboring atom. This is the highly localized one-year function. This is s orbital centered on tellurium, and this is s orbital centered on lead. These three orbitals explain all the infinitely occupied electron states in this crystal, yeah? And they are localized, although the crystal is highly infinitely extended. So this is the most compact picture of bonding you can develop for a crystal based on this one-year function. And you will see they are delocalized, they extend to further neighbors, and you have bonding, anti-bonding, sigma pi interactions as you go to alternate atoms. And that I show you on the next slide. You have this tellurium p orbital, you have sigma bond in the first shell, sigma star in the next, you have pi interaction here, pi star in the next shell. So this is what we uncover as a very special character here, alternating bonding, anti-bonding chemical interactions between p orbitals. And as a result, we explain how the bond order is fractional and subunity, and why 8 minus n rule is violated. So I promised to you that I will explain to you this very anomalous bond charge, which has a value of 10. So we examine one-year functions as a function of displacement of atoms. So black atoms in the undistorted state are at high symmetry phase structure. They move to the right, we get a distorted phase. And what I want to point out is very tiny electron moves from here to here. You see, here these two lobes are symmetric, whereas these two are asymmetric. There's a smaller lobe here, which means a tiny electron moves from this end to this end. But although it's a tiny electron, it moves all across the unit cell, like 5 angstrom. So you get a very large dipole moment. And this is in response to a very tiny displacement of this atom to the right. Same thing happens in the pi bonded tellurium p orbitals. You see there is a change here. This is where the charge accumulates on the left, and on the right it is depleting. So that gives you additional contribution to the bond charge. So this is a dynamical charge where electron moves to the left when the positive ion moves to the right by a small amount, and this moves by a full unit cell, giving you a very large dipole moment. And that's how we explain this anomalous bond charge. So this is a simple sort of cartoon picture we develop. This is similar to people working in magnetism, and they know this as super exchange or double exchange type interactions, except for the fact here they are spinless. Electron goes from one cation across the unit cell to the next cation, hopping through the p orbitals of an ion. And that's what explains this large matrix element between valence and conduction band, which gives you very large bond charge, very large polarizability, and so on. Yeah? So my time is over, but we have taken this work to 2 dimensions as well, and confirmed, because in 2 dimensions, it's even more challenging because the coordination numbers are restricted. You can't have extension coordination in third direction. Yeah? So here also, we have shown that the ideas we proposed for 3D apply and very nicely explain. In fact, 2D helped us in identifying what is the role of lone pair electrons, S electrons, which we didn't emphasize in the 3D. Okay, but since the time is over, I'll go to the concluding slide and then stop. Yeah. So in 3D, we have shown that you have a parent high symmetry phase, which is metallic. You weakly break the symmetry, you will get metavalent bonding. If you break this symmetry stronger, you can develop ionic and covalent bond states, well-known bonding structures. And the characteristic electronic mechanism is you have mixed bonding, anti-bonding interactions, which amount to having kind of a multi-center bond in some interpretation. And it gives you a very long range electron transfer in the opposite direction to the motion of positive ion, giving you very large bond charges. And we verify the same applies in 2D. I acknowledge my student, Ragya, who's Dr. Ragya Arora, who's from Harvard, and Professor Rao, who, of course, has been relatively calm, but has been terrific to interact with over the last several years, and many useful discussion with other chemists who work on this type of problems in the world. Thank you very much, and I'll be happy to take questions. Sunil is.
Thank you. So from your summary slide, if you could you just show it again?
Sure.
I just wanted to understand, since symmetry breaking seems to be the physics explanation for going from metal to metavalent bonding. So this weakly broken symmetry, is this supposed to be a spontaneously broken symmetry or explicitly broken by the deformation? This I don't understand.
It can be deformation or it can be chemical. So
Okay.
if you say you have lead telluride, it's a explicitly broken symmetry with respect to antimony, which is cubic.
Okay, okay.
But if it is they do have spontaneous part also. If you have spontaneous symmetry breaking associated with structural distortion, then it's a ferroelectric ground state, which is non-centrosymmetric. And that's also available in GETE system in the phase diagram I showed. If you move along y-axis, you would break it spontaneously. Along x-axis, it's alchemical and hence explicit.
I see. But how is this related to the Peierls instability that you're discussing?
Okay.
I just somehow missed that connection.
Okay, maybe I'll just, if it's possible, I'll quickly go back. Yeah, so it is Peierls instability generalized to 3D. In Peierls argument, it's strictly for one-dimensional system. What I showed here is you have a Fermi surface, which, sorry, I'm too close to the speakers. And Fermi surface is nested. Sorry, maybe I'll just.
Yeah.
See, on the left, Sunil, is the Fermi surface. And I have pointed out that one packet of the Fermi surface, by the way, Fermi surface separates occupied and unoccupied states in reciprocal space. It displaces to another packet rigidly if you have this wave vector R. And this R vector is spelled out here, which breaks the translational symmetry by translation with 1, 1, 1, or half, half, half in A direction of magnitude. And that's the translational symmetry which is broken by unstable phonon, which is shown here.
But this is a discrete symmetry, right?
Yes, it's a
So
discrete
discrete symmetry is being broken by this vector.
That's
So
correct. Yeah.
do we understand that to be, I'm just not clear about the chemistry side, but is this a spontaneous, is this something that you add in the system or it's in the system?
It is intrinsic. This
Intrinsic.
Fermi surface,
Okay.
what we establish is a simple cubic metal with half-filled p band, always is unstable in this sense.
I see.
Yeah.
I see. Thank you.
Sure.
Just one quick question. In addition to the orbital picture, have you had a look at total charge densities, their critical points and so on?
Yeah. So not us, but many other people have worked on it. Wutig's group is focused on analysis which is entirely based on charge densities. And they are useful, but in identifying orbital mechanisms, they are limited in some sense. So Wutig and us, we are now collaborating in sorting out some open issues in this field now.
Yeah.
There, Professor Bhatt. Or
Hi, Umesh. Thanks for the great talk. Just had a small question. Have you explored structural distortion due to these effects? Like, can some material change its phase, or when it's meta, like GAC, GET, is it more susceptible to phase changes due to external influences?
okay, if I understood your question, Akshay, so others have looked at the kinetics of transition from amorphous phase to the cubic structure, and what is relevant is the formation of cubic motifs in chain-like structure, which is what we find in chemical bonding, that you have chains of 5 atoms which are sort of bonded together by the single molecular orbital, okay? Now, your question is whether structural distortions can tune this type of bonding. We find that if it's a ferroelectric type instability, which is a spontaneous broken in discrete symmetry, they don't change metavalent character, but they do bring in additional functionality of spontaneously switchable dipole moment. Germanium telluride is a very simple and special ferroelectric with 700 plus Kelvin transition temperature from that, but it remains metavalent on both sides of the phase.
Great talk. Experimentally, how does one decide if the symmetry is weakly broken or strongly broken?
Sorry, I really couldn't hear you.
We are talking about weak symmetry breaking or strong symmetry
Yes,
breaking.
yes.
How does one experimentally decide if the symmetry breaking is weak or strong?
Okay, good. Experimentally, I don't think it's simple. I don't have a good answer for you. Yeah, because see, historically, these properties, the understanding of these materials is developed based on the properties measured experimentally. So, if they are sufficiently anomalous from the expected nominal behavior, we would think they belong to the weaker symmetry broken states. But there is no, one measurement you can do is the band gap, which is narrower the band gap, weaker is the broken symmetry with respect to the metallic state. But that's not necessary to be always true. There are other materials which are not metavalent and have small band gap as well. Yeah? So you need to have these conditions satisfied. You have a half-filled p band, the structure should be sufficiently close to the parent structure that we identify is metavalent, and then one can tell based on the gap. But that's only one of the properties, it doesn't always determine. Thank you.
So I thank you all for attending this inaugural session, and now we have the group photograph and the tea. And please come back at 11:30 into the auditorium for the next session.
We have arranged for cars for those of you who would find climbing the steps difficult. So you can, the cars are waiting on this exit door, the exit on my right. You can just go there, and there are cars which will take you to the front of the building where the photo shoot is happening.
Come back by the same.
And then you can come back by the same cars.
It's only,
No, even when standing here, I'm getting
yeah,
the
it's
echo.
on this side, not that side.
Welcome back after the tea break, and now we have a very exciting 2-hour symposium. The title seems to have vanished from the screen. Can we go back to the first slide? Okay, so the Catalysis for a Sustainable Society, a chemist's perspective. And I have great pleasure in inviting Professor Swadhin Mondal to take us through. He's the convener of this 2-hour symposium. Swadhin.
Good morning and hello everybody. It's my pleasure to be here and to organize this mini symposium. The title of the symposium is Catalysis for a Sustainable Society. And I'm very thankful to the Academy for giving me this opportunity to organize this session. So we have very distinguished speakers, 3 speakers. So we'll give more introduction, but I would like to give a brief overview of the topic actually, how we can take it ahead and what chemists can do. Actually, the right title would be Personal Perspective of Chemist. So you may not agree with my perspective. For that you can excuse me if you are not agreeing with me. So let me define what sustainability means actually. I'll take the definition which was made by United Nations World Commission of Development and Environment, meeting the needs of the present without compromising the ability of future generation to meet their own needs. So that's the definition of sustainability. So we need to make sure that we are not taking all resources and we are not leaving for our next generation. I am from Bengal, so I remember a famous poet who very unfortunately lived only for 20 years in his life. 21 years he died. His name is Sukanto Bhattacharya. And excuse me that I had audacity to translate his poem, which means that I'll make this world habitable for this child. This is my commitment to the newborn. So that's the sustainability has to do actually. And catalysis is something which has a lot of role to play. Sustainability brings 3 elements in harmony. It starts with environment. Of course, we cannot destroy our environment, and which is connected with our society directly, and of course with the economy. So we need to make sure our processes are economically viable at the end of the day. I'll give an example for a pharmaceutical ingredients. A company in Netherlands was preparing a compound called fluoroguanil, had to close down their company. It's not working. Can you give me that? So close down their company because fluoroguanil synthesis. This is a molecule which was used to treat colic as well as spastic pain of the digestive and biliary tract. So 1 kg of fluoroguanil used to make waste 40 kg waste. So these are the waste molecules that were produced per 1 kg of fluoroguanil. And for the waste management, company had to pay twice the price than they were earning out of fluoroguanil. So it was not sustainable. And so that there brings us something called environmental factor actually, which can be described as E factor. As we know that chemistry plays central role in making molecules and materials, which is immensely helpful for our everyday life to relieve pain from disease and all. So this is the E factors today's chemical industry. If you can look at the E factor, fine chemicals has quite high E factors. There are many chemicals, what we produce today, is not sustainable. 5 to 50 and pharmaceuticals has about 25 and less than 100. So we need to bring or develop a method that the E factor goes as low as possible. It should be 1. So that we don't have to lose any atom, we don't have to lose any, we don't have to create waste for the future generation. So since we are increasing our demand of resources every day, and as a result we are actually depleting, cost of what we are paying is the depleting resources. So we are moving towards an unsustainable world because you are building a lot of waste we are generating in the chemicals. So one has to come out of this through disruptive idea, innovation, and that has unlimited potential so that we can break this barrier and then we can move towards, we can reverse this process actually. And there again, catalytic processes are very, very important. How to make process sustainable. What are the conditions our planet should really follow is that in a sustainable society, nature is not subject to be systematically increasing the concentration of substance extracted from our Earth's crust. So if we keep on taking substances from the Earth crust, then we are not going forward towards the sustainable society. Concentration of substances produced by society cannot be increased, and we cannot degrade by physical means various natural things. So a sustainable catalysis refers to the design and application of catalytic process that are environmentally friendly and economically viable and socially responsible. Socially responsible means, as I told, that we cannot create and accumulate more and more waste. Challenges with traditional catalysis is, of course, we are depleting resources. When we generate API in ton scale, we are obviously taking a lot of catalysts which are coming from the earth crust. And by definition, catalyst is supposed to be regenerated, but there is no ideal catalyst which can be regenerated forever. So eventually you are depleting. So I am going to take you through some grand challenge what catalysis can do actually. How we can deal with. Basically I'll take some example. Of course chemists can give an initial solution, but technology can come later. But what are the problem? What we can do is that one problem comes in my mind is the how do we tackle global greenhouse gas emission problem. This is the data actually I took from a very nice article which is published by Professor Govardhan Mehta and co-authors recently. So if you look at this, we are actually creating increasingly more and more carbon dioxide, which is a direct correlation with our greenhouse effect. We are already gone up by 1.1 degrees centigrade before the, if you compare the temperature, temperature before the industrialization, and we cannot let it go beyond 1.5 degrees centigrade by 2050. So it's very important that we must take place to set up certain goals actually. One is that net zero. Net zero emission means carbon dioxide, whatever we are emitting, we need to find a process by which we can actually absorb back whatever the process is, so that we don't have effective emission, but it's very difficult. I'll tell you why it is difficult. Because this red and black arrow has to be equal, then you need to understand that why it is very difficult. If you look at the carbon cycle, which looks very good, looks like that everything is going on circular pathway, but if you look at the time scale, you understand the problem. Let's say start with oil, you get a fuel chemicals and then burn to carbon dioxide, and then it can be utilized by photosynthesis to get the plant biomass. The geological process can create back again oil. So it's all good, looks like. But what is the problem? Problem is that this process, formation of the oil is about 5 orders of magnitude lower than the rate of its consumption, right? It takes millions of years, this process. So leading to depletion of these geological reserves and emission of CO2. So no wonder today 80% of global energy is extracted from CO2, which creates CO2. For example, oil 32%, 28% coal, 22% natural gas. You fly from Delhi to Calcutta. You are responsible for 180 kg CO2 emission. And you can understand that the CO2 emission is increasing day by day. Now it's close to 37 gigaton. Now we can debate over again and again and again which is the way, good way to do the CO2 emission to stop or keep it under control. There are 2 major thought processes. That one is CO2 capture and sequestration and storage, and one is utilization. How do you make it fine chemical back? Now, many groups think that it is versus against each other, but I tell that it is not against each other. It has to be and, right? So both the process we have to explore. So let's imagine why both the process has to be explored. I am a chemist actually, I should support chemistry to be all CO2 to be utilized, but look at the numbers. So imagine that you have a super technology that all CO2 you can convert into methanol, whatever methanol you require today. Look at the number. In 2022, methanol production is over 111 million metric ton. Another chemicals, we always talk about carbon dioxide with formic acid. The global formic acid market has reached only 750 metric ton. Formaldehyde, urea, calcium carbonate. You take all these things and everything you convert out of carbon dioxide with your super technology. Then even you cannot take care more than 1% carbon dioxide emission. Because we are emitting now 37,000 million tons of carbon dioxide. What we need to do in this situation, that's why I'm telling that it's not either or actually, it has to be on. And then what we have to do is that we have to make sure that we don't stick to only few reaction of carbon dioxide to methanol, formaldehyde and all these things, because that cannot solve the problem. What it can make it better is that you need to create more and more new reaction out of carbon dioxide. So, for example, can you make carbon dioxide to olefin, which is the monomer comes from petrochemical industries? So, for example, vinyl sulfide is the monomer used by polymer science, material science and all. Can you convert them? One of the ways, this is just I'm telling, but I'm not going to show my work actually today. So one of the ways we made olefin, carbon dioxide to new olefin, which is not known actually. Vinyl sulfide can be prepared and various types of olefins you can prepare, and then you can use for polymerization. One of the carbon is harvested from carbon dioxide directly. Another problem is that N2O activation. Okay? We are not caring that actually. Because why we should care about N2O activation? Because we are agricultural country. The rate we are emitting N2O, we are not able to utilize that. As a result, if you see the data for India, it's increasing again and again. And remember that N2O is 300 times more potent greenhouse gas than carbon dioxide. I am showing a very recent result from a group from Germany, Joseph Cornella. They utilized N2O to prepare pharmaceuticals. Which functionality comes from N2O to get a lot of pharmaceutically active molecules, and then you release nitrogen, which is a very, very inert gas. So that's one of the sustainable process if you can create technology. This is one process I'm talking about. Then another very important area, actually one we should talk about, is the waste recycling. Well, we have awarded Nobel Prize, not we actually, Nobel Prize committee. So Carl Ziegler and Guido Natta, awarded Nobel Prize in 1963 for making polymers. Now we are struggling how to break the polymer back because they are forever chemicals. If you take a banana peel, it goes biodegraded with 2 weeks. Plastic bottle takes 450 years. And plastic bag takes 1,000 years to degrade. We need to find out a solution how you can really go back to fine chemicals. This is again, Catalysis came out with a solution. I am showing you a very recent result by John Hartwig group from USA, University of California, Berkeley. They showed that, they showed back that you take the polyolefin, sorry, this is not playing, but anyway, you take polyolefin and then you can use 3 catalysts, iridium, palladium and ruthenium based, you can get back to the starting material, propylene back. So you can do that. The another thing is that periodic table, I would like to show you that there are certain elements which are used for catalysis are orange colored elements, cobalt, rhodium, ruthenium, osmium, palladium, platinum. And they have rising threat if we are going to use too much. We need to use more and more green elements, which is abundant for doing catalysis, but they are not catalytically active. What you need, we need a disruptive idea so that we can bypass this very, very expensive and rare metals, actually. If you look at Nobel Prize in catalysis, actually, so all have used, most of them, except one, actually. So we used always metal-based catalyst. And many of them are very rare. So can metal-free catalyst made with green elements replace rare and toxic metal catalyst? We need to do that. We need to think that. Here, once again, I'm bringing a Nobel Prize of 2010. And then you see that carbon-carbon bond-forming cross-coupling reaction, everybody think that without metal it cannot happen. With palladium, is a very rare metal. Now, I'll end up with this example that you can see that one can do without metal catalyst and you can prepare a lot of drug molecules by using simple reaction, by using simple organic molecule to do the Buchwald-Hartwig coupling to avoid palladium metal at all, because palladium metal in pharmaceutical industry, even if it is trace amount, it is toxic for our body, and we do take many medicine for years, 10 years, 15 years, lifelong. How much rare metal actually, how much heavy metal we are consuming, we don't know actually. So this is a method that we can do it without metal. This was not known, this type of molecule. What we need to do is that we are working in small pocket and we need to connect with each other, and this is a right for platform to discuss more about that, how a chemical engineer, how a process chemist, chemistry can discover reactions, but chemists cannot do scale up. So how can we utilize these processes, sustainable processes, to make a better society? So that is the topic today for our discussion, and we have very distinguished speakers, 3 distinguished speakers. The Catalysis for a Sustainable Society. I would like to tell you that, please note that 15 minutes discussion has been integrated with the talk. It's a 5-minute discussion. You can ask question and discuss about after each talk, so we'll not have later discussion. So the first speaker is Professor Matthias Dries from Technical University, Berlin, Germany. So we are very lucky to have him here because he was visiting Goa for other purpose. Professor Dries did his PhD with Heidelberg University and postdoctorate from University of Wisconsin-Madison with a very famous silicon chemist, Bob West, whose chemistry we learned from our textbook. And he built up and he's associated with various cluster of excellence, which unifies concept of various catalysts, which is needed, as I told today. And his area of research is synthesis of novel molecular function-based compounds with heavier main group elements, organometallic chemistry yielding molecular models for heterogeneous catalysis, electron transfer complex, and the synthesis of molecular single source precursor for nanostructures in organic materials. And he is decorated with various recognition and award. He is member of the European Academy of Science since 2020, member of the Berlin-Brandenburg Academy of Science 2014, and he's also member of the German National Academy of Sciences. He's awarded with Wacker Silicon Award, Alfred Stock Memorial Prize, and today he is going to talk to us about expectation of chemistry, all in to meet the needs of society. So Professor Dries, I invite you to be here. Thank you all.
Okay. Good morning. I'm very pleased to be here, and I'm very honored to have the chance to share thoughts about catalysis and perhaps as part of it to reshape our world. What I'm going to share with you is about what the chairman has introduced. I don't have to repeat this. We are all asked to contribute to this. It's not a matter of, we wait until somebody is doing that and then I will maybe follow on this. This is why I've chosen this title. If you go to a casino, you have the option to diverse, to spend this all over, or you said, okay, I think I have only one shot, or maybe two, all in. So, and what that means is this is another way of showing what we talk, what we say, what we mean if you say it's about sustainability. What are the expectations of the future? If you talk to chemists, and I guess there are some in the audience, but perhaps not all, you ask yourself, okay, chemistry, these are the people who make the world dirty? You have to clean it up. And in fact, it's not true that we make the world dirty, it's the way of using resources to the better world, to the mankind. And there are, of course, mistakes. As in nature in general, we're part of a nature, are mistakes. So it doesn't matter now to complain about, what is, let's go in the future, do something new and reshape. Expectation is this. These are words. But what does it mean? Behind that, I hope to explain that to you more clearly. Greener means that we do use chemicals which are not toxic. So as part of the synthesis is the question how we get rid of this stuff at the end of the lifetime in wastewater, in all this waste we produce. And in nature, there's no waste. Everything is in a certain way recyclable. And we need to adapt to this more rigorously. The other thing is, you don't want to make thousands of different experiments in order to make a compound. Here is the hour for the theoreticians. You should predict something. The prediction, the value of prediction, which basically is the difference between science and theology, right? So we respect each other, but the job of a scientist is to be predictive and not trial and error. So if you put all this together, you end up with this kind of advertising slide you have seen so many times. So Sustainability, and as pointed out very clearly by our chairman, is more than chemistry. It is a bunch of different business and thought aspects under one umbrella. And if you now go to the chemistry part as is, we have, again, in the chemistry, various different aspects we obey here. And if you talk about green chemistry, the green chemistry is a bunch of rules we might want to obey in order to make synthesis, in order to be producing better. Fortunately, we are not the first one who think about it. Of course not. The question is, who is listening? There are two gentlemen, 20 years ago, they wrote a book, Green Chemistry for the Practical, so practical use. And the definition of green chemistry is sometimes not clear to everyone. It's not making us happy. The green chemistry thing is the design of chemical processes and processes that reduce or eliminate hazardous substances. And so that means it's immediately connected to pharmaceutical, toxicological aspects. So what we inhale, what we drink, what we eat, everything what is on Earth we basically produce will end up in our chain, so to speak. John Warner and Paul Anderson. John Warner is an entrepreneur. He used to be a professor of chemistry in the University of Boston. And Paul Anastas, he's in the US as well, and he is a professor for chemical engineering and various other things. And they wrote this book. And they thought, okay, let's put all the different aspects together which define the green chemistry. These are the 12 principles of green chemistry. And you can start on the 12th and go back, it doesn't matter. They're all interconnected. What that means is, if you want to be really according to this rule, you're trying to make what you do as a chemist accordingly. Pollution prevention means if you do a synthesis, nobody next to you should be caught because of what you produced, right? Or if you do synthesis, you would like to be atom economic. Even if you produce water at the end of a chemical reaction, that's waste, actually, by definition. So why don't you try to make a reaction more efficient in this way? To cut a long story short, we hear about this. Catalysis is a key thing. What is catalysis? The kinetic phenomenon. It's accelerating a chemical reaction, lowering the energy you need in order to activate the process, right? So we're talking about more efficiency in using resources. And there are reactions which would never take place by its own, although thermodynamically easy to undergo, actually, on paper. Let's say N2 and hydrogen to make ammonia, the fertilizer. It will not take place without a catalyst. We would not sit here without this process, right? So which is basically feeding ours. So therefore, now we go a deeper step in asking ourselves, how could we do this even more efficient? In Berlin, and now I do a little advertisement, I'm sorry about that, but the point is, you will see, it's not that I'm hiring somebody or something. The point is, it's all about education. And we need a common language to do that. It's not enough to publish papers or to go to politicians and say, I need more money. It's all about us. We are the people. If we do not change, if we do not have the same language, we will fail. So we thought we had the chance. It all starts to have some funding, right? Of course. The Germans, in 2007, set up an initiative which was called the Excellence Initiative. It's about all disciplines, from astronomy to deep sea diving. Where are the best people trying to interconnect fields and to generate something new? And we had the idea, hey, catalysis is spread over in very different disciplines. In chemistry, homogeneous, heterogeneous catalysis, whatever that means, in biological catalysis. So chemistry and biology, they are not strangers. They're basically the same. Because if you look at the kinetic phenomena, we're running a reaction. So producing ammonia in a bacteria is chemically the same as we go to a plant, chemical industry, BASF, to make ammonia. The difference is the conditions are very different. Yeah? The nitrogenase starts the ammonia synthesis at room temperature and 1 atmosphere. The Haber-Bosch process takes 400 centigrade and 50 or 80 bar. Why is that? We said, okay, we should basically understand this. And so we set up this program, which is called Unifying Concepts Catalysis. It's another type of reunification of Germany, I thought. But let me tell you what that means. And we had the joy to do this for quite some time, you see here. And it was about the way chemistry, we as humans do, and mirror this, how biology in cells, this is taking place. And we focused that on activation of methane, activation of carbon oxides, monoxide, dioxide, these are key carbon-1 sources, and activation of hydrogen, oxygen, and water, and hydrogen peroxide, because this is something which, blue planet. That's what we are. And then another thing which is basically very complex is how reactions are triggered over a long time and space chain in nature, and we might be able to learn this to take it up as engineers to improve processes in industry. So why is that, and I come to that in a minute, so different? And now it comes the important thing, the most important slide, I would say. We thought, okay, this is not a program for making more scientific publications. This is a program to educate. So I had the feeling, and I always defined, because I'm the spokesperson, hey, this is a program where we make a new language, a common language. I said, this is the Esperanto of catalysis. And believe it or not, we started this before we got the cluster. We said we need a graduate school. And in the graduate school, you basically have, the assembling of all different characters and people in fields trying to contribute to the unification of catalysis, what I said about chemistry and biology. So we have every year scholarships, associate members, because not everybody was we associate. The academy does the same thing, right? You have fellows and you have associates. So we basically want to grow healthy in a way that we spread out, share ideas. Meanwhile, we have 140 PhD students. I can tell you 90% of them have a job before they finish. So we did some good selection. And half of them are going to academics after postdocs, spending some time somewhere else. And this is not a German club. This is an international forum. And what is also important, that's the difference to other graduate schools, I would say. You also have graduate schools. They spend the first 3 months in the same room. They're not allowed to go to the lab and disappear and do what's the specialty stuff in the first place. They have education plan. They write their research proposal. They present the research proposals to themselves and to the audience, to the committee, and then they get a tick after that, or say, you might have to modify that. And that's the difference. So they get the smell to belonging to one family. And we have to do that, I think. I tell you what the outcome, science papers, you can look up this. I think it's real comfortable, all good. But what is more impressive to me is what is the spin-off. When the German taxpayer, by the way, this was over the year, we got every year about 7 million euros, about 48 groups all over the place in Berlin. We have 3 universities in Berlin, University Potsdam, 2 Max Planck Institutes, Helmholtz Center for Energy, and so on and so forth. So in total, 9 institutions, okay? So that is to ensure that this has a wide range. And we thought we need, as a spin-off, something which radiates and has a gravitation effect. And that was my idea. Hey, gravitation effect? There was this man, Albert Einstein, who discovered that gravitation is a different thing and makes us our universe, basically. So we thought we're gonna assemble all the activities in a meta structure, and we then were able to associate research activities not belonging to catalysis on its own to this. So it's kind of a universal thing, right? To have the spirit and the common language thing. And we got an Einstein Center of Catalysis, which is an invitation to basically connect to, let's say, mathematicians, informatics people, genetics people, etc., right? So this is something which allowed us. And then, because we didn't not well, we're successful and also in the educational way, personal development in industry is such that they say, okay, we need another generation of chemists. Who are the best people? So BASF asked us to perhaps establish together a campus. So we now have, since 2012, actually started a campus, BASF campus at the TU Berlin. And that is called the BASCAT, the BASF Catalysis Joint Lab. And existed, 2011, there was the bottle of champagne, but actually starting off this was 2012. It has a funding period ongoing, and the topic shifted from resources thing to green chemistry aspects. I don't want to go into details. And we have 3 directors, and one of the directors is paid by the BASF. So we have permanently someone from BASF on our campus belonging to the team, which makes also a big difference. It's not only we want to have money, it's also we want to have the mindset change, and this is guaranteed by this. BASF has in Germany only 3 this kind of thing, and University of Heidelberg for homogeneous catalysis, KIT for battery research, and we are the heterogeneous campus, so to speak. Okay, new building, all facilities, so it's all in one. It's now, again, it's a unified complex where we do not only calculate, predict, but also synthesize and then test and then upscale, right? This is all in one building. And so it's all about how we see catalysis in the near future, making the gold standard in heterogeneous catalysis, which is basically the way of dealing with data. This is the gold in the future. If you know how to run, if you know how this works, what the parameters are which drive a reaction, you are in this. So it's, of course, again, a network in the catalysis and the data management world, which is basically here combined. Okay, I don't go into details, no worries. Gold standard, which means we're gonna follow a certain protocol. You see, again, it's not about publishing papers in the first place. It's about really to be sustainable, working with data which can be used later on. That's one of the drastic situations we are faced to. Many data in catalysis and research are among different standards, so cannot be repeated and cannot be evaluated. So this is a huge problem. And here is the way we propose to change that. And in terms of using resources, the chairman said this, we cannot wait until new oil is coming off. So we're taking that what we get from nature, which is the sustainable chemistry stuff. We get renewables from the nature, and we're learning what these composites are and use that as chemists. And finally, make a point about spin-off 3. What is the future of the young people? Why should they study chemistry? To learn all the things and ending up in industry, which is an established industry, had hard time to change. I recommend to go the 3rd pathway. The 3rd pathway is, why don't you just make a patent? You don't have to make a PhD actually for doing this, and trying to make your own business out of that. If you are keen in doing that, you don't have to go all through this, PhD, postdoc, somebody likes you or don't like you. So you said, okay, I have an idea, and I think even if it's a niche, and there is support for this, so we start off this. So this is something we created. So I created a pre-startup center for green chemistry. It's called the Chemical Invention Factory. And we have among them already 65 startups which came off, and 14 are business-wise successful. They stay on their own feet. That's great. And the success rate is not very high, we know that. And the trick is to keep them on campus, to give them freedom, and to allow also industry and potential customers to join. We do not rent space, okay? This is something which is not allowed. I think this is an intellectual platform which enables this. So we got a new building. The new building is paid from the state of Berlin and from the Technical University. We're talking about 9 million euros. At the time when we got the money, it was great. Then came this problem with the resources, pandemic and all stuff. So with that money, you would not get even half of the building. So fortunately, we could get more and stuff like that. But this is something which is ongoing, and this is a home for this third pathway. So what happens afterwards? Spin-off, we now go a step further. We make it more complex. Dealing with complexity is our business. We go for unifying systems in catalysis. So we would like to be like a cell, a biological cell, combining things where we have different steps of catalytic reactions which are interplaying and interconnected on time and space. And that's basically a long way to go. Most of the chemical reactions we perform in industry and on plant is we make a synthesis, we separate, we make another synthesis separate. As an outcome, square kilometers of a company is needed in order to produce something, right? What we eat, what we drink, what cosmetics we have is produced in this huge area. The vision is to shrink this, to basically scale this down on a level where basically everybody of us, even at home, you could produce something. I'm a big fan of this. The personalized way of synthesizing and making your life better. You don't have to rely on what big companies will sell you. I know that's very far away from reality. So this is I call this a greenopolis. Okay, why not? The difference is in biology, everything is this is a nerve cell, and while I'm talking to you, millions of reactions are taking place in parallel. This is a chemical plant. They're producing 1 or 2 chemicals. You see the difference is tremendous. And we need to basically make a bridge here in understanding and scale this in a different way in order to be able to do this reaction networks, what we have in nature, evolutionary, and what we by heart produced in industry to have a chemical network, and it's still, you need that huge space and time to be able to do that, right? So the dimensions are really dramatic. So in our research program, we basically interconnect various types of chemical reactions, of catalysis reactions, and we would like to learn from the feedback how we basically synchronize in time and space that this reaction can take place in one small entity, so to speak. And we're using the protocols of enzymes as well as chemical catalysts. Okay. And I like this animal here. We invented this animal. You see here, chemical catalysis, biological catalysis. So we get this conceptual movement, and then we thought, okay, we're gonna do this merge and focus on various topics. So we couple chemical reactions, chemical catalysis, biological catalysis, then the enzymes, chemical and biological, and then something which is extremely important these days is we're working with molecules which can be electronically accelerated with light or with electricity. So we do not need to rely on thermal chemistry. And that's called the catalysis of electronically activated molecules. What that is we will see in a second. Electronically activated molecules, we know this from photosynthesis. You have chlorophyll, and the chlorophyll gets a photon, and electrons are excited. Right? And this electron is then going away, and it produces a gradient, and you're producing proton-electron gradients, and they all go along a chain, and there, as an outcome, you're producing for CO2 and water, sugar, and oxygen. So this kind of process can also be applied, of course. Instead of activating chlorophyll, we can take chromophores, whatever you can do, produce in order to make the same, adapting this to the same processes for various reasons. We wrote an article in 2020 about this recycling thing. And Professor Mandel has pointed out CO2 is a big issue, and there are many people working on that. We have another focus here. The focus is what about the other very energetic, important molecules which are not so easy to recycle. But this is to say, if you want to produce photovoltaic silicon from silicon dioxide, this has an enormous carbon footprint. So 1 ton silicon has a carbon footprint of about 6 tons CO2. So if we do that, if you say, oh, it's a solution, all good, we have photovoltaics, and all this problem is energy is solved. We are not, we don't have the idea how to make silicon without carbon, right? So therefore, it's a lot of chemical research needed. And this is also true for other elements, phosphorus, oxygen, sulfur oxygen, which is associated to pollution problems, right? So we need to have catalysis in this. And the reason why it is so difficult is to reduce them is because of the bond energies. Here it's indicated, carbon-oxygen bond energy to pull apart the oxygen from the carbon, it's 799 kilojoule per mole. If you go to silicon, it's not far away from that. And if you go to phosphorus, the same thing, right? NO, same thing. So in other words, we should not stop at CO2 to look at this problem. We should go on in other types of molecules. And here's an example, a brief example. Phosphine oxide to back to phosphine. You need 2 electrons, and the oxygen goes off as an oxide anion. On paper, very easy. In fact, this is, when you ask yourself, maybe why is that important and what is the relevance here? This is the way we still make vitamin A. As an example, there are many other reactions where phosphine is used. The phosphine is transformed into a so-called phosphorus ylate, and this makes a metathesis reaction, so they change the atoms. Phosphorus takes the oxygen, the carbon, so you're forming olefins. This is what the first way to make olefins. It was such a great discovery. Georg Wittig, 1979, he received the Nobel Prize for that. So this reaction is ongoing, so you're left with phosphine oxide. And the question is, first of all, to collect the phosphine oxide, and then to reduce it back to phosphorus. And this is a very messy business. So when you take a pill of vitamin A, you should recall this, right? Separating something in industry is substantial in terms of energy consumption. Most of the chemical reactions we invent in our laboratory, will not make the step to industrial application because of the costs, of separation costs. So therefore, I bring this up here, the removal of phosphine oxide is a pain. And there are protocols, and people do that on a large scale. And if you want to reduce the phosphine oxide back to phosphine, you can use small molecule, high energy small molecules to do that, like silanes, boranes, and so on. This is done. Also, BASF did this, but then you're producing another type of waste you have to deal with after that, right? So you postpone the problem, basically. And chemical reduction, this is the newest patent from 1996. Look at this. They're using phosgene. Unbelievable. In order to make that guy here, and then using as a sacrificial reagent, so to speak, aluminum. They make an electrocatalytic reduction. So you're ending up with aluminum oxide. Also something you don't want, because this is also wasting resources, and it's very unlikely then to get this easily back. So this is the idea. Okay, excited state of phosphine oxide. We basically want to make electrolysis of phosphine oxide back to phosphorus. This is the idea. And of course, we were not the first one to tackle on this. All the protocols which are known, I show you here, are based on sacrificial reagents. So basically, you do the reduction, but you transfer the problem to another problem. You make waste. You're using aluminum mostly for that, so you have basically aluminum oxide production here. And one trick to accelerate, to facilitate the reduction is to lower the oxidation, phosphorus-oxygen bond order. It's a double bond, you see, to a single bond when you use a Lewis acid. So when this kisses the oxygen, the bond order reduces from 2 to 1, and then it's more feasible in electronic chemistry here to make this reduction process, but still high energy needed for that. Okay, this is the plan we had. We want to do all this, not only the phosphorus oxide reduction, but also the formation of the olefin in one pot, in a consecutive manner. Step by step, you can monitor, and you can basically do this with robots if you tell them when it's time to stop and to inject in the next step. And the recycling of phosphine oxide for the Wittig olefination reaction, we start here, we reduce, we insert the compound which we're going to make, then the ylate we need to make, and then we make in a final step the olefination and make this. And all this should be tolerable to make the reduction process. So we make a circular chemical process here. Again, something which is not very advanced, not very developed these days. And the research questions I'm asking, I answer it. Otherwise, I wouldn't stand here to present that to you, right? So can we do? And the answer is yes. And there are a couple tricks. I said you have to lower the bond order. The problem is, why is it so difficult to reduce that electrochemically? The problem is that the phosphorus-carbon bond energy is lower than the phosphorus-oxygen double bond energy. So whatever you do, you excite electronically, you give energy, it's likely that the phosphorus-carbon bond is broken. And this gives you a messy product mixture. You don't want that. Therefore, you need to basically activate. And what we use is an organic acid, Lewis acid, which again lowers the bond's odor. But at the same time, when we do later on the reduction, we get a product. In that case, when we use methyl triflate, methyl cation, we get methanol. And for methanol, going back to a Lewis acid like methyl triflate is not a problem. So we, again, these substrates we use here in activating can be recycled. Hey, that's cool. And when you submit such things to a journal, you'll see how the world is. An organic chemist gets this as a referee, says, of course, this is known. And electrochemist says, well, is that of relevance? Here we have a philosophical problem. You have to bring all this together. That's a showcase. It's just a starting point. Doesn't matter where, in which journal, all this kind of, I want to encourage you. Give all this big name journalists shit. I'm not frustrated, but look to solve a problem first. And all this honor stuff and all this kisses come afterwards, no worries. But I think we need to be really focused here. Now, if you do not apply this Lewis acid trick, you see, you gain not much energy if you add an electron in this, so exciting. But if you put this guy on here, the methyl oxide here, you gain 60 times more energy. Whoosh, you're gonna go through this, right? So, everybody can do this. This is a setup of the electrochemical cell, divided cell, and you can look at the phosphorus NMR spectroscopy when you have the phosphine oxide. This, of course, there is an electronic change. And then you do the electrochemical. This is a cyclovoltammogram. And you see here dramatic lowering the energy you need in order to do that, 870 millivolt. And you do this, you're using a silver electrode. It's a silver cathode. This is where the electrons come from. In acetonitrile, not water, because otherwise you would produce hydrogen. Protons in water are also hungry. But you see here, this is a not so happy. We were not so happy, 93%. We got back to phosphine oxide and methanol. And the reason for that, I told you, is this, all molecules are lazy. You need to activate something that they fall apart. So we need a Lewis acid for doing that. And I show you why. So you go all the way along here, this electron comes in, and now if you have that species here, before it comes to this game here, you're losing, you're gaining minus 50, you have another process where this bond can also be cleaved. So you have to ensure, in the presence of a Lewis acid, that this process goes in the right direction. And what we use as a Lewis acid was scandium triflate. This is a redox innocent Lewis acid. It sits there, it waits until it's ready to take off the meth oxide. Look at this, jump up to 79%. And we tried to find other stuff, but this was at the moment the best one. What are the drawbacks? This is almost stoichiometric amount. It's a high amount of scandium triflate. Although we can recycle, that's not what we wanted. And the other thing is silver electrode. You don't want to use a silver electrode. Are there alternatives? But before I come to this, I show you we really went all the way around because we made, this was the first paper we published, we could basically make olefins from that in one pot. And all the products, it mixes, it doesn't harm. And then you have a filtration process after a certain time, and you have a certain concentration, and then you can basically work this up. So this is something which was really according to what we had in mind. Well, nice. And then we thought, okay, could we get rid of the silver thing and platinum? And then we said, okay, we use different types of Lewis acids, and this is one We use tin triflate. Tin is cheap. And when we did this, we took the electrode, we used it and dipped it out. The platinum electrode turned black. And when we investigated what is on the electrode, it's elemental tin. I said, wait a minute, if elemental tin in this way, look at this, conversion rate, 98%, that's great. Faradic efficiency, 79%, super. Can we do using tin instead of silver at all, and platinum? So we went in a shop, we bought staniol full and used it, folded it as an electrode. Yeah, it worked. Because when you use tin foil, look at this, 92%. What it means is we now, and we do not need any additional Lewis acid. So the tin has a dual function. It is a metallic conductor for the electrodes. Electrons have to move. And it forms Lewis acidic sites. So they do the job that the meth oxide is carried away. That's great. We studied that, why is that, and so on. I skipped this. And now we are ready to do that, right? So George called me up and said, let's do it. Now we do this without this, silver, platinum, scandium stuff. So we make this kind of starting material, and then using the tin cathode, we were able to show that we can do that in reasonably also starting materials which are used in order to make pharmaceuticals. So of course, I'm not an organic chemist, but was pleased to see that colleagues said, hey, we're interested in that. Why should we, This is also in the mindset of this systems in catalysis and this transfer of substrate stuff and so on. And this is my proudest slide in this. So we make even nature products by that. And look at this guy here. We could make the starting material in 80% of vitamin A precursor using that protocol here. So all this was for us just perfect. What's the future? The electrons should come from renewable resources. So we do this reduction thing, and we oxidize an organic we can extract from nature, from wood, for example. And giving rise to starting materials which are used in other purposes. And look at that, we combined. You can do the oxidation of alcohols to aldehydes, and the electrons which are liberated here are used for making this reduction process here. So at the same time, we can combine. This is called paired electrolysis. You see here, we're scaling the complexity. We make circular things, and then. That's the future. And, everybody is invited to join this. And by the way, you don't need purified compounds, organic renewable compounds, to deliver electrons in here. We're making something which is perhaps of interest by its own. 12 principles of green chemistry. Let's do it. Thank you so much.
Thank you, Professor Matthias Dries, for your wonderful lecture. I'm sure, the concept he is trying to establish is extremely important, and I would like to see questions or any queries coming for the discussion.
I forgot this, sorry about that. Most important, the people who did the work.
So before you start, actually, I'll start with a question, actually.
Sure.
It's more technical,
Sure.
Professor Dries. So it's excellent that you could do phosphine oxide, because that's the Wittig reagent, actually. Basic reagent, and we always, phosphine to phosphine oxide goes back. But there is parallel another problem. What is your comment about that silicon oxide back to silane?
Right.
So that's one of the problem. Or boron always end up with BOB or
Right.
SI.
Yeah, that's a very good question.
So it's probably more difficult. I don't know actually. So can you?
Yep.
Is it possible to do that?
So if you look at the structure here, I told you we have the oxide, and when we basically lower the bond order, we add an Lewis acid, organic Lewis acid, we get this. This can be adapted by silicon compounds. The silicon has 4 electrons, tetrahedrally coordinate, but it has no charge. So you can basically take that same thing here if you have triphenyl silicon O-methyl, alk oxide, siloxide, and trying to reduce that back to a silane by what? Lewis acid where you have to add the Lewis acid again here to make a silicon cation external addition. We're currently working on that. We have indication that works. The same thing is true for boranes. Now, if you want to do this with silica, SiO2, you need to produce soluble silicates, organosilicates are known, and to find the right Lewis acid to trigger that. I'm sure one is able to make elemental silicon nanoparticles in solution at reasonable conditions.
That will be really great. That will be really good. Thank you. So any questions coming? Anybody wants to ask? So, yeah.
All right. No, very nice, of course.
I see that you have a very large research group in Berlin University, I mean, where you are working. I am just curious to know how many Humboldt Fellows you have hosted during your this research time, because there is a large number. India's total Humboldt Fellows, chemistry shares a large number.
Right,
so that's why I'm asking this question.
Yeah, we do have, of course, guests from all over the world as Humboldt Fellows. In numbers, I personally had 9. And guess who was one of the? So, this is one of the things to interconnect us, right? But we also offer internships and guest professorships in the program. And yeah, so, but you're absolutely right. This is important. The attraction, exchange, and of course, the most important thing, the last slide, the colleagues, I mean, the students who did the work. This is about, if you make a conference, the students should talk to each other. More space, more time, more experiments in ways to communicate. So this is on our side. If at a certain age, my age, I'm an old guy, so you need to, give the next generation the opportunity to do that.
Thank you. Thank you, Professor Rees, for your excellent, wonderful presentation.
Thank you so much. Thanks.
Now, we'll move to the next speaker, Professor Sebastian Peter. Professor Sebastian is from JNCSR, Bangalore. He has obtained his PhD from University of Münster in Germany, and he had a postdoctoral fellowship at Max Planck, one of the Max Plancks in Germany, and in Northwestern University. He works on carbon dioxide capture and utilization, water splitting and fuel cell, solid state, and structural chemistry. Sebastian, please.
Good afternoon. Myself Sebastian Peter. Thank you for your kind introduction, and I would like to thank Academy for inviting me and to give a lecture on sustainability. And it is a nice platform to showcase the activities we are currently doing for last 1.5 years, or we started in 2015. Already Chair and Matthias, already spoke about a lot about sustainability. That made my presentation quite easy. So here, but I just only summarizing only one particular problem currently we are facing. Every day in newspapers, social media, scientific magazines, this particular compound CO2, always we talk about CO2 issues, CO2 related issues, how to tackle that when people talk about capture, sequestration, utilization, storage, etc., etc., etc. So, and you can see that Catalysis design, and this is the heart of the technology. If you are smart, I'm a scientist, material scientist, the experience and expertise, how well used to develop the catalyst, and then how that can be scaled up for the technological solution here. That's what I'm going to do here. We can say that one, okay, well, I'm not using any automobile, I'm not responsible for the, this global warming. No, we all equally responsible, or at least some portions, we are responsible. And if you look at this figure, anything that we are using daily that is coming from oil, say for example, whether your shoe or dress or whatever it is, anything that you are using. And it also used for energy source, you can see here. At the same time, we are also depending on these resources, already mentioned that oil, coal or natural gas, whatever it is, or even talking about other energy sources. Over a period of time, the demand is increasing, and you can see that extrapolated one by 2040, this graph is going like this way. It is actually predicted 2015, but you can see that when some of them are exponential growth. And when we do this one, all kind of chemical reactions happen. When you take a coal and you burn it and you get energy, but during that process, you produce carbon dioxide. When you take natural gas, yes, same thing. Or you take even petrol or diesel or whatever, you can see that one producing. Massive amount of CO2 producing. One number provided by Swadhin in this introductory remark, aeroplane. When I put it on the road, if you drive your car 10,000 kilometers, 8,000 pounds of CO2 you are dumping to atmosphere. It's a massive number, and you can see that one amount of, the number of automobiles, coming, every household, at least 2, 3, 4 cars are there. Each individual, they are going to drive, and I have 4 vehicles at my home, and I can understand that this is a massive problem. No, we don't want to stop anything. This is a part of the development, but when it is a part of the development, what are the solutions we can provide? That's what I'm going to address here. And if you look at this cartoonic presentation, last century or more than a century, and you can see that the temperature is increasing because of CO2 level is increasing, and around 2 degrees, and you can see that one in a website like all this kind of website, or if you go to this observatory in Hawaii, and you can see that every day basis, you can see that second decimal is increasing. And only time actually that came down during the COVID time, because most of the things were shut down, and that as of now today is 418.84 ppm. Okay, it was actually gone down to 403 during the COVID time because of most of the industry, car, etc., and all shut down. And it may touch by 450, but that is a mark everybody put forward. We should not cross beyond that one. It end up in series of issues. It can end up in problem with your organs, biological systems, marine life, or agriculture, everything. So you can see a lot of articles. One figure I want to show, this is IPCC report, International Panel on Climate Change. It's published in 2020. You can see that the shaded area, it's going to be underwater by 2050 if we are going in this way. The place we are sitting here probably underwater if you are not going to take a proper attention. It's a serious matter, and we have to take the graph either to stabilize or bring it down to save our sustainable life. You imagine a lot of people living on the seashore, like, I mean, if you take a city of Mumbai or Kolkata or Chennai and all, and it completely, I mean, a massive, I mean, problem. And you can also, I mean, understand that when many fishermen living with the life, I mean, the fishing, and if you want to, catch a good fish, you have to go to the deep sea. And you won't get, I mean, the good fish at the seashore. Automatically, the price of, the cost of fish actually going up. You cannot imagine one sea fish if you want. I mean, if you want to buy, it is around 1,000 rupees, 500 rupees. It's expensive compared to last 5 years. So it is a massive problem. But with that, as I mentioned, I am a chemist, and I want to showcase certain activities. I will not go to the deep of the chemistry here. However, if you look at the figure here, we work on direct air capture. That's nothing but capturing CO2 from air, concentrated CO2. We also work on, I mean, the really concentrated one, but there are technology available. Capture CO2, how to convert into chemicals and fuel by photo, thermo, electro methods. Many chemicals, ethanol, C1, C2, C3. I will show some examples here. We also work in the area of hydrogen production. This hydrogen can be utilized for the reduction of a CO2, or this hydrogen can be used in the fuel cell. If it's fuel cell hydrogen, there is no CO2. On the other hand, if you are using methanol in fuel cell, CO2 will be produced. That CO2 can be captured, and then you can have a cycling. So all this process, I mean, what is my job is to develop the catalyst to bring down the energy that mentioned in the previous talk, and to make it as actually very efficient way of, or economical way of, processing that. I just bring out the price here. This is published in Nature Catalysis. Sorry, I did not cite here. So you can compare, this is a projected one. Current market price, if you look at here, and produced from CO2. If you take it, scale it up, there is a projection that one, we can be economical process, except methane. Methane is not possible from CO2, although people talk about CO2 to methane. I also published that one. But it's a difficult task because thermodynamically, I mean, there is another counter, I mean, and also methane production by natural way, it is a difficult. So all this chemical can be processed, I mean, economically if you develop proper catalyst, along with the proper engineering, a combination of all together can be done. In JNCSR, what we have achieved, if you look at that thermo, electro, and photo, all these chemicals we synthesize from CO2. Okay, you can see that around this area, among that one, we scale up methanol to the pilot scale capacity, and then DME and methane. This is up to 300 kilogram of CO2 per day in the JNCSR campus. We tested the facility for the conversion of CO2. I will show the facility. During this period, we designed the catalyst. There are a lot of interesting way to design the catalyst. You can see that you can make it in a different nanostructuring or different types of support metal interactions. That also play a beautiful chemistry at the interface, or shape, or different types of polymers, adsorbate, core shells, etc. During this period, you can tune this intrinsic activity and increasing number of active sites. So there's a tug of war between what should be optimized. So that optimization needs a lot of research activities, a revisiting of this one. It is with the help of theoretician and our own understanding experimental way of designing the catalyst. So I will take you one first step, CO2 to C1. C1 is actually carbon monoxide, formic acid, formaldehyde, methane, and methanol. And if you look at the mechanism, it's very simple for a chemist. Probably outsiders maybe it's quite complicated. But you can see that any of this product can be formed. Depends on the way you design the catalyst. And I want 100% conversion, 100% selectivity. But practically speaking, it's difficult. What happened actually when it is not 100%, it ends up in actually purification cost. That purification cost depends on what product you are getting. If it is one gas and one liquid, yes, easily can be separated. But if it is two liquid, it is difficult. So that cost will be coming to the picture. So how we can smartly do that? We have a lot of work. I will not take too much, but I just give the emphasis. Say, for example, palladium and indium, two classical metals. Palladium is well known for hydrogen production. Indium in the indium oxide CO2 to methanol. We made a bonding between them and then make an intermetallic alloy and cover with the indium oxide, protecting. So the protection is nothing but to protect the oxidation of palladium. If palladium oxide is forming, it will form carbon monoxide. So I want formic acid. So to protect that one, I do this one, and then during the course, if it is not protected, you can see that carbon monoxide is getting Faradic efficiency close to 80%. It's nothing great value. Faradic efficiency 100% reported by silver at a different particle size. Or if you want to make a syngas, say for example, syngas is nothing but a standard synthetic, what you call fuel for the production of any hydrocarbon you can think about it. So, but the trick is actually how to tune carbon monoxide to hydrogen to have a molecule, a compound that you are looking for. So here this is very fundamental work. We designed this as porous organic polymer with a different metal. Cobalt is favoring for hydrogen production, and zinc we are favoring for carbon monoxide formations. You can tune, and there is a charge interaction, charge transfer between porous organic polymer and then this metal favoring for the syngas 1:2 ratio, and that 1:2 ratio we can do. Again, this is a photocatalytic green energy way of producing. Or if you take, Sadhin Mandal already mentioned that one, metal-free material, how we can do that one. So metal is always expensive, metal has its own implication, etc. Again, this can be also tuned. You just take a system, it's a planar molecule, and then twist it by designing, catalyst design. When you're twisting that, the chemical nature is changing, and it is a selective conversion of CO2 to CO formation. Again, or if you go to methanol, so that is a carbon monoxide and formic acid. If you go to methanol, one work we have done, Professor Wakmar is actually collaborative partner. He did the theoretical calculations in that one. So there is a plant in Iceland that is manufactured. I will show the plant. That is done by, Professor George Oller, Nobel Prize winner, and then Surya Prakash. And their plant is actually the conversion is 22% of CO2 to methanol conversion. This is a 4,000 ton of methanol per year capacity production. They use geothermal electricity, but they use a pressure 300 bar. 300 bar pressure, you need a lot of energy input in that one. And here, the attempt was to reduce the pressure. You can see that at 20 bar, it's 16%. Compared to that one, that is a 22% of CO2 to methanol conversion. But we have the record now, 30%. I'm not going to show that one. But the idea is actually during the operant condition, that molecule slowly transform into a stable molecule, and that is actually giving the activity. Or if I take another example, again, my aim is actually to keep the feeling that on how the design. If you take a graphite, graphene layers are there, and there is a two-dimensional. And like that, if you design a system here, two-dimensional system, when you do this electrochemical condition, this metal can etch it out, and the metal can form oxide. That will change the game. Okay? Here what we have done in this case, this is a two-dimensional, this is a three-dimensional, and gallium is etching out. Gallium is forming a thin layer of gallium oxide. And that thin layer of gallium oxide smartly doing CO2 to methanol process. And we got a record value. This is holding the highest value of Faradic efficiency, CO2 to methanol process. So I am taking a little bit, complicated one. If you go to C2, there are a lot of mechanism reported. If you take an ethylene path, or if you take an ethanol path, all this molecule you can get it. Okay? Along with the C2 molecule, you can get C1 molecule also, carbon monoxide, formic acid, etc. and all. So eventually end up in your product mixture probably 5, 6, 7 different types of compounds there. As I mentioned earlier, purification of these compounds is extremely difficult, and that is one of the reasons still the technology is not economically viable. Well, we continue our journey from methanol to ethanol, and we design, I'm just making as a case here, red phosphorus, natural abundant species. And you can see that there is a band gap. This particular, only if you take a red phosphorus, you end up in actually formic acid. And one problem with the photochemistry, there is a easy way of electron-hole recombination. So the available electrons are less, and the band edge positions also not in favorable for the product we are looking for. So we tuned this material with the band edge position and entrapping the electrons here, and that gives ethanol. And with this one, we also tested this catalyst under the sun over a period of 8 months. Morning, evening, cloudy, sunny, etc. and all these conditions we tested. And you can see that in June month, I'm almost 75% compared to the artificial light that we used. So this is around 35 micromole of ethanol per hour of, per gram of catalyst compared to 55, 52, we are getting. So then we continue that one. Another molecule we designed. This is another example, Bi2S3. Again, what I'm saying that this compound reported. So as a chemist, how to modify the compound in favor of the chemical you are looking for. You can see that's kind of a ladder structure. We introduce chlorine into that one. The structure change. During that structure change, this bismuth 3 plus, that changed to bismuth 2 plus at here, and bismuth 3 plus, delta plus and 3 plus, delta minus, charge polarization. When this charge polarization come into the picture, the intermediate coming, that is nothing but CO and CHO, stabilizing, and it is forming CC coupling. So to stabilize that CO and CHO, design this catalyst, and then eventually you end up in ethanol here. Ethylene, again porous organic polymer, and we tuned this one, charge transfer from polymer to the metal, and that facilitating proper carrying, and either this kind of organic moiety or this kind of organic moiety, that will tune the charge transfer and then charge what you call band edge position. And with this one ethylene, we got 98.9% selectivity. 98.9%. Again, I don't say that it can be scaled up. It is not possible because it's a photochemistry. Efficiency is less. It is very nascent stage, and we cannot do it at the moment. And then we continue this one. You all know that one, zinc sulfide. Most of might have studied in +2 class or at least in the BSc class. Zinc sulfide, Wurtzite structure. And you take a copper on the right side, left side, and gallium on the right side, copper plus and gallium 3 plus. Substituting at a copper, and you get zinc, and you get a charge polarization again. That is also giving ethylene. And here we improve the record. It is a 200 micromole per gram. We are holding the highest record of ethylene in terms of yield by photochemistry here. Then acetic acid, I'm going through fast, and then we got a very good Faraday efficiency, close to 0 potential, very close. And we continue to propanol, and you can see that particle shape we control, either it is a sphere or cube. When it is a sphere, the crystallographic surface will be different. Packing density of atoms are different, and that will actually, both are giving propanol. If the packing is better, that will give more propanol. And we got a propanol close to 17%, and this is considered as one of the best in the current scenario in propanol. And then we continue butanol, and here we take a simple Fe3O4 iron oxide. This is also natural abundant. If you take just iron oxide and heat it at a high temperature and pressure in the presence of carbon dioxide, it will form iron carbide. That iron carbide, there was a talk olefins, it will easily form olefins like butylene, propylene, etc. and all. So what we have done, actually introduce indium into the lattice, and that even change, create a strain within the system. The strain actually push the Fe3O4 into different oxidation, different coordination environment. So that changes the mechanism, end up in higher alcohol, like a butanol, pentanol, heptanol, and even isobutylene. Whatever the cosmetics we use, the fragrance, isobutylene, that also we got from this product. So, but that's a very small amount, it's only 2%, 3% only, but higher alcohol we got a large amount. So what we have done, the amount of CO2 absorbed at the surface, and you can see that it is increasing with another modification is increasing. So I have taken all this, we have published almost maybe 25 papers, including original article, review article, viewpoint article. What's the idea actually, how the journey from, the basic one, how we can improve the catalyst, chemistry to have a better product distribution. This is the first warning, right? Okay. So product distributions, we can do that one. So the dream project probably photosynthesis, you never know. How you can mimic that photosynthesis in the laboratory and get as good as or better as CO2 to glucose if we can produce. Anyway, I will take one product out of all this one product, methanol. Already mentioned methanol economy. You can see that lot of advantage. It can be used in fuel cell, more stable than hydrogen, sustainable, renewable, multiple application, eco-friendly, etc. and all. All this were there. And if you look at the energy contained per volume, you can see that starting from diesel up to hydrogen in high ambient condition or higher vertical pressure, etc. You can see that methanol is somewhere in the middle of that one. It can be considered as a good fuel. And also government of India proposed methanol economy. It can be blended M15, or even Chinese company, they already introduced the cars actually M100, 100% methanol based engine. Or if you go to Israel, they have, Italy, they have A20, that is methanol and together with the diesel that can be. So this is considered as a fuel. This is not a new one. 1973, there is a science article written by these two gentlemen, and then you can see that they proposed methanol economy. At that time, the boom of ethanol, E10 came into the picture slowly after some time, and even it was introduced in Chicago. It was introduced in Chicago. And you can use it, even the cold condition also. Somehow it not turned out to be good, and Professor George Olla, and he was a student of George Olla, and they started the work way back in 70s and 80s, and he got Nobel Prize in 91 for his contribution to the carbonate chemistry, and they started a company in Iceland. The reason I can tell you, Iceland they started because of the geothermal electricity. The cost of electricity here in India approximately 7 to 8 rupees if you are using the grid technology. But this is very cheap, and you can see that around 4,000 ton of methanol they produce at a higher pressure and everything. And there's another project here in Germany and a couple of projects in China, etc. and all. It took almost 8 years, 9 years to reach the TRL level, technology readiness level by 8 or something like that one. Okay. But this plant cannot be taken into India because electricity cost is high. Hydrogen is actually cost is also very high. It's very difficult. So what we have done, we started this journey in 2015-16, and I just introduced one term, space-time yield. That's nothing but gram of methanol in a gram of catalyst in an hour. So typically, publication comes conversion and selectivity, but if you want to go to the next level, it is not the one. We have to consider all together. So you can see the generation of the catalyst, my students, develop, and also in collaboration with the Pune, NCL Pune. And you can see that during the period, there are papers came into Science or Nature, etc. It's a healthy competition, but we hold, record of 5 catalysts at the current scenario with the best space-time yield. I'm not saying that one, we scaled up. We only scaled up this well. So most of the catalysts we cannot scale up because of various reasons. So what we have done, we started a company way back in 2016. I'm not going to the detail. And we also came into the picture of Stellaris noted companies in the various area, and then you can see that in carbon sequestration along with the carbon clean solutions, we are already listed in that one. And carbon clean solution, they recently commissioned a plant of a 5-ton capacity of CO2 capture from steel, and Tata Steel, they started that one. Anyway, this is a technology. This is the CO2 capture. We have a partner, and this is the technology we have developed. I'm not going to any engineering part, but there are engineering partners involved in that one. And then recycling and the product distillation, and finally electrolyzer, and we all integrated together, and we demonstrated this technology at a various platform, both national and international. And we also got an ISO certificate in that one that is available in the website. You can download and then understand the technology. And the technology life cycle analysis of the technology done by University of Calgary, and then endorse the technology. This can be a carbon neutral technology with a condition if the hydrogen is producing from renewable energy. Okay, so this is a plan. This is a building in JNCSR, and you can see that various stages starting from catalyst synthesis, reactor, and various control unit, and then you can see methanol distillation. Finally, you can see that methanol collecting by the student. So this is 300 kilogram of CO2 per day capacity that we have done at JNCSR. I just bring the cost of the item. 1 minute I will finish. Yes, so here we calculate the cost. It's in the range of 20 to 24 based on the utilities. Okay, it can vary if the CO2 coming amount, I mean, if it's a what you call food grade CO2, the cost will come down. And if you compare the market value, this one, and you can see that the market, I mean, particularly China or Asia Pacific region, how this is actually. Currently, we are working with the CMPD and CAL, Coal India Limited, to build a plant with a capacity 1 ton in the single cycle 500 kilogram. And you can see that this is a 650 megawatt plant, and this is a chimney, CO2 coming from here, we capture and purify, and around 3 kilometers we are building the facility for the conversion of CO2 to methanol. And we have also anyway Center of Excellence funded by DST, the generous fund for 5 years. This is actually to make a strong network within the country for the sustainable solution, particularly in the area of carbon capture and utilization. And I welcome all of you, I mean, so we can interact if any common practice is there. So finally, I would like to thank my team. There are good bunch of, so very strong, group of students. They develop this catalyst and scale up the catalyst. I can tell you, I scale up the catalyst, I mean, even with a capacity of 10 kilogram per batch capacity at the site. We, I mean, customize that one. But beyond that, we did not work. We had to work with the big agency. So my last slide. So we are making the tree of products from CO2. Okay, we are growing, but at the same time, we are going to the root also, from CO2 to carbon nanotube. We made this one, but we yet to understand the chemistry there. It is in the early stage of the result, because it's a lot of challenges involved. With that, thank you very much. I'm happy to answer the questions if you have.
Yeah, thank you, Sebastian, for your great talk, actually. So you, in fact, continued what Professor Matthias Dries was telling,
Exactly.
actually. Yeah. So in the interest of time, I'm not taking any question or further discussion. So we'll just directly move forward to the next talk by Professor E. Balaraman, who is from IISCR Tirupati. Professor Balaraman did his PhD from University of Hyderabad, and then his postdoc is from Weizmann Institute of Science, Israel. And now he's working on CO2 chemistry. He utilizes CO2 as a C1 source for doing variety of value-added chemicals. Professor Balaraman.
Good afternoon. Thank you, Chairperson, for your kind words. At the outset, I would like to thank the Chairperson, Professor Swadim Mandal, and then Academy for giving this platform to showcase few of our research work and what we have been doing at IISCR Tirupati, how our research contributions helps for the sustainable development. And most of the industrial processes are mainly dependent on catalytic processor. Over 90% of chemical which the industry produces is based on catalysis, right? And most of these catalytic reactions we have to depend on precious metals, for example, palladium, ruthenium, rhodium, iridium, etc. Now, but ultimate aim is to replace those metals by a metal-free catalytic system. And Professor Swadim clearly explained how this group exploited a metal-free catalytic system for various synthetic transformation. But that's in the futuristic thing, because we have to go long way to make the things sustainable. And now that presently we are in an era to replace the precious metal catalysis by non-precious metals, particularly So basically based on the first row transition element, particularly we are working on manganese, iron and nickel. And how one can use these non-precious metals for a various synthetic transformation. So both the speakers are discussed about how one can use the carbon dioxide for the production of various important compounds including fuels. Now I'm going to touch upon few things and based on non-precious metal catalysis using alcohols as well as the CO2. These two are fundamental feedstock chemical for making various interesting compounds. And my first talk I'll be discussing about how one can utilize alcohol as a sustainable feedstock for making various chemicals. And second, we'll also touch upon hydrogen generation from waste material, and finally CO2 to polymers. And you look at this slide, by looking at this slide it reminds us as people wearing the mask is a COVID situation, but this is not the one. So what they are doing is they are trying to dispose the chemical waste produced by the various industries, particularly pharma industries. This is a place called a Valley of Drums in Ketsuki, and you see that so much of chemical waste was dumped, and these two gentlemen trying to dispose this. But you know, there's a proverb called prevention is better than cure. So before producing this, you should mitigate. Before mitigating this, you should come up with a new type of solution how one can avoid the formation of all this chemical waste. So this sustainable catalysis in an affordable chemical manner, this is the one which gives a kind of solution, right? And with that, several world-class companies which are listed over here, they are partner of Organic Chemistry Institute. They had a brainstorming section almost a decade where when I started my independent career. They discuss the reactions that are frequently used in the industries, and they also discuss what is the waste management, how to mitigate those waste and all the things. And these are the reactions which they are routinely using their industries and also produces a copious amount of waste. So one of the reaction, if I look at it, this alcohol activation for amination reaction or CC and CN bond forming reaction paid much attention, and you see out of 6 companies, the 5 companies they voted, and they need a better solution. Presently what they are doing is they want to have an alternative or better solution. The only solution they prefer is a catalytic manner, how one can activate the alcohol and use alcohol for various chemical synthesis. And based on non-precious metals, always is most welcome one, right? And removal of hydrogen from alcohol, this is the way one can activate the alcohol, and it's not a simple process, it's a thermodynamically uphill process, right? And you must require huge amount of energy to remove hydrogen from adjacent molecule of ethanol. So you must require a suitable catalyst design for that to do the dehydrogenation, and we have been working on a catalyst design based on the non-precious metal for this very interesting reaction, that's dehydrogenation of alcohol, right? And why non-precious metal? It's obviously all know that it's relatively much cheaper, and very important things are these elements are biorelevant, and if you look at the toxicity level is concerned, except cobalt and other things are relatively toxic when compared with the precious metal which mostly used in the industry for making various chemicals. And however, while working in the non-precious metal complexes, one has to encounter several challenges. What are the challenges? So the metal dissociation is one of the problems. So metal comes out from your ligands. So you have a metal nanoparticles, so it's very difficult to understand the reaction, sometimes there will not be any reactivity. So you must have judiciously design a catalytic system to stabilize this metal center, particularly the 3D transition metals. And also the interconversion between the oxidation state. For example, if you take magnesium in the periodic table, it's one of the elements which the oxidation state of this manganese varies from -2 to +7. So 0, +2, +3. So there is always a variable oxidation state. So if you want to use it in a catalytic reaction, there should be a discrete electron transfer or this oxidation addition or reductive elimination, which are very common in chemical reactions that would happen, right? And how one can tackle this problem? So you must come up with a suitably designed catalytic system. This is what we have been doing, and here we have designed a catalyst based on manganese. There is a purpose for designing such kind of a rigid backbone. I don't want to go into detail, but what it does it, and typically in organometallic chemistry, basically I'm from organometallic background, the metal center is the only active center. So whatever the reaction you perform, the reaction happen only at the metal center, right? But if I look at the biological system, for example, several metalloenzymes, not only the metal center, the ligand, the secondary interaction plays very, very important role. But making such kind of synthetic molecule is always challenging one. But last few decades, people have contributed a lot in this particular field, and we are one of them from India, where we have chosen a kind of metal complex. You see there is a manganese, and this is a d-aromatic in nature. And upon reacting with alcohol, and this alcohol OH bond activation took place, and you see carefully that hydrogen has gone to a ligand site, and then this alkoxide has gone to a metal center. So means that metal center is not the only active center. Ligand also plays very important role. Such kind of complexes are known as metal ligand cooperation process or cooperative complexes. So this helps us to maintain the oxidation state of the metals throughout the reactant same. This is very important whenever you are working with the 3D transition elements, right? And upon heating, you get back your complex with the formation of hydrogen and then value added product. And the same complex, upon reacting with the hydrogen, and you get a ring hydrogenated product, you get this compound. I look at it very carefully, and these two are, when you react with alcohol, it behaves like a Maelstrom catalyst. It's an Israeli scientist, where this aromatic to de-aromatic, that's the driving force. And if I look at it in the hydrogenation chemistry, this behaves like a Noyori type of catalytic system who received the Nobel Prize in 2001 for asymmetric hydrogenation of prokaryotic compound. So in a single system, you can have two different metal catalytic system. This helps us to do a dehydrogenation chemistry using alcohol, as well as the hydrogenation chemistry utilizing hydrogen, right, for various reactions. And initially we have used this metal catalyst for the conversion of carbon dioxide to methanol. So Sebastian already has a plan for converting carbon dioxide to methanol, which is an heterogeneous system at the technology level hired. And here what you have shown is a fundamental approach. One can convert the carbon dioxide into methanol using this particular catalytic system using amines. So amine is acting as a autocatalyst. How? So initially this carbon dioxide converted to amide, and then followed by hydrogenation, you get methanol. Now people talk about the circular economy or circular chemistry. So it means that whatever the waste you are generating, you should bring it back to the same system. That's what Professor Sadim also clearly mentioned. This is also one of the goals which chemists should address, right? And now what you have used is the same catalyst can use for dehydrogenation of methanol. So removal of hydrogen from this methanol. So you get hydrogen. That hydrogen will be utilized to convert this kind of various intermediates or compounds to several other products, right? Not only this chemistry is applicable for the transfer hydrogenation, you are transferring hydrogen from one molecule to another, and instead of deuterated methanol, if you use, the deuterium incorporation would happen. So deuterated drugs are very, very important, which has the strong metabolic stability. And you know, many pharmaceutical companies now they are moving towards deuterated drugs. So yeah, our simple chemistry help us to make such kind of molecule in a sustainable and affordable manner using methanol as a fundamental feedstock. And now I can explain to you how one can utilize this alcohol for making various chemicals. I don't want to go into detail, just I'll touch upon a few things. And you know, alcohol amination is very, very important reaction. So for example, if I want to do the alkylation, so typically people use alkyl halide, which is metogenic in nature and as well as it's a toxic. When you react with alkyl halide, you produce a copious amount of base, acid base, and also the product which is more nucleophilic than your primary amine. So there will be a multi-alkylation reaction. So there is a challenge whenever you work on this particular system. So, but simply you use alcohol. This alcohol first undergoes a dehydration dehydrogenation, there will be a removal of hydrogen, and then you get carbonyl compound, and there will be a condensation reaction, there is a water, and whatever the hydrogen is liberated, that will be utilized by the same metal complex in the same system, you get the N-alkylated product. So we have shown this reaction and using a nickel-based catalyst, so one of the non-precious metals, and not only the amines, even for example nitro compound. You know, nitro compounds are the fundamental chemical for making various pharmaceutically important compounds. So what you have shown here, simply using a deuterated methanol, so you can hydrogenate. So first this NO2 compound converted into amine and followed by an alkylation. So again, deuterated chemicals, so one of the pharmaceutically important compounds, is very important thing. In a affordable manner we did it. Okay, and also this strategy was extended for diazo compound, and diazo compounds are a dye industry based product, so one can have a value added to dyes also by using a non-precious metal, using alcohol as a hydrogen source as well as alcohol as a alkylating source. This chemistry is not only for C-N bond forming reaction. In organic chemistry, C-C bond forming reaction is one of the fundamental reactions. Also applicable for C-C bond forming reaction, particularly amides, and later this strategy can be applicable for a peptide modification. So what are the peptides out there, using our strategy one can modify, that will have a big impact in synthetic chemistry as well as the chemical biology. And also this is very interesting reaction. The reason is you are taking a two different alcohol which are abundant and feedstock chemical, one can integrate it, one can make varieties of extended alcohol, and later this can be dehydrated and hydrogenated, one can use it as a jet fuel or rocket fuel. And also ethanol to butanol. Butanol is considered as one of the biofuel, and we have applied our strategy for making this ethanol to N-butanol. And using our synthetic strategy, like non-precious metal is one way is using non-precious metal. Another thing is alcohol is a fundamental and feedstock chemical. We could make varieties of pharmaceutically important compound as well as several lifestyle molecules, right? So both CC and CN bomb strategies used to make these molecules. We have used a very low catalyst loading of non-precious metal, and second thing is alcohol as a starting material. And during the course of the reaction, water is the only byproduct. And we applied this strategy for direct amination thing, and these are kind of monomer mostly people use in the polyurethane industry. So the terminal OH was converted into amine, and that is considered as one of the monomers for polyurethane industry. Okay. We have also used a reusable nickel-based catalyst for converting alcohol into amine. And the C bond forming strategy also was applicable to make one of the donors molecule which plays very important role in Ziegler-Natta polymerization reaction. And Ziegler-Natta polymerization, you must have this particular donor which has a cell limiting or self extinguishing property. And with this indigenous company, and we developed a synthetic strategy for making such kind of molecule using again alcohol as a fundamental feedstock, and you could make a kind of varieties of proprietary type of molecules, and which really indeed reduces the imports cost from $390 to $98 per kg of this particular molecule. And not only applicable for making a pharmaceutically important compound as well as the petroleum industry relevant compounds like a polyurethane industry as well as and Ziegler-Natta polymerization, we can also make several heterocycles, and these are from the chemist perspective. One can have various interesting molecule which has these cores, several pharmaceutically important compound as well as biologically important compound which has these two cores, and one can make this molecule by abundantly available the starting material. So you are taking unsaturated system, you are taking a saturated system and you are making unsaturated system with the formation of hydrogen gas as well as the water. So in overall process, only these two are the co-byproducts. And these are some few representative example, and we can have a multi-substituted various type of compound. I don't want to go into detail, but we are I'm going to convey here is one can use alcohol as a sustainable feedstock for making various type of heterocycle compound from a simple aliphatic system with the formation of hydrogen gas and water as the only co-byproduct. And these are some recent contribution on making our strategy for various heterocycle synthesis. And these are what I have shown in the first part is how one can alcohol can be exploited or used for several interesting reaction which plays very important role in synthetic organic chemistry. And now in the second part I will touch upon the carbon dioxide, and already both the speakers gave a brief an overview about why the carbon dioxide utilization is very important. And there they talk about the hydrogenated route. So you must record the hydrogen. So in situ you make a hydrogen, and that used to convert the carbon dioxide into the value-added chemicals, particularly the fuels or shorter hydrocarbons and all. So what I'm going to show here is the non-hydrogenated route. So you don't record any hydrogen. That's called carbon dioxide sequestration, and then non-hydrogenated route can convert into variable or very interesting molecule. So we are very much interested on this polycarbonate diol. So you know these two compounds one can synthesize from a carbon dioxide via copolymerization reaction with various epoxide, particularly ethylene oxide or propylene oxide. One can have these two, and this is very well established process. But the process of making a polycarbonate diol, so in the world only there are 3 technologies. One is the November based catalyst and also the Evonik catalyst based on the bimetallic system with the William Coates catalyst, and also Saudi Aroma catalytic system. But making such kind of molecule is always very, very challenging things. So why this molecule is very important? So if we have this terminal OH, it has a different additive properties, and not only that, this particular process is one of the well-known process. One can incorporate up to 50 weight percentage of carbon dioxide. If you take other thing, it's not that easy, but 50 weight percentage of carbon dioxide theoretically one can incorporate in a single molecular system. That's the reason this process is very, very important, but it's also such a challenging process. And this once we have this terminal OH, and mostly in the polyurethane industry, you just take a polyol and that be reacted with polyurethane, you get the 2-3 minutes, and you can make a polyurethane. But here you are making a different type of monomer, you are incorporating the CO2. So the polymer which you derive out of this, which has a biodegradable property, this is one of the reasons we are more focused on this. And but there are always challenges. You need to work on the catalytic system as well as the several parameters, and also depending on the condition you do expect a different type of polymers also, both alternative as well as the copolymer, block copolymer. And also with respect to the catalyst, both steric as well as the electronic property to be tuned. The reason is we have a 2 system. One is electronic deficient system, that is CO2, another the epoxide is the electron rich system. So in a single catalyst you have to activate both the ends. One is electron rich, another is the electron deficient. It's always very challenging things, and we have used a zinc, mace and manganese, the bimetallic system, to perform such kind of reactions, and we could get a 43 weight percentage of carbon dioxide in the polycarbonate diol. And also the operational temperature or condition is very, very mild, and you see it's a simple copolymerization reaction. You add a carbon dioxide to epoxide without using any hydrogen, and we can make a kind of carbonate with a terminal OH, which plays very important role in the polymer industry for making a polyurethanes. And the final part, so far I discussed about the homogeneous system. In the heterogeneous system, making a homogeneous catalyst into heterogeneous is always the industry wants because of the reusability and other thing. So pyrolysis strategy is the one which use first the metal complex and get absorbed on the carbon support, and pyrolyze under elevated temperature, you get a kind of n-doped material. We use a nitrogen system, and this is very well exploited in electrochemistry as well as the photochemistry. But in the thermal catalysis is very less explored. And we are shown an ion-based catalytic system for a dehydrogenase chemistry for converting simple amines as well as alcohol to hydrogen. And also we have used this strategy for making a very interesting formation important compound. And we have also systematically studied the nature of support and the metal ligand ratio, and several things were studied systematically, and we found that this composition as well as the size distribution and this core shell microstructure is very important for the hydrogen liberation reaction. Okay, and this is very much highlighted by various media. And finally, I would like to thank first of all the chairperson and also the academy for giving this opportunity, and at least I hope I convince you people that whatever the chemistry or little chemistry we are doing is definitely will be helpful for the sustainable thing. Though the long way to go, since I'm a young scientist and we try to contribute for the sustainable development. And thank you for my motivated students as well as various funding agency, and thank you for your patience for listening to me talk, and I'll be happy to take up any questions.
Thank you, Professor Balraman, for a wonderful lecture. So we can take one question, actually, quick question. Yeah.
Cobalt bimetallic system for your ChemCom paper.
Yes, I mean
So-
SNS systems for
so-
CC bond forming reaction.
So what advantage you get using a bimetallic rather than a monometallic system?
Yeah, so this is a homogeneous system. So when you make this complex, so you got that's a sulfur system, SNS system, and this monomer is not that stable. So it crystallized out, or you got the bimetallic system. But the moment you use that catalyst for our reaction, and when the moment you put it in alcoholic solvent, there is a symmetrical cleavage, and then the solvent coordinates, you get a monomer. I mean monometallic system. That's the one is catalyzing the system.
So it goes through cobalt 1?
Yes.
Okay, thank you.
Yeah, thank you, Professor Balraman, once again for the wonderful lecture. So, is there anyone who wanted to ask a quick question? Whatever.
Yes.
Yeah, wonderful talk. I just want to make a quick query.
Yes.
Like for your transfer hydrogenation using methanol, what solvent you would like to use for those transformations, and are they green solvents, or you have some solution for that?
No, we didn't use any solvent. Methyl itself is considered as the solvent as well as a reagent.
Okay.
Yeah, so no
And
solvents.
Methanol can be reused for
You
further
see,
reactions.
you just take methanol as a solvent there, and then it liberates hydrogen, and that hydrogen get transferred. You don't really record any other solvents.
Right.
Yeah.
Thank you so much.
So methanol
Further
itself is
discussion can be
considered
done over lunch, actually. I have to stop
Maybe
here.
we'll discuss during lunch.
Yeah, thank you, Professor Balraman, for the wonderful lecture, and I thank all the speakers, actually, especially Professor Matthias Dries, who cut down his holiday time in Goa and agreed to give this lecture. Thank you very much for coming here, and thanks to all other speakers, and thanks Academy for giving me this opportunity to conduct this session, and I give it back to Academy now. Thank you.
Thank you very much for conducting this symposium. And now, of course, the announcement that you're all happy to hear is about lunch. So I'm going to turn it over to the local.
Okay, lunch venue is just behind. All of you can use this door or maybe the other door. Most of the volunteers are waiting here. They can guide you to the lunch venue. It's very nearby. Please come this way and then use this road, and this way, and go that side.
I can also say that since the lunch will be at this level, when you come back to the venue, you can then occupy places, not right at the top of the venue, but you can occupy places closer by. Yeah?
This way.
ఇక్కడ వస్తుంది. హలో యా హలో క్వైట్ ఉన్న వస్తుందేంటి? ఇక్కడ కూడా వస్తుంది యాక్చువల్లీ క్వైట్ ఉన్నా కూడా ఏం తీసుకుంటుంది అది.
సో నేను ఏం ట్రై చేస్తాను తెలుసా, ఐఎమ్ క్రియేటింగ్ సీన్స్. ఇప్పుడు మనకి ఒక సెటప్ ఉంది,
సీన్ మార్చేస్తే అయిపోతుంది.
సీన్ మార్చేస్తే మనకు కావాల్సిన సెటప్లోకి వచ్చేస్తుంది. జస్ట్ కదా ఒకడు పీపీటీ అని అంటాడు, అప్పుడు మళ్ళీ ఒక్కటి అడ్జస్ట్ చేసుకుంటున్నా, సీన్ చేంజ్ చేస్తే వచ్చేస్తుంది.
హలో 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 రావట్లేదా? అయితే ఏం నాయిస్ తీసుకుంటున్నారు అక్కడ? హలో 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 అవునా?
working. Sound is working fine. ఇక్కడ కొట్టినా రావట్లేదా? డైరెక్ట్గా అనిపిస్తుంది.
triple ITs, NITs coming together. And the gender ratio is pretty good, 50-50 in the higher education sector. Our gross enrollment ratio is pretty low, so but that's what NEP is targeting to take it to 50%. And if you are wondering how many PhD students are there in our academic institution, this is a slightly dated kind of a number, but growing at 10%, over 200,000 PhD students. Now at this rate, it would have crossed 250,000 now, and close to 300,000 PhD students are currently pursuing their PhD in our universities. So these are the statistics. And the current status, if you see, India ranks third in the world
Yeah, talking about B6.
Yeah.
Well, I had sent this crystal to Sydney, and the problem, we sent this one and it took a lot of time, you know that you have to send a proposal and all. And by that time my turn came and this crystal died and we could not get a proper data. But it was okay, it was titanium, was not a big metal, so somehow we could, yes, as you said, that there are too many hydrogens, but we don't have a neutron difference.
Any more questions, please? Okay, if there are no more questions, let us thank Professor Ghosh for a very nice talk. Some extent. Please.
It was on folder. I don't know. Have the pen drive on the pen drive? Just this IAS talk.
Okay, we have second speaker from Chennai in this session. He is Professor Vijay Kodiyalam from Institute of Mathematical Sciences, Chennai, and we switch from chemistry to computer science now. Vijay received his BTech computer science from IIT Madras, and then he switched to mathematics. He did his MSc and PhD from Purdue University. He is a winner of Birla Science Prize and a fellow of Indian Academy of Sciences and National Academy of Sciences. The title of his talk is Infinitely Many Quantum Solutions to Euler's 36 Officers Problem. I was told that this problem was posed about 243 years ago. He will tell us more about.
Thank you. Thank you for the introduction. And I'd like to thank the Academy for giving me an opportunity to speak here. So, yes, as you said, the problem is quite old in its original form. So this is the Euler's 36 Officers problem. I'll give an introduction. And my goal in this talk is to explain all the terms in the title. What is the problem? What is meant by a quantum solution to this problem? And what is meant by infinitely many? Now it might seem surprising that I'll have to explain what is meant by infinitely many, but when you have quantum solutions, we'd like to know when two of them are regarded as equivalent or essentially the same solution, and so we need techniques for that. And that's one of the main things that goes into the proof of various things. So all of this is joint work with Suhail Radhar, N. Ramadas and Arul Lakshminarayanan at IIT Madras, physicists at IIT Madras. And that picture down there this picture is what is called a picture invariant, and this is one of the main techniques that we use to solve the problem. I'll say something more about picture invariants as we go in. Okay, so let's begin with a little bit of origins of this problem, Euler's 36 officer problem. So the date, it's roughly the late 1700s, and that's Catherine the Great of Russia. Euler was at her court during this time, and folklore has it that she asked him the following question. Okay. So the question is the following. There are 6 different regiments, each having 6 officers of different ranks, and we'd like to arrange these 36 officers in a 6 by 6 square grid, such that every row and column contains 1 officer from each regiment and also 1 officer of each rank. So this is just a puzzle problem, right? So if you like puzzles, then you can try and think about how one would solve a problem of this kind. Now when you think about this, the first thing you might try is, why 36? Why don't we do with, say, 3 by 3 where you have 9, or 4 by 4 where you have 16? So you can try this problem for any square. There's nothing particular about 36, but on the other hand, we will see that there is something particular about 36 a little later. Okay, so here is a solution to the 5 by 5 case of the problem. So where are the officers and where are the ranks and regiments and all that? So we think of chess pieces as representing the ranks of the officers, and colors as representing the different regiments. So there's a black one, there's a red one, so all of these are different regiments, and the king or the queen or the rook, they all represent ranks of these officers. And you can see that in this arrangement, each one occurs 5 times. So the king here occurs in all 5 colors, this queen occurs in all 5, this rook occurs in all 5. Each of the 5 occur in all 5 colors, that's one property. Further, every row and every column has each of the colors represented and each of the chess pieces represented. So if you look at this first row over here, it has all 5 colors and all 5 chess pieces, and that holds for all the 5 rows and all the 5 columns. So this is the kind of arrangement we want, but not for 5 by 5. We want the answer for 6 by 6. We want such an arrangement for 6 by 6. At least that was the problem that Euler dealt with. So the terms that are used nowadays, they are called Latin squares and orthogonal Latin squares. So let me explain what a Latin square is. Each of these 2 pictures, so this square here and this square here is a Latin square. So what is a Latin square? In a Latin square of size n, you have n symbols, and these n symbols have to appear in each row and in each column exactly once. It's a very simple kind of thing, right? So in this one, all the chess pieces appear in each row and in each column. And it's very easy to make lots of different kind of Latin squares. That's very easy. The thing is, here you have one Latin square and here you have another Latin square, one of colors and one of chess pieces. Now the thing is, when you merge the 2, then you get the picture in the previous, what we saw on the previous slide. Sorry. So this picture is obtained by merging those 2 Latin squares. Of course, it will have every color once in each row and column, and every chess piece once in each row and column. But what is special about this is that each piece occurs 5 times in all 5 colors. Each chess piece occurs in all 5 colors. That's what is special. And that is when 2 Latin squares are said to be orthogonal. So these two Latin squares are orthogonal Latin squares. When you combine them in the way that I have described, you will have each one occurring as many times as that n. For in this case, n is 5. So Euler's question therefore is, does there exist a 6 by 6 pair of orthogonal Latin squares? That's the mathematical phrasing of that question. Okay. So let me begin with a brief history. So as I said, that is Euler's question, roughly 1780 in St. Petersburg. That's where it arose. And Euler himself answered it in some cases. So he showed that if n is odd, or if n is a multiple of 4, then there exists a pair of orthogonal n by n Latin squares. that is for odd n or for n divisible by 4. So that leaves out all the others which are even and not divisible by 4. That's the sequence 2, 6, 10, 14, 18, 22. For all of these, we don't know the answer. At least he didn't know the answer, and he conjectured that there do not exist any such pair of orthogonal Latin squares for these numbers, for n a multiple of 2 but not a multiple of 4. And it's very easy to see that when n is 2, you cannot find a pair of orthogonal Latin squares. You just scribble on a piece of paper and you'll see very easily that you can't find orthogonal Latin squares for 2. And the next case, n equal to 6, is the case that he was asked, and he had an intuition that it's not possible, but he couldn't prove it. He couldn't quite prove it. He just said that, as he conjectured, it's not possible for any of those. So this problem has an Indian connection. So I'll come to that. So in 1900, so that's a good 120 years after the problem was posed, a French amateur mathematician, he was a French civil servant, Gaston Tarry, he showed that Euler's conjecture is true for n equal to 6. That means you cannot find a pair of orthogonal Latin squares of size 6. And this involved quite horrendous computations running into thousands of cases, but he did it, and this is considered to be the first proper proof that it's not possible, that Euler's conjecture is true for n equal to 6. Then about 50 years later, Bose and Shrikande showed that Euler's conjecture is false for n equal to 22. So they constructed a 22 by 22 pair of orthogonal Latin squares. So they constructed for 22 by 22 a pair of orthogonal Latin squares. And a little later, a year later or something, so Bose, Shrikande and Parker, they showed that Euler's conjecture is true only for n equal to 2 and 6. That is, 2 and 6 are the only things for which you cannot construct a pair of orthogonal Latin square. For all other values of n, they always exist. So Euler's conjecture was quite spectacularly false, right? Except for the first 2 cases, all other cases it's false. Okay, so now we know that the conjecture is false. So for 6, we really cannot solve the original problem that Euler considered. So what do we mean by a quantum solution then? What is meant by a quantum solution to this problem? So yeah, so let's look at the passage from classical to quantum. Typically in physics, when we first encounter something like quantum mechanics, the thing that arises is discreteness out of continuity. So the energy of the electron is quantized. It takes only a certain discrete values. Here we are going quite in the opposite direction. What we are going to do mathematically is we begin with a finite set. So this is a set of D elements. So we want to replace this set by a Hilbert space or an inner product space of dimension D, or rather just a set of unit vectors in that space, but let's not get technical. So we want to replace this set by a vector space with a basis of D elements, and on the set of symmetries of this set forms the symmetric group sigma D, and this naturally will get replaced by the symmetries of an inner product space of dimension D, which is the unitary group of D by D matrices which are unitary. And distinct here will correspond to orthogonal there. That is, 2 vectors which are orthogonal that's the analogy for distinct elements of this set. And an example of this is when D is 2. So you have a bit takes 2 values, 0 or 1, and in quantum computation a qubit is a unit vector in a 2-dimensional complex space. That is, the topology of that is the topology of the sphere S3, but never mind. So all of these this is a rough dictionary between classical to quantum. So here is a Latin square. This is a Latin square of size 4. This is a Latin square of size 4. All the numbers 0, 1, 2, 3 occur in each row and column. So what would we mean by a quantum Latin square, QLS? So that is that QLS in the title over there. What is meant by a quantum Latin square? A quantum Latin square is a square, and every element of that square is a vector. It's a unit vector, and the rows should be orthogonal and the columns should also be orthogonal. So there's a very easy way of constructing from a classical Latin square a quantum Latin square by just taking, for 3 you take the third basis element, for 1 you take the first basis element, and this will give you quantum Latin square. But there are many more quantum Latin square than this construction can supply. Not all quantum Latin square are classical, right? So there are many more such objects. So now we get to what would we mean by a quantum orthogonal Latin square. That's what we want, a pair of Latin squares which are orthogonal. What does this correspond to? In order to explain what this corresponds to, I want to discuss two operations on matrices. So let us say a 9 by 9 matrix. We actually have to deal with 36 by 36 matrices, but for illustration I will just deal with a 9 by 9. Take a 9 by 9 matrix and divide it into blocks of size 3 by 3 each. And I want to describe two operations. One of them is very simple operation, it is called partial transpose. So this operation is the so-called partial transpose operation. You take each one of these blocks and transpose the block, right? You take the transpose, that is you reflect about this diagonal. So in each of these blocks you reflect about the diagonal, you will get another new matrix, and that is the partial transpose matrix. That is one. Then there is another operation called realignment sometimes. In realignment, what you do is you take each block of this matrix and write it down column wise. So 1, 4, 7, 2, 5, 8, 3, 6, 9. You make that the first column of your new matrix. Then you take the second one, the block below it, then you write its 9 elements in the second column, and so on. So these are two operations on matrices. This might seem, why would one want to do such operations? But it turns out that this forms the building blocks to whatever you can do to a unitary matrix of size d squared. These two operations. So a matrix is said to be a quantum orthogonal Latin square if this matrix originally should be unitary. After performing this realignment, it should be unitary, and after performing this partial transpose, it should be unitary. So it should satisfy unitarity in so many different ways, right? Such a matrix is called a QOLS, quantum orthogonal Latin square, or a 2 unitary matrix. Sometimes it's called a 2 unitary matrix. I don't really like the terminology, but that's the way it is in the literature, because these two operations, under these two operations it's unitary, besides being unitary on its own to begin with. Okay, so an example of a 2 unitary matrix of size 9 is given here, right? And the reason I have given this example here is that this is a unitary matrix, but it's much more than a unitary matrix. It's a permutation matrix. It has only zeros and ones as entries. All these blank entries are 0, and then you have these ones in these places. And this, you can do the realignment or the partial transpose. You will still get permutation matrices, and they are also unitary. So this is a 2 unitary matrix, and the reason is, the reason that these permutation 2 unitaries are important is they correspond with orthogonal Latin squares of size 3, right? It's a 9 by 9 matrix, but it corresponds to pair of orthogonal Latin squares of size 3. So if you want a quantum solution to Euler's problem, what we are looking for is a quantum orthogonal Latin square of size 36. So we want a 36 by 36 matrix, which should be a unitary matrix, such that when you realign it should be unitary, such that when you do partial transpose it should be unitary. So this was an open problem in this quantum computation community for a while, and until it was solved. And this solution received quite a bit of attention even in the popular things like Quanta magazine and things like that. So this is 36 entangled officers of Euler, quantum solution to a classically impossible problem. So these two of my co-authors, Suhail Radar, Arul Lakshminarayanan, and 4 Polish physicists, so gave this solution whose names I think I'll not pronounce. It might be difficult for me to do that. So they solved this problem, and by explicitly constructing a 36 by 36 QOLS, quantum orthogonal Latin square. So let me just show you how that looks. So look at that matrix over there. All the blank entries are 0, right? You can see it's a very sparse matrix. There are 1296 squares over there, and most of them are blank. 112 of them have entries. And of the 112, some are blue, some are red, some are green. And what do this blue, red and green represent? Red represents a complex number with modulus this value. Green represents a complex number with this modulus, and blue represents a complex number with modulus 1 over square root 2. And this is not, this doesn't give you complete information about the matrix. Since I've only given you the moduli of the complex numbers, there is still phase factors. So there are phase factors which have to be very carefully fudged in order to make this into a QoLS. But this is what they succeeded in doing. Okay. So now let me get to asking whether that's the only solution or whether there are more solutions. So we would want to know, if you're given two quantum orthogonal Latin squares, what distinguishes them, or when would you say they are different? Of course, you can say they are different if they are not equal as matrices, you can say they are different, but that's not a very good definition. So for example, let me just go back a couple of slides. So look at this Latin square. If I interchange two rows, or if I interchange two columns, or do any permutation of the rows or any permutation of the columns, it still remains a Latin square, right? Those are all kind of trivial modifications. So permutations here correspond to trivial modifications, and remember, according to this dictionary, this permutation group corresponds to the unitary group in the quantum situation. So somehow whatever notion of equivalence you are giving should involve the unitary group, and indeed that's what the definition is of equivalence. So we say that two matrices A and B of size d squared are equivalent. That means we want to think of it as representing the same solution if you can find unitary matrices x, u, y, v satisfying this equation, and this equation can be pictorially represented by this picture. I'll explain what this picture is a little later. Let me just see how I'm doing on time. Okay, I'm almost done. Okay, so we want to be able to distinguish these solutions in some way. In particular, we want to say when two solutions are different. Okay, I'll state the main theorems. So the main theorems that we have shown are the following. First, that if you take 9 by 9 two unitaries, I gave you one example of a 9 by 9 two unitary. There is only one LU equivalence class of such two unitaries. That means there's, for 3 by 3 quantum orthogonal Latin squares, there is only one, and that's the one that I showed you. Whereas this theorem 2 that says that as long as d is bigger than 3, for example for d equal to 6, which is the case we are interested in, there are infinitely many different solutions of size d squared, and that means there are infinitely many quantum solutions to Euler's 36 officer problem. This is what we showed. So, and how did we do this? There's very little time, so I'll try to not explain this pictorial representation. I just want to say something about this one though. This is the Ouroboros. It occurs often in many cultures. It occurs in art, and today, in many talks of today, benzene structure has occurred. As everybody knows, Kekulé discovered the benzene structure after having a dream of a snake swallowing its own tail. As it happens, this Ouroboros is also important for us mathematically, because it represents one of the most important invariants. So if you take a linear operator, these pictures all represent various kinds of numbers, and a linear operator where it swallows its own tail represents the trace of that operator. It's a very important invariant of that operator. Okay, so more generally, this theorem was proved with my colleague Sundar in 2004, almost 20 years back. So what we did was we tried to give conditions under which two operators, or two sets of operators more generally, are unitarily equivalent. And this is an if and only if condition for unitary equivalence. The first part of the theorem is very trivial. It's the second line which is the important line. These conditions are complete for equivalence. So we'll tell you, given two operators from a tensor product of vector spaces to a tensor product of some other vector spaces, when are these two equivalent? And these two are equivalent exactly when many of these pictures that you can build from these operators turn to give you the same number. For example, one such picture is what was illustrated at the beginning of the talk. So this is a picture that can be built out of these two operators S and T. You are allowed to use S, T, and also the adjoint of S. If S goes from R to B tensor G, All of these are vector spaces. I've just represented them by colors. Then the adjoint operator S star will go the other way. It will go from B tensor G to R. All of these have pictorial representations, and closed pictures that you can form from these evaluate to numbers. If all of these numbers are equal, then the operators are linearly equivalent, are unitarily equivalent, otherwise not. Okay, so I wanted to say a word about the proof, but I don't think there's enough time for that. I'll stop here. Thank you.
Yeah, thank you very much for a nice talk and sticking to your time. We have sufficient time for discussion.
So it was a lovely talk, but there was some step in between which I think I missed. If I can just ask you,
Sure.
You discussed classical, what you called orthogonal Latin squares,
Yeah.
and then you squared the size of the square
Yes.
and
Yes.
defined the quantum.
Yes.
But I didn't see the connect. In the
Yeah, the
quantum
connection
case,
is-
there was some two operations that are supposed to.
Yeah, why
preserve
squaring?
integrity.
So the reason for
Yeah.
squaring is if you take a QoLS of size 9, which I illustrated, and so each one of those square blocks had an entry. Only one entry was 1, all the other entries were 0. So for example, in the first block, the 1, 1 entry was 1, in the second block, the 2, 2 entry was 1. So if you write down this 1, 1, 2, 2, 3, 3 for this entire thing, you'll get a 3 by 3 matrix, and that's actually a pair of 3 by 3 orthogonal Latin squares.
You get one 3 by 3 matrix or
Yes.
a pair of, then how,
Because you'll write down both the row and the column numbers. So the row numbers will give you 1, the column numbers will give you 1. And together they'll form a pair of orthogonal Latin squares. So that is why the squaring occurs.
And the use of the word quantum, I thought you were going to take linear combinations of since you introduced Hilbert space, I thought you
Well,
planned
in
to
a sense,
take-
yes, we are
So
taking linear
that is
combinations
what you
because
did.
all of those things involve very complicated kind of
Operations on the
Yeah.
vectors, I see.
They
Now
are
I begin
they are
to
not
understand.
simple basis vectors. They are complicated linear combinations of the basis vectors.
I see. Thanks.
May I ask?
Yeah.
Does your description hold for decimal numbers only, or can be
hold for sorry?
Extended to bits and applied to cryptography?
I don't know what kind of application. There is something called quantum cryptography. I don't know much about it. So I don't understand the question. Sorry.
No, the first part, at least the first part.
The first part is meaning?
The number system is just 0 and 1.
No, the number system doesn't really matter. It's just a finite set. You could do it for any finite set. 0 and 1 is just a choice. You could do it with 3, for example.
Okay. Then one can think of cryptography,
That's-
data and encryption.
It's possible, but I don't know that.
Okay.
No, I can hear you, but I think. Thank you.
I find the analogy to be something like I hear a beautiful Rama Sita story, but then at the end I want to ask you what is the relationship between Rama and Sita? Please don't laugh at my question.
No.
As I understand, Euler conjecture there is no solution.
Yes.
And you call it a classical solution.
Yes.
And what I understood from the wonderful presentation by you, very crisp, very nice mathematics, there is a quantum solution, infinite number of quantum solutions for this problem.
Yes.
Now, even though I'm familiar with some differential equations, classical solution and non-classical solution and all that, what exactly is the difference between a classical solution to the Euler conjecture problem and the infinitely many non-classical quantum solutions to the problem.
Yes.
What I want to know is there a measure of this discrimination between a classical solution, yes, there is some number, and there's a quantum solution, there is another number, and the difference is infinite, or something like that. What is, how do I hold your solution in my hand?
Yeah, there is a very precisely defined notion of what a classical solution is and of what a quantum solution is. So we are getting, so in a way we are getting around Euler's problem by redefining what we mean by solution. So what was originally meant by a solution was a classical solution, which essentially means a permutation matrix of a certain size satisfying certain properties. But now we have said we are not looking for permutation matrices. Let us generalize the class of matrices to unitary matrices which satisfy certain natural properties, and there we can find solutions.
That means you are departing from the starting point of Euler's statement. Is that the case, or what exactly is that?
In a sense, yes, because we know Euler's original problem has no solution. We know that. So
that means it is as though you reformulate a problem and come out with infinite solutions. Is that the case?
Yes. But it's a very natural reform. I mean, one can do it, it has to be done tastefully.
It's remarkable. I admire your presentation.
Thank you.
The thing is, in Sudoku, there are some sort of similar problems associated.
Yes, there is a quantum Sudoku also.
Oh.
There is a quantum Sudoku.
My hearing is bad, that's why I couldn't get to know. But whatever you have presented is absolutely beautiful. I admire your presentation. The thing is, I wanted to see where do I hold this. That means it is as though I don't have a solution to old problem. I will give you a modified problem for which I have infinite solutions.
That's
is
true.
That the case?
That is correct.
Thank you very much. I am grateful to you.
May I ask a question? Thank you for a really lucid presentation. I just had one continuation to the question that the professor asked there, that the classical solution would actually be a special case of the quantum solution, right?
Sorry, what?
Would you get the classical solution as a special case of the quantum solution that you got here?
Will we get what?
The classical solution to the Euler problem.
Yes.
Wouldn't that be a special case?
That would be a special case, but the classical solution doesn't exist in the 6. There is no classical solution.
Even though there are infinitely many quantum solutions, none of them in the limit
None of them,
gives
it's
you
not a classical solution. No classical solution exists. The point of this whole thing is, the quantum solution exists. That was the really nice discovery by those physicists in early 2022. But now what we can see is, it's not just one quantum, not an isolated thing. Despite the fact that they had a lot of difficulty finding exactly, you have to match parameters very carefully in order to be a quantum. Despite that, you can still find an infinity of quantum solutions.
At the
That's
risk
the
of
point
asking
of
a slightly unfair question, this quantum solution is linear algebra or is it numerical, or very roughly what was the method that helped you to converge onto this solution?
You can say it's basic linear algebra. It's basic.
Thank you so much.
Very quick question.
Yeah.
Quantum terms,
yes.
Will there be an infinite number of quantum solutions always?
In fact, one of the, that's a good question. Thank you for asking that. In fact, for one of the cases, we started with a classical solution and then modified it by changing phases to produce an infinity of quantum solutions. That's not always possible, but in one of the cases, it is possible, and that is how we did that.
Quick question here at the back. Very nice talk. So actually I have two questions. One is more of a quick clarification.
Okay.
So the popular Sudoku puzzles are technically a Latin square, right?
Yes.
Right?
They are. They are more than a Latin square, because there are conditions even on the 9 by 9s, small ones. It's more than a Latin square.
Okay, all right. And the second question is sort of a lazy one, because I should probably go read that PRL paper, but anyway I'll ask you. So it sort of follows from the question that came earlier.
Okay.
So for the particular solution that Arul and co-workers had constructed last year, so was there an algorithm that they devised to search for this solution?
Yeah. See how they got it. They did a lot of computer work.
Okay.
And then they slowly converged on something which seemed to be a solution. Then they did it exactly, and rather very nicely the golden ratio is involved in their solution.
It's an exact, for their solution is an exact solution. It's not a numerical one, it's an exact solution, and the golden ratio is involved in this construction.
Okay, so when they were searching, so there's
I
no
think,
a priori.
if I may,
Okay, all right.
you can
I'll talk to you
continue
later.
that
Yeah,
over
thanks,
tea.
thanks.
Thank you so much.
Yeah. Yeah, let us thank Vijay for a very nice talk, and we can continue the discussions over tea and coffee because it had generated a lot of interest. So thank you very much.
And thank you, Professor Gadre, for chairing this, and that was a delightful session. Tea and coffee are outside on this level, right? So everybody just migrate in this, and please come back by 4:30 because we've already eaten up time. Oh, I'm told it's on both sides, on the right or on the left. So if you're a right-handed person, you go that way or this way, doesn't matter. Please get your welcome back after tea. Hope you had a chance to get tea and coffee. We now start the next session of talks by fellows and associates. And to take you through this session, I invite Meena Mahajan to chair. Just before we do start, I want to make one announcement. Dinner tonight will not be in the location where we had our lunch. It will be in the lawns outside the guest house, and I'm told that there will be transport available just outside. There will be cars and buses that will take you to the guest house. So just in case you were worried or concerned about where the dinner was. And I'm also told to inform you that dinner tomorrow will be on the boat itself. So after the public lecture, we will be getting onto a boat and we will have dinner on the boat. So sorry, Meena, I had to make these announcements. It's all yours.
Thank you. Welcome all to this session. In this session, we have two talks by recently elected associates of the Academy. The first talk is by Dr. Momanty Poddar. Momanty is a faculty member at ISER, the Indian Institute for Science Education and Research at Pune. And she's going to talk about combinatorial games on random premises. If you see in the booklet of abstracts, there's a much longer title, which has now presumably been absorbed into the talk.
Thank you so much, Mia. And thank you everyone for coming, and thanks Indian Academy of Sciences for giving me this opportunity. It's an honor to be here. So I'm going to talk about what I do my current research on primarily, and then towards the end I'll talk a little bit about the other topics that I work on. And the primary topic that I work on that I'm very interested in exploring, and there are really a plethora of questions to try to answer in this area, are combinatorial games. And I, being a probabilist, I study them on random graphs, okay, so random structures in general. So I did my PhD, I'm not that old, so I did my PhD in 2017, completed my PhD in 2017, so I thought I would just start with the premise there that my doctoral thesis, this focused on studying graph properties that can be expressed in terms of first order logic or existential monadic second order logic on random graphs. So look at these properties that can be expressed as sentences in this particular logic. And then I study the probabilities of these sentences holding true on certain classes of random graphs. So looking at Erdős-Ronai random graphs, looking at Galton-Watson trees. So I'll come to some of these random graph models in a bit. So since then, random graphs have formed a fundamental object of interest for my research in general. And random graphs, I think nowadays pop up in everything. So they are the go-to models when you want to model networks of any kind. So it could be social network, could be electrical networks, could be biological networks. So, and as I was saying, so the most fundamental, I guess, the most primitive model of random graphs were the Erdős-Ronai random graphs proposed by Paul Erdős and Alfred Ronai in their 1960 seminal paper. And they're still very useful, but of course we have branched out. We now have other kinds of random graph models, like the geometric random graph models. We have random graphs that are used for modeling community structures, like in clustered networks. So for example, we try to have these, so we use regular stochastic block model or stochastic block models in general for trying to model clustered networks where there are communities present. Okay. So random graphs kind of show up everywhere, and there are various ways of studying them, various angles from which we can approach them. I do try some of these angles. One of the favorite ones is working on two-player combinatorial games on random graphs. So I'm sorry that I'm not able to control the pointer very well, so it's kind of going haywire. And these games, so because I'm very interested in combinatorics, so they are interesting by themselves, trying to understand both strategies as well as probabilities, because we are playing these games on random graphs, so there is always probability involved in all the questions I address. But these games are also useful because they do have certain very fascinating connections with topics in both physics and theoretical computer sciences. So in physics, for example, percolation and statistical mechanics in particular, that I have seen. There are probably many more connections that I don't know of, and I'm trying to learn. And then in theoretical computer sciences, something that I come across again and again in my research is automata theory. And in particular, I have encountered now probabilistic cellular automata and probabilistic Cree-automata. So cellular usually refers to the automata being defined on some lattice structure and infinite lattice graphs, and Tree-automata on trees. So a two-player combinatorial game, so what is it? It's a perfect information game. So what does that mean? For me, what it means is that since I'm playing this on a random graph, what do I do first? I take the random graph model, I simulate a realization of the random graph from this particular model, and this realization is now a deterministic graph. It came from a random graph model, but now it's a realization, so it's a deterministic graph. It is revealed in its entirety to both the players, and the players can. I usually assume, but although it doesn't sound very practical, but it does simplify a lot of mathematical work for us. I assume that the players have infinite foresight. They kind of can really foresee all the strategies that can be used against each other. The questions, as I was saying, that I'm usually interested in are basically trying to understand the probabilities of the various possible outcomes of these games. So what are the three possible outcomes usually? Usually there are three outcomes. First player winning, first player meaning the player who plays the first round, makes the first move in the game. First player losing, and in some cases there is also the possibility of draw. Draw meaning the game will continue indefinitely forever and neither player would be able to achieve a desired outcome. And I try to understand the probabilities of these various outcomes depending on the random graph model that I am working on. Sometimes I'm interested in trying to figure out winning strategy, at least one winning strategy for one particular player. And this is of particular interest when the players' roles in the game are asymmetric. So there are some games, I can throw some of the names in here, even though I'm not going into the details. So some games such as normal game, Misere games, the game that I will talk about primarily here, percolation games. In these games, the players' roles are symmetric. But then there are some games, such as make-or-breaker positional games. These are a very popular class of games in which the players' roles are asymmetric. So there are many applications of combinatorial games, but since I started with mathematical logic in the very first slide, I just want to mention one of the first applications that I encountered, thanks to my doctoral advisor, Professor Joel Spencer, introducing me to this class of games. So there are something called the Ehrenfeucht-Frasse games. Often we shorten the name and just say Ehrenfeucht games. These are used to check if two given structures or two given graphs are elementarily equivalent. What does that mean? That means that if you take, there is a notion of quantifier depth, which is involved with first order logic. So let's say that you have a given quantifier depth, it's a positive integer, some k, okay, so it could be 10, for example. And you look at all possible first order sentences, these would be some graph properties, some local graph properties actually, of quantifier depth, let's say 10. And now you are asking, so you have been given two graphs by somebody. When you ask whether these are elementarily equivalent in terms of these sentences, what you're basically asking is, if you take any such sentence, let's say A, does it hold for both the graphs or does it fail to hold for both the graphs? If it's something like that, then you say that these two graphs are elementarily equivalent. And one of the ways of checking whether two graphs are elementarily equivalent is by playing these Ehrenfreund-Frasse games on these graphs. Okay? There are 2 players involved, spoiler and duplicator, and if the duplicator wins the game, again not going into the details of this, then you say that these 2 graphs are elementally equivalent. The similar questions can be answered in other, not just first order logic, but any other class of logic, any other class of logical sentences. So today I kind of want to dwell on percolation games since, you know, these caught my fancy since 2021, and I have been trying to delve deeper into this. And it's just absolutely fascinating because they tie in so closely with the notion of percolation in physics. And so what's the notion of percolation in physics? I guess a lot of people here already know, but I'll just say it for the sake of completeness anyway. You have usually an infinite graph, but it probably doesn't need to be infinite. And in this graph, certain edge, so every edge is open with a certain probability and closed with a certain probability. And you have the notion of a source and the notion of a sink. And you're basically thinking of a fluid that is starting from the source and flowing towards the sink, but it's not able to flow through any of the edges that are closed. So is there a path for the fluid to go from the source to the sink? This path has to consist of only open edges. Can you find such a path? This is the primary question of percolation. And in case of percolation games, see, I was talking about flow of fluid here, and the fluid is the fluid and this random graph that we generated by, you know, assigning open or closed labels to the edges. There is no notion of adversary involved. But what happens if you do bring in the notion of adversaries? If there are 2 intelligent agents trying to do this thing where they're trying to find a path from the source to the sink, what happens in that case? So this adversarial nature is what makes the games really interesting and really different from just the processes. So in a percolation game, you have some directed graph G. I usually consider infinite lattices or infinite rooted trees. And every edge of the graph is assigned a label independently, which is either a trap. So, I'm sorry. As I said, I'm like not good with the handling of the, yeah, okay. So I'm not sure what happened there. Sorry. Can I? Okay, thank you. So every edge is labeled a trap with some probability P. So P is of course between 0 and 1. It's labeled a target with probability Q, again between 0 and 1, or it's labeled safe or open. Is there a problem? Okay. So it's or it's labeled safe or open with the remaining probability 1 minus P minus Q, which tells you that P plus Q is less than or equal to 1. And the game is as follows. So it involves 2 players. As I said, these are 2-player combinatorial games. And there's a single token. And the whole point is basically moving the token. And directed graph means that you will move the token along the directed edges. Now the token will start from some initial vertex, which we refer to as the origin. And these 2 players will take turns to move the token. So if the token is at some vertex U of the graph G, now whichever player's turn it is to make a move can move the token from U to a vertex, any of the vertices V in G, such that the directed edge UV is in G, okay? So there is an edge that leads from U towards V. And this from U towards V, this notion comes from the directed nature of the graph. How do you decide the outcome of such a game? A player loses if, I should have written a player wins, I'm sorry about that. Player wins if she's able to move the token along an edge which has been labeled target, or she's able to force her opponent to move the token along an edge which has been labeled a trap. This is the basic understanding. I'm really sorry about like missing that. A player wins, that's what I meant. And I studied this on 2 different settings. The first one is this class of random graphs that are basically rooted random trees called rooted Galton-Watson trees. So what are these things? Just to give you a very one-line introduction to this. this model was proposed by Francis Galton and Henry Watson, I think 1875, I don't remember the exact year. But the whole idea was they were trying to model the dwindling of aristocratic family lines in the UK, or back then I guess it was not the UK, but Great Britain. And they proposed this very simple model of a tree where you have a root, which is the original vertex, and then it gives birth to a random number of children. This random number follows a distribution that is referred to as the offspring distribution. And then these children, each of them independently gives birth to a random number of children according to the same offspring distribution, and so on. This continues. And their question was always to try to answer when there is a positive probability of the tree surviving forever, and when it is almost surely going to die out and be a finite tree. So I played this game, this percolation game, on such rooted Galton-Watson trees. And I guess, as I said, the whole point is to try to find probabilities of various possible outcomes of the game. And what we end up finding is that, so if I let W denote, so W, P, comma, Q, because it has a dependence on these parameters P and Q with which you mark the edges, trap, or target. So if I let W be the probability of the first player winning, then a certain nice centered and scaled version of W equals the minimum positive fixed point of a certain function. This function I haven't dwelt on because the technical part doesn't matter. This function depends on PQ and something called the probability generating function of the offspring distribution. And usually you don't get explicit expressions for these probabilities, you do get them as certain fixed points of certain functions. And then you analyze those functions to glean as much information as possible about these probabilities. The interesting thing, so you also get some similar results about the loss probability for the first player. But the interesting thing is this, the last thing. We show that the probability of draw in this game, on this percolation game on rooted Galton-Watson trees, is 0 if and only if this same function that we saw here, it's written in this weird manner because it's the composition of the same function with itself, GPQ with itself. So that's why I wrote a 2 as a superscript. This function, if and only if it has a unique fixed point. So if and only if it has a unique fixed point, the probability of draw in this game will be 0. So by analyzing the function, you get to know if the probability of draw is 0 or not, if you can analyze the function, if it's simple enough to analyze. And why are we interested in the probability of draw? Because you see that there is any possibility of draw only if you can find, let's say the token is initially placed at the root of the tree, only if you can find an infinite path from the root, starting from the root, which comprises entirely of open or safe edges. Okay, and this ties in with percolation. Immediately you know that for draw to happen, an infinite percolation cluster has to exist. So, and I just wanted to mention that for when you take the offspring distributions to be some specific distributions like binomial, these are very popularly studied distributions in probability, in discrete probability. So binomial, Poisson, negative binomial. You actually can find very neat expressions for the regimes depending on P, Q, and the parameters underlying these distributions where the probability of draw is 0. Okay, so for example, when it's binomial d comma pi, whatever that means, so there are a bunch of parameters involved in these distributions as well. It's a very neat condition. So this inequality has to hold, and if it does, then the probability of draw is 0. So you can actually check it in 2 seconds. Okay. When it's Poisson lambda, again there's this parameter involved. Then this inequality has to hold, and if it does, then the probability of draw is 0. So this kind of stuff is what we call, at least we refer to as phase transition phenomena. So when I was listening to Professor Umesh Wagvare's talk in the morning, he was talking about this germanium antimony tellurium and how it undergoes this amorphous to crystalline phase. I think that would be referred to as a phase transition phenomenon. Okay, and phase transition phenomena are so of interest to probabilists and people who study statistical mechanics. So So, and I'm interested in these two and this kind of, so once this inequality is no longer true, then there is a phase transition that happens and the probability of draw goes from 0 to positive. That's what we refer to as phase transition. Okay, there is a transition of the phase. Okay, and a similar question we tried to answer, but couldn't answer in its entirety, partial results on the two-dimensional square lattice. So here, you can move the token from where it is currently located, let's say xy, where x and y are integers, to one of its neighbors, either x plus 1 comma y or x comma y plus 1. And in this case, we show that whenever the probability of trap and target, P and Q, they satisfy these inequalities, the probability of draw in the game is 0. Okay, but simulation tends to show that this should be true whenever P plus Q is strictly positive. How am I doing on time? So 2 minutes left? Okay. So I just want to mention that this kind of questions, the instance of draw, whenever we are focusing on the instance of draw in this kind of games, it ties in very closely with something called ergodicity of probabilistic cellular automata or probabilistic tree automata, whichever structure you are studying the game on, whether it's lattices or trees, that's what it depends on. And ergodicity is always of interest to us because it helps with numerical computations a lot. If something is ergodic, especially for probabilistic cellular automata, you get a Markov chain, and as long as that's ergodic, it helps with numerical computation. So we are interested in questions of ergodicity. It also relates very closely with spatial mixing properties in models of statistical mechanics. Since I don't have a lot of time, I don't want to go into too much detail about this slide. In this slide, I was just going to talk about another kind of percolation games where you mark the vertices of the graph, either trap or target or open, okay, not the edges. And here we actually do have a complete result. We are able to show that the percolation game that we were considering, and this is a very recently accepted paper and a very favorite one of mine. The probability of draw is 0 whenever P plus Q is strictly positive. Okay, so that's a very stunning result in the sense of like how fast this phase transition happens. I just wanted to mention that, why are we interested in probabilistic cellular automata or probabilistic tree automata? Because they have countless applications. When I was writing this paper, I was looking into what kind of applications these have. And since this is a very mixed audience, they have so many applications in modeling systems in physics, chemistry, biology. They have applications in dynamical systems and computational cell biology. They have applications in combinatorics, in statistical mechanics. I even found this paper that talks about modeling astrobiological history of the Milky Way using cellular automata, which is, to me, it's like amazing. So we are interested in knowing more about these objects, and okay, I'm going to end here, that ergodicity is a question that comes up very much in my research and is of primary interest to me. And I wanted to talk about that. And thank you again for giving me the opportunity.
Thank you for this talk. We do have some time for questions. Are there any questions right now?
Just take a minute. Thank you very much. Is it on? Yes.
Hello, am I the first questioner? I have actually 3 basic questions.
Maybe I'll come closer because I cannot hear you.
The first one is,
yes.
Do you consider your random graph approach to certain problems as anything to do with the game of chess in which the 2 fellows choose random sort of patterns, as it were, in their choice of moves?
But
that
they
is
will
one.
still be choosing
I'll spell out the question so that you can answer.
Oh yeah, sure.
The second one is, do you consider the chess game as a non-zero-sum game or zero-sum game?
Okay.
Third one is, what is the order of complexity involved in trying to come out with the random graph approach to a chess situation, let's say end game situation?
Okay, so first of all, when we think of chess as such, it's not a combinatorial game. So I only focus on combinatorial games where the players are basically like gods. They can see everything. But in chess, I mean, the practical applications of chess, I guess that's not true. So I'm not sure about this the zero-sum approach, and I don't actually know like whether chess is played with this kind of random moves, like because correct. But yeah, I have actually no idea whether like how that connects with this, because this is, and chess is also, like I said, it's not a perfect information game. Yeah, so you would not be able to really read your opponent's mind, and you probably won't be able to see how the game can unfold, like several moves from now. Even a computer cannot. So that behaves very differently from this game. Yeah, in general, that would be the, and I actually don't know about the complexity answer, like no, yeah, no idea at all. Yeah, thank you.
Any other questions? So I have one question. You talked about the probability for draw being zero in certain circumstances, and then one of the two players has a winning strategy. But do we get any information about how easy or hard it is to find these strategies, some
Correct.
representation of the strategies?
Yes, some sort of algorithmic question, right? So I don't really deal with that, but I don't think it's that easy always. Like usually the questions that are answered, now that could be because only people are interested in only that part of the existence of a strategy, you know, whether that is true or not. For example, the question about understanding logic on random graphs, again, it's always about whether there exists a strategy for the duplicator. But I don't think finding such a strategy would be easy. At least when I was proving the existence, I was already kind of like, wow, there's so many different cases to consider and this and that. So I don't think that it would be that easy, but yeah, again, complexity questions, I don't know, sorry.
Okay, yeah.
Thank you.
Okay, so if there are no more questions, let's thank Momanty once again.
Thank you.
Our second speaker in this session is Dr. Uttam Gorai. So Dr. Uttam Gorai, he is
that is produced normally Haber-Bosch process.
చెక్ హెడ్ ఫోన్ పెట్టుకో స్టార్ట్ చేసేసావా చెక్ అందులో పనిచేస్తే పనిచేసేస్తుంది అది ఇయర్ ఫోన్స్ కదా
Good evening. May I request you all to settle down and take your seats, please? Okay. On behalf of the Indian Academy of Sciences, I'm delighted to welcome you all here for the first public lecture organized as a part of its 89th annual meeting this year. Indian Academy of Sciences was founded in 1934 by Sir C.V. Raman and has been engaged in the cause of promoting scientific activities and the creative research in the country. Beyond promoting science in the country, the Academy is also holding the social cause at the highest level while facilitating all the activities through the help of fellowship. And this annual meeting had a strong focus on the regional issues, particularly relevant to Goa, and sustainability was one of the issues touched in this annual meeting. The public lectures are organized as part of these annual meetings in the evening. The purpose of a public lecture is for the fellowship to listen to the topics from a perspective of a deep thinker from another area than science, and also connect these issues with the society in the region particularly. So one of the public lectures is given by an eminent personality from the local region, and we are really pleased to have Mr. Dean De Cruz with us today to deliver this public lecture. He is a graduate of Sir J.J. College of Architecture in 1983, Mumbai. He set up practice in Goa in 1989, continuing to co-found Mosaic Design Architectural Wing in 2001. Sustainability has been at the core of his design ethos, gradually gaining shape and recognition since 2012, particularly with the urgency of climate change as witnessed by the rest of the community. He has conducted numerous workshops and seminars on architecture, planning and environment, with works and articles published in leading magazines in India and abroad. He has collaborated with the Royal Institute of Art, Stockholm, Oxford Brookes University in United Kingdom, and the Pratt Institute, New York, on architectural and planning programs in Goa. Having designed over 250 houses, 50 hotels, 30 housing complexes, 30 institutions, offices and factories, he is a recipient of multiple awards. His strength today is in the hospitality industry, from boutique hotels and jungle lodges to 200+ room resorts. His current efforts are aimed at improving academic standards across the country through awareness of criteria that address environmental and social issues in architecture and planning. His current emphasis is on urban interventions, sustainable principles and conservation, which gel very beautifully well with the overall program and the theme of the Indian Academy of Sciences activities. It's a pleasure to welcome you, Mr. Dean De Cruz.
Good evening, everyone. I normally speak extempore, but realizing that you're a group of scientists, you're extremely analytical of whatever happens around you, so I thought I'd maybe write it down as well. Yeah. Well, thank you for inviting me here today for this event. It's always a pleasure to speak to people who are enthusiastic about what's happening in the world and concerned about what's happening in the world as well. Most often we think of architects as people who just design buildings. But there's a greater need for architects to actually contribute to what's happening around us. Our education gives us the broad base to actually look at the world in a holistic manner. And therefore I chose the title of The Art and Science of Design, because architecture is this blend of art and science. And design is the process of envisioning and planning the creation of objects, interactive systems, buildings, vehicles, and so on. Art is considered an expression of abstract emotion, while science is considered the measurement of our tangible reality. Art is said to be creative based on personal experience, while science is empirical based on observation. The support systems of a career in science far outweighs of the arts, and making it a preferred choice for students. That's why I see a lot more scientists than artists today. My father was an engineer, so back in those days after leaving school, it only seemed logical to follow his in footsteps and join IIT. Fortunately for me, I did not get in. Imagine graduating and then going to America and working hard and getting only 2 weeks leave in a year to come back and see your parents. Unfortunately, BITS Pilani didn't exist over here in the Goa campus. So instead, I secured admission at JJ College in Bombay, where I realized the world of architecture and design had this wonderful combination of the arts and the sciences, where architecture involves the creation of attractive forms and spaces, using the sciences of engineering to make it viable. During my education, I was influenced by two brilliant designers, Buckminster Fuller, who I'm quite sure you must have heard of, who pioneered the concepts of Dymaxion, tensegrity, geodesic domes, and many others. Over 75 years ago, he published books which are seminal, recognizing Earth's resources as limited and the need to treat it as a living machine, integrated and connected in every way. He challenged the concepts of education and even dropped out of Harvard out of frustration with the dated methods of teaching. He saw the world differently and understood the basic module of stable structure as a triangle, applying it everywhere from small objects to big maps. He questioned the wasteful expenditure on weaponry and showed how if the world could be made better using those same resources and instead supporting livingry. He mapped resources across the world and showed how efficiency could be created by tapping resources in creating products and ignoring these man-made boundaries that divide us. These powerful thoughts influenced my thinking, and even cyclostyle papers. We didn't have Xerox papers at that time. We cyclostyled these copies to actually start concepts of how do you work with a triangle. Normally as architects, the first thing we draw is a square and we start filling it in or cutting it up. And these went on to developing it in various thoughts. This was many years ago for the Goa airport design, using the triangle and then eventually translated into hexagon and subdividing it. This was before the era of aero bridges, where the actual nose of the plane entered the building, and it was a warp slab system. So the departure, from the departure, you walk down a warp slab, entered one side of the aircraft, and the arrival, you actually walk out the other side of the aircraft. So you're always walking down. It's much easier to walk. And they're connected by a central elevator, which also connects up to the aerodrome tower. Antonio Gaudi was another great inspiration. His buildings emerged from the earth in natural forms, where the structural approach of nature was explored in actually highly engineered buildings, almost as works of art. The learnings of both these masters show up in our own work over the 40 years. Nilaya, built 30 years ago, was rated as one of the 100 best small hotels in the world at that time. It captured the multicultural diversity of Goa, using nature and cosmic themes, incorporating craft and recycling building materials. Our projects recall the traditional building systems using arches, vaults, domes, with a minimum amount of concrete, reviving finishing techniques like situ floors, lime-plastered walls, using renewable wood resources like coconut and bamboo. And over the years, trained and mentored over 200 building craftspeople who now work in different places across Goa. The dome, for example, is actually an 11-meter dome just built in plain mud brick, built in 4 days itself, with no concrete at all. A lot of it's recycled materials, as you can see. And every room is theme-based. It's based on, the sun, the moon, earth and fire. The Kandra University in Hampi is an example of an architecture responding to the style and form of construction in this historic area. It has the gopurams as visually anchoring structures, but also functional as wind towers that capture air at a high level beyond the radiant heat and hydrate it, thus cooling it through evaporative means, and allowing the cool air to enter this library building, dropping the temperature by about 8 degrees. It has a central traditional water body tank courtyard from where the heated air escapes, and deep corridors that shade the main building from the harsh sunlight of the area. The structures. The building is constructed with over 90% of it as local stone, recalling these traditional methods of building, where even the columns are about solid granite, about 6 meters tall. The cathedral in Karwar challenged the typical approach to a religious building by moving away from a symmetrical entrance and responding to the side road which really accessed the property. Its roof is supported by columns in a tree-like structural system that floated above the screen walls. The building is stepped to enable its occupants to look at the central altar from a distance, and the area below the raised platforms are underground air tanks to even cool the building. Every work of architecture is a challenge. For the Taj Fisherman's Cove in Mahabalipuram, a 65-room extension, it's situated on a narrow plot in a CRZ area. So we twisted the building and even got Tata Blue Scope to make trapezoidal roofing sheets to respond to its curvature. Architecture is all about adding a twist and pushing the boundaries a little. The Taj Bandhavgarh Jungle Lodge responds to the local building materials of brick and mud plaster, but with technology tweaks of double walls and integrated heating and cooling systems. It is built with the local men of the village, and the women worked on the architectural decoration and also incorporating the arts and craft in its interiors and finishings. The Sarai Lodge did a similar thing in Bandipur and also integrated village construction techniques of stone and thatch roofs to root the architecture of the area. Our lodges don't just respond to the materials and craftsmanship in the area, but also look at passive technologies in heating and cooling the buildings. Some lodges, like the one in Tadoba, have a different approach, where we use recycled prefab panels to create a building that is lightweight and sits 12 feet above the ground, using fallen jungle wood and recycled thin planks for its finishing. Being lightweight is an approach that Fuller also spoke about determining the efficiency of buildings. Hence, in this office building we worked on a hollow column, hollow beam, it's in Noida, hollow column, hollow beam structural system, which actually ran the services right through the structural members. Most often, structural services actually run cladded to structural members, creating a messy situation. Even the air conditioning system was a high velocity system, much like the ones used in vehicles, giving cool air at its needed points. The building is in steel, completely modular, with stone slabs mounted on neoprene pads. This allows for change over time and even complete dismantling of the building. And if one sells it after dismantling, one could possibly get more than the cost of building, a constant rise in construction prices, whereas most buildings actually are demolished and all its value is just landfill. We incorporated passive cooling systems of green walls, underground tanks, and solar stacks. For the thin wall cladding in places, we had the choice of using a natural stone or a vitrified tile. Natural stone seemed the most sensible choice from a perspective of embodied energy. But when we visited the quarries, we found the tremendous water and air pollution, and more than that, the human rights violations, where workers were almost treated like bonded laborers, trying to repay the loans they had taken. Whereas a vitrified tile, even though it had a high embodied energy, used material efficiently, it handled pollution effectively, and gave workers a fair wage. So when you talk about sustainability, it's understanding individual situations and responding to them in a sensible manner. This is Antilla. I think we all have seen this building. It's a fancy 26-story building housing 5 people, I think 4 now. It has a platinum LEED rating for its efficiency. Design sustainability is not just about materials and energy, but also about how much we use of it per capita. And if we are really concerned about lowering our carbon footprints, we should also be looking at lowering our physical footprints too. Thus, we're working on a small 50 square meter, 2-bedroom house, which is completely off the grid, self-sufficient in water, energy, and partly food as well. It has a built-in flexibility and quick to build. Efficiency is also about the speed of construction and flexibility. The water has an approach envisioned to be closed loop, cleaning its waste, much like in ships and space stations. Its fresh water and wastewater tanks actually act as the foundations of the main building. In fact, Fuller in his designs had worked on shower systems for submarines here. And you could shower in half a glass of water using a high pressure jet in an enclosure where it didn't really need any water drainage point. It was high pressure, so you didn't need soap as well. You just run it over your skin, and eventually the evaporated air would be sucked back into the system and taken on. So we have technologies today that we can actually use effectively in areas where resources like water and energy are in short supply. This book on sustainability opens one's mind to the various complex issues of sustainability of money, cultures, value systems, community engagement, and challenges of the future. A must-read for any designer concerned about these. We had an opportunity to work on the Sustainability Center at a large scale, having been shortlisted to design the Sustainability Center for the Pune municipality about 20 years ago. It gave us a chance to really understand the issue of materials, technologies, and systems, to deliberate on it and provide possible solutions. But designing responsibly is also about engaging the end user. In this very small, low-cost house, which is actually just here in Vasco, the clients actually got involved in purchasing the materials, directly engaging the workmen, decorating the house, and adding all the finer details to it. The boys actually sacrificed their scooter handle, the CDs, and the skateboards and everything. So it was a personal experience, and that's extremely rewarding. If you're looking at sustainability, it's also about engagement. It's about how do you get people on board to understand these issues and really work with them. This also brings us to the question of, does architecture need to be permanent? And how light the footprint can we go? This 40-seater beach restaurant for the Taj, we used all natural materials, some of which get renewed every season. It costed about 9 lakhs, and with a profit of about 50,000 every night. It has covered the cost of construction in just under 3 weeks. We suddenly see the viability of an architecture which is really temporary, used only for the purpose that it's meant for. The Japanese are experts in being lightweight, and for these temporary beach rooms, we used wood much in the same way that they do, lifting it off the ground, keeping it as transparent as possible, enabling one to feel its free-floating nature, and adding a Japanese aesthetic of minimalism driven by nature themes and climate seasons of winter, autumn, fall, summer. And then interior detailing also included a haiku describing the season. The world over, people have developed their own approach to architecture, using materials available to them in close proximity, with building techniques handed down through the ages. Most have been lightweight, using natural materials, and not even designed by architects. This interesting book catalogs a number of these approaches. In fact, it's only in the last couple of centuries that we have penetrated the biosphere in search materials, metals, and heavy construction, and energy materials like oil and coal. This has led to the pollution of our biosphere and a complete reliance on the lithosphere materials, unlike biosphere materials, which get recycled in nature easily. And this delving beyond the surface of the biosphere has really been the major problem, whereas biosphere materials really are able to be renewed, provided we use them judiciously. When people speak about holistic design, it's best defined by a design that responds to the needs of the user, by creating a link with the past through research, contemporizing it for the present, and envisioning its change to the future. Its design approach that addresses all aspects from the external to the internal, the spatial experience, and to the tangible objects one uses and feels. This Ayurvedic spa for the Taj emerges from a study of the snake temples of Kerala and demonstrates these principles, right from the spatial effect and creating rituals as you move along. Buildings need to be celebrated in the way we live in it and the way we use it. Yeah. So the inside of the building is also lit with diyas, which is ritualized when it's used, and so is the outside. In design, we research. We look at where we can draw inspiration from, in this case, the temples of South India. What are the themes we could use of earth, air, fire, water, creating spaces that capture that spirit, and detailing it out in every way in terms of the artifacts, the menu cards, and the furniture that is developed for it. Most often as architects and designers, we tend to serve an elite clientele, designing high-end homes, hotels, and institutions. But it's this inspiring book of Design for the Real World by Victor Papanek, which really defines the true needs of people, catering, in this case, it influenced us to actually create a moving school, catering to construct the children of construction workers who constantly get moved from site to site every few months or so. So here the actual school moves with construction workers, and the teacher moves with the school and imparts their knowledge. It also brings dignity. In this case, designing a trike, which is electrically assisted, for Lamani women who normally carry recycled materials across in heavy bags. So this is sponsored by an NGO, which actually allows them to carry these loads in dignity, cycling around with electrical assist. It's about imparting knowledge and educating them. In this case, teaching kids about composting and how it could be done in a fun manner. You can actually turn the composter around and it composts even faster. Or look at how we can work with industry. Our office actually designs, if you have an IFP machine, our office has probably designed that machine as our product design wing is. So we work with IFP to actually look at how their cartons could be used effectively, because normally they're thrown, we unpack your machine, the carton is thrown away, and here you can actually reuse your carton as seating. So even the cushioning of the machine actually has these inbuilt cushions at very little extra cost. As a design firm, we felt we could do much more than the typical architectural and product design projects we work on. And so we established the COCOM Design Trust to bring design in the public domain and for greater good. One of the areas we felt needed to be addressed was the social sector, where we believe that good design could actually solve a number of problems. Design which involves social problems are called wicked problems, and they're problems which are influenced by cultural diversity, social differences. And these are really interesting problems to solve because you really involve the public and understand the ground realities. So we looked at 7 different arenas in which we could actually solve these problems in terms of learning spaces, resilience, environment. So this we held as a workshop, which is where we addressed these 7 issues a few years ago. We worked with and partnered with Justice Adda, which is an organization dedicated to being to bring greater understanding and accessibility to justice systems to the common man. We identified 3 typologies, which is the police station, secretariat, and the High Court, as areas where we could make a difference. So we actually involved the College of Architecture, the Law College, and PhD students from BITS as well, in actually going to these spaces and understanding how we could make them more friendly. Going to a police station or a government office or a courtroom is extremely intimidating and unfriendly. But how could we actually soften these as designers through communication, through wayfinding, through means in which you can make people feel acceptable and dignified in this space? If you look at judicial systems, the judge sits on top and you sit down over there. The police station is another frightening experience to go to. Government offices, so bureaucratic with these corridors, multiple corridors all over there. That's why they keep on calling them corridors of power. So how can we actually change it by changing the form of these buildings, the layouts of these buildings, to make them more friendly? So these studies were really interesting, came up with some really interesting solutions to them. So design has a great potential to actually bring about changes to the way we use our buildings. As an academic, I also had the chance to work with the Royal Institute of Art on the envisioning of the future of Goa, understanding its assets and ecologies, and seeking ways to find a sensible and sensitive solution to the problems it faces in Goa. So we looked at the various ecologies of Goa, the various areas that we have in terms of the coastal areas, the plateau areas, the field, the forested areas, and how the coastal areas are being oversaturated, the interior areas, the forest areas through mining at that time, and how we could address that in many ways. We also looked at governance systems, and governance systems are usually bounded by these smaller political boundaries, whether it's wards or village panchayats or districts. But really a geographical boundary system is a watershed. A watershed is where all the water from the area is collected and there's a single stream. And India, in fact, is a giant watershed. And we subdivide the India. So if we actually look at political and governance boundaries by watersheds, we'll have a far more efficient system of governance in place, where water is the life giver of everything that we have, and looking at that as our boundaries. Every village has an asset. Some villages in Goa, for example, is known for its banana, some villages for its watermelon, some villages for its rice or other products. Being an agrarian society, of course, coastal villages for its beaches and fish and tourism maybe. So every village has an asset and maybe a different asset. But how do you actually network these villages, bring economic development where you're actually trading the assets that you have? And how do you preserve its assets of its coastal areas, its forested areas, its field areas? There are many examples worldwide. For example, the fields, if you see in Southeast Asia, the concepts of agro-tripping, which is basically bringing tourism, but a live tourism, where you participate in the actual development of the state through agro-tourism. The experience is far more rewarding. How do you link these biodiverse areas through things that we call chlororinks? We look at these pockets that are slowly, you must have heard recently in Bangalore about that leopard entering an urban area. And it didn't enter the urban area. The urban area entered the leopard's area. So we really need to look at how do we actually preserve and connect these biodiverse spots to continue the biodiversity as a fabric throughout our state. We worked with Pratt Institute on a coastal village in Agonda to study it as a typical case, and as a case in which tourism was just affecting it. This was about 10 years ago. We looked at how tourism was affecting the village, and being a turtle nesting site, extremely sensitive in terms of its development and how it could be brought about. And keeping sustainability at its core. So with sustainability at its core, how do we look at the environmental issues, the social issues, at the same time allowing for economic development of it. And we also looked at smart ways, and unfortunately smart has been misused today in sort of smart cities that we have, but in terms of how we could actually make things specific, measurable, achievable, realistic and timely. So keeping the reality of what actually can be done in a particular time frame was the main goal. And achieving it through a vision. Everything that we need to do for the future is through a vision. And this is a vision that was created by the people, mapping it. These were 10-day exercises held over 3 to 4 years with the people in their village intensely, where we stayed on site and actually worked with people. And thus this gave me a background to actually work on the regional plan for Goa. So about 15 years ago, I was asked by the Goa government to actually, along with Charles Correa, Edgar Ribeiro, to actually work on the regional plan for Goa. And the first thing, as an architect, not a trained planner, was understanding what Goa is all about. And that's really its natural and its built heritage. So we really needed to preserve what we had as a resource in terms of our coastal areas, our fields, our forests and orchards. We decided that we needed to protect them and therefore map them. They mapped all the eco-sensitive areas of Goa as Eco 1 and Eco 2, preserving them as no-go areas. And we mapped also the settlement areas. Where is development taking place so far? And mapped them in terms of its density. And how do we actually connect these all? Connect them to roadways, preserve the certain density so there's no strip development or ribbon development, as they call, which stretches across highways. But in fact create a development in which you're creating nodes for development, where road and rail meet, rail and water meet, or areas where you have at least 2 networks of transportation to allow for development. We assisted villages in understanding what their village is all about. It's the first time that, besides Kerala, a participative plan for development was created, where we actually created a framework and took the plan to the people saying, what do you want? This is what you have as an asset. Can you map it? And so the people mapped it. They actually mapped, this is the village of Para, which is very close to my village. They mapped all their fields, their forest areas, their water resources, their animal paths, their bird nesting sites. And in fact, in this village, all the large banyan trees of their property. It creates a certain sense of belonging to the place, a certain sense of identity, and that's what is needed. And we also had to make them understand what development is all about. So we created a presentation which actually talked about what development and infrastructure is about, where when we talk about infrastructure and development, we normally think that it's infrastructure is about roads, buildings, factories, but infrastructure is also about where we get our water from, where we get our food from, where we sequester our carbon dioxide, where we get our energy from. And usually as a resource, we need about 4 times the area from these natural resources versus, say, the hard infrastructure, or what we call the gray infrastructure, to support it. So to give this understanding to people, you cannot convert all the land as settlement area and develop everything. You have to have a green space, which is your breathing space, which is your resource space for everything. Goa is an assemblage of some 300 odd panchayats, maybe 420 or something odd villages. And every village has a completely autonomous nature to it. Every village has usually water bodies, an orchard area, fields, settlement areas, which actually make it completely self-sufficient in its structure. And therefore we need to work with these villages to make them realize that they're actually independent and capable of not just being dormitory towns to urban areas, but actually economically independent as well. While the regional plan is many years old now, the issues of unsustainable development still persist. And with the people concerned about how to address it, and for that reason, a few of us got together and we created a platform called Act for Goa that actually empowers people to be able to police, complain, and lobby for development that is appropriate to Goa. So Act for Goa actually has a website and an app where you can actually map. You can go to a place, you Google pin it, you can say, okay, fine, there's a field being filled or some development's happening or something's being cut. And it'll tell you the owner of the field that can pop up. It can pop up your form for complaint or find out if it does have a license. So these empower the people. I'm part of the Goa Foundation, and at Goa Foundation we get constant complaints. Somebody says, somebody's cutting my tree, but you can do something about it. So Act for Goa actually looks at ways in which people can actually take up the action on their own by empowering them with the data and the means to. All development, they say, is market driven, and the best way of handling it is creation of a circular economy and closed loop systems. All over the world, people have been addressing it in different ways and coming to a realization that social aspects of health, equality, energy, food, etc. are important, as well as ecological aspects of climate change, land conversion, pollution, etc. And this has led to a concept of a three-dimensional circular economy, otherwise known as a donut economy. And it's very interesting. There's an Oxford professor who actually developed this theory for donut economy, which is a resilient economy in which you're taking both the social aspects and the environmental aspects on board in creating a circular economy. As design chair for NITI University, we are working on a new curriculum that will start redefining the roles of architects in societies, where designing buildings is just one small aspect and creating sustainable communities the bigger goal. For this, we are going to have a curriculum change where its new campus will take students through the whole process of design, from understanding the land and community engagement to actual buildings with all the materials and technologies. Envisioning the future is always exciting, and like scenes from Star Wars, has many possibilities. Though Star Wars seems to be from a parallel universe, it is actually about our present, a fight of good over evil, to sustain a future with all its potential technologies and advances, but always drawing from the imagery and values of the past. We all have a potential in whatever field we are in to envision and design our future. May the force be with you. In case any questions, you're most welcome to ask her.
Thank you very much. Are there any comments or questions from the audience?
Very impressive talk. I would like to know if you would like to comment on the differences between the design of machines, which scientists do most of the time, and design of the structures that you design normally. What are the crucial differences, or if there is any difference?
I'm sorry, I didn't get the question exactly.
Design of machines, scientific equipments and so on. So designing those and the designs that you described, is there any fundamental difference in the approach? The machine should also be designed in a way which is sort of harmonious in some sense or something, have some artistic value, or what is the crucial difference
between a machine and a building?
Building machines, of course, they have a purpose, and here also there is a purpose. So what would be the crucial differences?
I didn't get that exact. Could someone? Yeah, transfer. Yeah.
Versus design, the kind of design that you are talking about, is there a crucial difference between machine design and the design that you talked about?
So actually, so I mean, as a firm, Mosaic is a firm that actually designs both buildings and products. So besides the IP washing machines, we're designing lights and fans for the new range of lights and fans for Crompton Greaves. We designed the front end train of the high-speed trains in some parts of India. The Skybus that you saw in Margao was, the body was designed by us. We designed bodies for various, industrial purposes. And machines, of course, have a certain vocabulary. For example, we look at, say, a vehicle design. We worked on tractor bodies, for example. So what is the expression you want to give? What will actually make people buy a machine? What is the selling point or the USP? Besides, of course, the efficiency of the machine itself, the visual aspect. For example, if you buy a car itself, while you're concerned with the performance and the mileage and the various features it has, you're also concerned about the looks of it. So bringing in an aesthetic, bringing in an approach of what connects to the people. For example, the same car which is, say, sold in the Gulf usually has a lot more, gold trimmings and silver trimmings to it, whereas the same car, say, a Mercedes, sold in Europe itself. It has less trimming because they require a lot more flash over there. So it's really about even cultural aspects that you actually look at. So in designing a machine, it's not necessarily just the raw mechanical working parts of it. There's also an aesthetic aspect that's needed. Whereas buildings, actually, it's far more complex in a way because you're dealing with so many users. Yeah. In machines, it's usually just a few users. In buildings, it's multiple users. It's not just the owner of the building, it's the people who use it. Say, if it's a university, it's the people the students, the faculty, it's the people who clean the buildings who use it. So how do you respond to these various uses is extremely important. So how do you make something that's fairly universal in a way that stands the test of time as well? Because buildings last a lot longer than even objects or machines. So this needs to last even longer. But there are possibilities of how do you upgrade a building. More and more buildings are getting redundant fast. Technologies are improving quicker and quicker. And therefore, we need buildings which are either flexible or actually designed for a specific time period. Yeah. If that answers the question. Yeah.
If I may, yeah. Thank you so much for a really refreshing talk on the aspects that really touch us when we don't really explicitly think about it in a technological
Just a little louder,
institute.
please. Okay.
Yeah, so I was thanking you for your talk, and my question is that in an area like this where you're talking about architecture and design and sustainability, would you look for, what do you think is the market for education in this space? How many students do you think we could attract if we were to design a program in architecture and design as part of a technology institute? Would you be able to comment on that?
Yeah, when I studied architecture, there were 20 colleges of architecture across the whole of India. There are now over 600 colleges. And the profession is suffering greatly from this thing. There are not enough academics to actually engage with architecture. And the standards have dropped dramatically. So it's important that how do you actually look at this? It's a challenge which maybe you cannot address immediately. So how do you integrate, say, the way universities abroad do is, can you actually engage your university with the professional world? Yeah? So you'd actually get part of your training live in an office. Yeah? And like what we're doing in NITE now is actually making sure that, rather than sit on hypothetical design projects, the students are actually going to be involved in the whole building process. So the more live it is, the quicker they're able to actually grasp the concepts of design and its execution. Sadly, the profession is getting redundant. I think we need to look at architects not just as people who build buildings, but who build communities as well.
So thanks for a very fascinating lecture, and it was very soothing because your voice was so soft and sort of as though everything was happening with ease. But my question is about, you said Act for Goa, and I would imagine that some amount of activism is also necessary, right? And I'm thinking of other places like Pune and Hyderabad and places like that where questions about conservation archaeology really, come up with hurdles, especially of the state. The state becomes a major hurdle, right? Because there's this whole question about development and then destruction of, some indigenously organized old structures and all that. So how much of this, in your professional journey, how much of this, whatever you have done and however you are thinking of the future, how much of it involves serious activism?
A lot. Yeah, I'm also actually currently the president of the Goa Foundation, which has had a lot of landmark judgments in court, where we've taken on the mining lobby, we've actually got some really nice landmark in terms of forest areas, in terms of sand mining and CRZ areas. And for that, you get a lot of flack and pressure from the government. Though I'm not a street fighter, there are a number of people who are street fighter. We prefer to work with the law, work with hard data, and actually put it across. And unfortunately, we really have to, at the end of the day, to go to the courts to do that, which is a sad aspect. The reason I was put on preparing the regional plan was I was the one, along with a number of architects, who actually opposed the previous regional plan, which is the 2011 plan. So we actually had a three-pronged approach. We took the streets, both in Panjim and in Margao. We got 8,000 people, which is a record without having to send buses and give biryani for lunch. We managed to get people to come on the street because we had communication. We actually put out drawings, we put out, this is what's going to happen. We did photo montages to say that this is, say, Baga Hill, it's going to be full of buildings, so you need to stop it now. And people realize that. So it's all about communicating your idea clearly. Besides that, of course, we tried to lobby with the political thing. I even wrote to politicians in the center. And of course, we took to the courts. We had 4 Parsi lawyers who came down and actually represented us in the courts for free. So this three-pronged approach really worked well. So it's not just about activism, but a multi-pronged approach that really worked. And as punishment for blocking and stopping the old regional plan, which is the first time any regional plan has actually been revoked, I was put on to prepare the new regional plan. And I realized that stopping a plan is far easier than trying to make a new one. Yeah.
If I take metropolitan cities or any city as a it's a very complex situation. We say that a city like Pune are not growing, they are swollen beyond a point. What's your insightful thought about how to redeem these things? Are we beyond point of no return, or there is still some hope? That's the first question. The second one is, in such situation, how much of modeling, simulation will work, if at all?
Unfortunately, our cities are at breaking point. Yes, you're right. I mean, look at Delhi's pollution levels today. It's dangerous level. It's almost killing people. All cities all over India are actually facing a great issue. And the problem is urbanism. India is just 30% urban, 70% or 35% urban now, and 65% rural. And we're aiming for a 50-50%. Places like America and some parts of Europe have gone up to 70-75% urbanization, but they have all the infrastructure to support it. We don't. So I think we need to look at a new model of how we're going to grow. And the answer really lies in supporting tier 3 cities. Is keeping and creating density at a much smaller scale. Density is needed, no doubt, because it brings about efficiency of all your resources. So whether you're supplying water, power, your road networks, it's nice to have a certain level of density, but the moment it grows beyond a certain point, it can become destructive. And therefore, to determine what is the correct limit of density of a thing, where you can get all your resources from close by. Most cities, for example, the water is piped from 40-50 kilometers away. The power comes from someplace else. And you're actually depleting those resources from where you're drawing those resources. Food comes from a great distance. So if you talk about sustainability, it is actually long-term unsustainable. There's a very interesting book called The End of Oil. And it talks about the scenario of what if we had no oil. And if we have no oil, we would not be able to support 9/10 of our population. We will be down to 1/10 of our world population. It is oil that actually brings us the capability of transporting materials across great distances, of energy, and bring all the other resources we need for a proper livelihood. So let's look at a scenario where we do not have this horrible resource, polluting resource, damaging resource of oil, which is the big cause of climate change, for example. And how do we actually reduce that? Yes, we can't kill everyone and get down to 1/10 of the population, but how do we actually reduce our needs? And that really comes from being local. And that's why when preparing the regional plan, is said, let's be as local as possible. Can we get our food resources? We don't have to get our apples from Himachal. And we've been spoiled with the ability to actually transport things over great distances. So how can we actually get people to change the way they live and really be local in everything they do? Luckily, with the pandemic, the ability to work from home, the ability to communicate a long distance without having to travel has offered us a possible solution. So we should really be tapping that as much as we can.
Thank you, sir, for this nice lecture. I shall be
Okay, right. Thank you very much. That was a wonderful talk. And the beautiful pictures you showed of the buildings you've created, of the spaces that you've created. I had two quick questions. One is, when you're faced with a problem of designing, how do you start? What is your thought process? That is one thing, the architect's mind. And second, in this era of artificial intelligence and generative AI in particular, which is now the computer systems are coming into the domains of artists and musicians, what do you think is the future? I mean, will the systems also be able to design such beautiful spaces? And so as a discipline, is architecture also worried?
I think AI, as we all know, is a tool. I mean, I studied at a time when the most sophisticated computer, all my calculations were done on a slide rule. If I show it to students today, this is a slide rule, can you calculate it? They can't figure out what it is even. They haven't even heard of it. So computers came in, much afterwards. And I can see the change that computers have actually brought, a detrimental change to the way students think. Because a lot of thinking now happens in the computer. They do not think themselves. Above my drawing board in college, I had a little sign which is think before you ink. I mean, if I used to use a rotring pen to actually draw out everything, there's no way you could erase it from the paper. So you had to have all your thoughts in your mind before you actually put pen to paper, because you couldn't erase that. And that rigor has been lost in today's architecture. It's all about lines, you zoom in, you zoom out. The sense of scale has disappeared. And in a similar manner, AI is actually creating that problem where it's a very superficial things. AI is powerful, no doubt, because AI can draw the images, but it draws images from what's available on the net. AI, with time, will progress. It'll actually become far more developed. It doesn't right now look at structural systems, services systems. It's pretty images, quite fascinating to most people, but lacks the depth of its resolution. It will probably develop with time, actually having structural systems inbuilt to it. But I think it's also about the creativity that we actually put into it. While this will create systems that will offer us possible solutions, there will still be leaders needed in actually envisioning what the future is all about. Because AI only takes what exists, processes it, and throws it at us. So we need to create visionaries as designers to be able to actually determine where our future is heading.
Very nice talk. I have a quick question, which is that, these days, very often we are trying to save electricity inside the buildings. So we have sunroof and so on and so forth, allows the light to come in, so we don't need, artificial lights. But at the same time, there is air conditioning in the buildings. So there is a sort of, opposite poles. While the sunlight comes in, the temperature inside the building goes up, and then we have air conditioning. Overall, I'm not very sure that we are saving on electricity and what's happening to the atmosphere. What are your thoughts on these?
I mean, for centuries we've lived without air conditioning. I mean, we had passive cooling systems. You look at the buildings, say, for example, in North India with their jali walls or high evaporative cooling systems. They did it fairly effectively, and they're fairly comfortable buildings. But with the advent of technology, where you have these machines run on electricity, it's made us actually reliant on them completely, and actually prevented us from actually understanding what these passive systems and incorporating them, whereas one easily can. When we designed the Sustainable Building Center for the Pune municipality, we had designed auditoriums which actually had louvers on top. We're sitting here in bright daylight, and you still need lights on. Whereas that could actually modulate the light and bring it in. It could also take the hot air out. the air conditioning system was an underfloor air conditioning system. So again, you got your air conditioning exactly where your seat was. You didn't have to cool the whole volume of it. So the various means in which you can actually look at passively cooling the system. But because power has been so cheap to us that we don't really bother about it. And people really have a great misunderstanding of what is cheap and expensive. Because nature is actually paying for everything. Everything we use and we call cheap, nature is actually subsidizing it tremendously. And that, if we realize that and actually take the true value of how we're damaging nature, I think then only will we wake up to the reality of our consumption.
Thank you, sir, for this nice lecture. I shall be going back with some idea about my next lectures to introduce some of the subject matter related to symmetry. My query at this stage is that while
hold this mic up, please.
While designing a particular architecture, do the architect considers structures created by animals or simply animal builds or creations created by small creatures and so on?
Yeah, actually, it's called biomimicry, where the animal kingdom has actually understood how structural systems work, and human beings have adapted to that, looking at how they've intertwined natural materials, how they've actually responded in an elegant manner to structural systems, responding to climate at times. If you look at, say, bird nests or a lot of other creatures which rely on, say, some sort of protection, there's a lot to draw from it. And biomimicry is not just about nests as well. It's also about how nature provides its structural systems, its services systems. So in fact, when I took the concept of the triangle across, I looked at road networks across cities and why are they so inefficient? If you look at nature, I mean, traffic is like a flowing, dynamic sort of movement here. And if you look at nature, whether you look at our circulatory system, if you look at the venation system in plants, there are no crossroads. It's all about divergence or convergence of movement through a system, through nature. And therefore, if you actually triangulate your road networks, you actually only have roads that converge or diverge, you'll get a far more efficient circulatory system. The distances may be greater, but you do not have stopping. So we actually did a simulation on, if you suppose you have actually a triangular system, which is popularly called in Goa as the Tinto, which is basically a 3-road junction. You don't have to stop. You can actually keep on circulating through a space. You may go a greater distance, but the fact that you're not stopping, you're not wasting the energy of actually stopping and starting again. So that's a response to nature, and understanding that in nature's flow, it's far more elegant, far more efficient. And there's a lot to draw from nature. In Gaudi's work, for example, all the structural systems are based on nature. Those arches that he has drawn over there, he used to hang his models upside down. So all those, the Sagada Familia, the first building I showed, is a building which is, some of those towers go up about 20 floors, all in stone. And he models it by just hanging the building upside down. He just takes strings, hangs it upside down, and he gets the exact curvature of the arches that are needed, and then inverts it, and that becomes an arch that stands on its edges. So nature really has those responses built in, and if we understand that, we can definitely draw those principles.
Okay. Thank you. During the day, we listened to technical talks in science and technology to achieve circularity and sustainability. It was very nice for us to listen to you and appreciate how the concepts in art and science of design and planning, along with the socio-economic issues, involvement of people with nature, are crucial to achieving this sustainability. Thank you very much. On behalf of the Academy, we have a small moment.
Exactly 1 hour, very good.
manifestations and wonderful public lecture here, triggering our thoughts. I think we need a bit of relaxation, a bit of entertainment, and our students here at BITSCO are ready to provide some of that, beginning with a magic show for you. One of our students is extremely good, so he's going to perform a bit of magic. And we usually say BITS is magic for what we do for our students, and some music. Hopefully you'll be able to enjoy it, and then we'll end with a dinner at our guest house lawns. Thank you very much.
So this is on behalf of the transport team. Let me just quickly share few information with you. We have a travel desk outside. If you have a requirement of transport to the airport tomorrow, please register over there. And if you do not do today, then till tomorrow at 11 a.m. you can register. We will make arrangements. But if you go from hotel directly, hotel will take care of your transport. So this is from our side. Once again, transport from BITS to airport can be arranged if you register. Thank you.
I guess we just need to wait for a few minutes before the magic show. So please don't go away.
Gaudi is fantastic. It's Sagrada family. You think it's decorative? No line, no single line, no straight lines, no straight lines.
Thank you so much, dear. That was delightful. No, not at all.
Complaining about the food.
We'll have a separate discussion on that. Yes.
On the stage.
Thank you. So do you have any initiatives helping universities design their buildings?
Yes, I'm actually working on this, right?
मुझे कोई भी चेंज करना है E101 चेक करो कौन okay okay please check okay
No, we didn't get it. We just I think you already had
I didn't know. I will talk to you later. They need a collar mic, the magician. Collar mic. Yes, sir.
আমার ভাইয়াকে বাজো করে check blocking
So now the modified program
check
China was allotted for stand-up is now the everything is
Good evening everyone. Today while this setup is done, I'll just entertain you with a few magic tricks. Yeah, I'll just come in the audience. while the setup is doing, I just entertain with some magic tricks.
No, not me. I think
Okay.
you need to entertain others.
It doesn't matter, sir.
You can call someone to the.
Okay. Sir. Would you like a magic trick?
Oh, no, I can ask anyone who are among us here. Want someone?
Like while the setup time, while the setup is getting on.
You want to try something? No, just wanted to meet you.
Okay, sir, I understand.
No, we are from BHU. Yes, when they have been introducing the magic started, you announced that magic has started, so he is the person who will show us the magic, and it has already been.
Yeah. So, hello everyone, I'm going to show some magic. Actually, I'm going to do some close-up work, so I need to go in the audience. So.
First talk from there, then come down.
Good evening everyone. I'm going to show some magic tricks. I'm going to come to the crowd, and while the setup is done, I'll just entertain you. Yeah, I have a.
Oh, you have.
No. Can I start with you?
Okay.
Yeah, she can. But you have to face them, no?
How many people?
Yeah.
I'm actually a close-up artist, ma'am. So
It's fine. Come here.
Can you come?
Come here. Light will move. You come here.
Would you mind just picking a card?
Just say we are beginning.
Yeah. So, guys, I'm beginning with some magic. Okay. So ma'am has picked a card. Yeah. So ma'am has picked this card, and it's in the deck. There are many ways to get the card lost in the deck. You could give cards, you could give shuffles like this. But what happens when you give this deck to kids? They shuffle the deck like this. They turn over cards, and they make a complete mess of the cards. So if I lift the deck somewhere over here, the face-up card is on this side. If I lift it somewhere here, the face-up card is on this side. If I lift the deck somewhere, there are no face-up cards on either side. But if I just snap my fingers, the whole deck is in complete order. Except for one card, which should be ma'am's card. I need to help ma'am for another trick too. So we're going to play a game. It's called Card Monte, and the job of the the spectator, which is ma'am, you have to track this card, the 4 of hearts. Okay. So where's the 4?
With your hand.
Yeah, it's here, right? It's good. I'll create a distraction. I'll just add another distractor card. Ma'am, could you just give a hand like this? So what card are you holding, ma'am?
My card.
Yeah, ma'am is holding the 4. Okay. It's easy. I'll just put one more distractor card now. I'm just turning over the cards like this. Could you give a hand, ma'am? So, what card are you holding right now?
Distracted. Sorry, the right card.
It's here, ma'am.
Sorry.
I switched it. You didn't notice when I switched it. I'll make it a bit easier for you. Just hold it. What card are you holding? You have to track the 4, right? So where is the 4? It should be here, right? Check it. But I'll make it a bit easier. The thing is, ma'am has 2 eyes and I have 3 cards, so it's tough to track. So I'll just get rid of this card. So I have 2 black aces right here. So where is the 4? It's in my pocket, but when you look at my pocket, I just switch it. I had an ace in my pocket. But even if you feel it's a sure bet, ma'am, even if you feel it's a sure bet, you shouldn't take it because I'm cheating. I have extra cards. But you might be thinking whatever I'm doing right now is sleight of hand. But you have to believe that whatever I'm doing right now is pure magic. I just go in, yeah. I'll do one with you, sir. Huh? I'll do one trick with you, sir. Sir, could you just pick out any card? Yeah. You can like show it to me too. It doesn't matter. Okay. Sir has picked the 10 of clubs. Okay. Sir, could you mind just standing up if it's okay? It's fine. Sir has picked the 10 of clubs. Okay. So your job is to track this card, right, on the deck. So where is the card right now? It's here. So do you trust me if this is the card? You should not trust me. Like it is going in, right? Just push the card in.
What is this?
Okay. And we'll do one more trick. Just pick any card, sir. Yeah, show it to the audience, don't show it to me. Oh, man, don't worry. Put it back inside. I'll pick another one. Put that in.
Okay. You saw it, huh?
Yeah. Oh, I didn't see.
You saw it already.
Doesn't matter, sir. Okay, it doesn't matter. I'll just put it inside the deck like this. Okay. And if I just go behind my back and do some like this, okay. When I went behind, I just turned one card upside down from the deck. And hopefully, I just felt the card. Is this your card?
No.
It is, yeah?
No.
It is.
No.
You're trying to trick me, sir. Yeah. We'll do one last pick. Okay. Just pick any card, sir. Okay. I won't look behind. You can like show it to the camera and everyone else. Done, sir? Okay. Place it here. Where's the card? Place it here, sir. Card. Okay. So everyone remembers the cards, right? So I'll just give this deck a few cards and a few shuffles like this. Oops. Sir, I'll be needing you to like pull out both of the hands. I'll just make 3 partitions of this deck, and what happens is I expect that at least on the bottom of one of these 3 packs there should be Sir's card. Okay. So even if I find your card, don't tell me. Okay. So is it visible? Yeah. The king of diamonds. I don't think this is your card. No. Yeah. So I'm just gonna like pull it out like this and place it here. Okay. 8 of hearts. I don't think this is Sir's card either. So I'm just gonna pull it out like this. Even if it is your card, don't tell me. And the third one, the king of diamonds. I don't think this is your card. So I'll just pull it out like this. And oops, so sorry, sir. So what happens is, it generally happens that there is one card which comes out to be yours. But I don't think I did it right this time. So could you tell me any number between 1 and 10, sir?
Me? 5.
5. No influence from my side, right? So I'll just deal out 5 cards right over here. 1, 2, 3, 4 and 5. Right. If you had picked 6th, the card would have been the ace of spades. If sir had picked 4, the card would have been the 6 of diamonds. Could you tell me, sir, what was your card? Could I tell you? It was the king of diamonds, right?
Yeah.
Yeah. The king of diamonds. But now you might be thinking that the king of diamonds was here, right?
Yeah, it was here.
It was there. But the thing is, this is a totally normal deck. There are no duplicates in the deck, so this card has changed.
There are some special cards or what?
It's not even my deck, sir. I just got it from a friend. The thing is, sir, I could manipulate cards easily. If this is the 5 of diamonds, I could just shake it and make it the jack of hearts. You never know when I switch cards.
You all ready?
Yeah, I'm gonna perform.
You have a magician in Bengal named Sushita.
Okay.
He teach the audience
Oh.
how to do some magic. You can choose one.
Okay. Actually, sir, where magicians have 2 rules we could not break. First thing is, we could not do the same trick twice, because the first time it's a trick, second time it's a lesson. And the second rule is we could not disclose how we do our tricks, because it's against the code. I'm so sorry, sir. No, sir, I just learn by observation. I like try to catch people do their tricks and I do it. I don't know him exactly.
बोल ही रहा हूँ मैं अभी आ रहा है हेलो चेक 1 2 6 चेक 1 2 6 हेलो हेलो चेक 1 2 6 हेलो 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 सा बाकी है, गए तुम गए हम थम गए, हर बात बाकी है, गए क्यों? न आए हो न आओगे, न दूरियां दिखाओगे, न थाम के वो जोश में होश से उड़ाओगे। न आए हो न आओगे, न झूठ से सुनाओगे, न रूठ के सिरहाने में रिमोट को छिपाओगे। गए तुम गए हो क्यों, रात बाकी है, गए तुम गए हो क्यों, साथ बाकी है, गए तुम गए हम थम गए, हर बात बाकी है, गए क्यों, ये क्यों? रात भी थम गई ना थकी, रात भी ना बटी ना कटी, रात भी छेड़ती मारती, नींद भी लुट गई छिन गई, रात भी ना सही ना रही, रात भी लाज़मी ज़ालिमी। गए तुम गए हो क्यों, रात बाकी है, गए तुम गए हो क्यों, साथ बाकी है, गए तुम गए हम थम गए, हर बात बाकी है, गए क्यों, ये क्यों, गए क्यों, ये आए हो न आओगे, न दिन ढले सताओगे, न रात की नशीली बात से नींद में जगाओगे। Thank you. Before we leave, I'd like to introduce everyone who was a part of this performance. On the guitars, we had Raymond. On the bass, we had Tejas. On drums, we had Shaurya. On the keys, we had Harshit. On vocals, there was Saket, and I'm Shiv. Thank you so much.
Guys, can I have more levels on the vocals? Hello, hello. Hello, sir. I want a bit, excuse me. Reduce a bit of reverb. Reduce a bit of reverb. Yeah. Good evening, everyone. We are Misok. We'll be performing a fusion, Carnatic and rock integrated fusion song called Dhanashri Tilana. Hope you guys like it. Let's go with the song. tagada dam dane dim 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 dani alari dam 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 tagadani alari dim 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 tagadigu dani alari tadim dirana udani dani dani tadim dirana taditton taganaga dari dadadi tagadadi dim tagadadi dim alari alari tagida dam dana tagada dam dani tagada dam dana dim 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 dani alari dam 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 tagadani alari dim 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 tagadigu dani alari tadingina to nanjera gori tani tante ida tani tante ida tani tante ida digu dagadi tadi Thank you so much. I'll introduce the band once again. We have Devansh on the tabla, Siddharth on the guitar, Aryaman on the bass, Rishabh on the guitar, Ayush in the keys, Srijat on the drums, and then you've got myself, Vedang, in the vocals. Thank you. Thank you so much. So, yeah, up next we have a instrumental Jugalbandi with the violin as well as the tabla. You guys enjoy.
Hello everyone. So we'll be having a live dance and a music performance. So this is done by the students of the club Shutilaya. So this is the announcement of the performance.
Hello. Check. 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 Hello. Check. Check. 1, 2. Hello. 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 One. Check. 1, 2. Hello. Check. Hello. Hello. Sorry for the delay. Um, we'll we'll directly get on with the song. The song is called Chandra Choda. It's a classical song. It's called Chandra Choda, and we are mixing it up with Veera Raja Veera. Hope you guys enjoy it. கணியர் கானம் பாட கணிகையர் நடனமாட பார்வையர் புலவை போல பனி நீர் சகடமாட அலைமேல் கதிர போல விளங்கிடும் அருமதேவ பணியடி பெருமை சாற்ற புலர்வக தமிழுந்தீர் கடமேல் போயலை போல கலங்கள் விரிந்து பாய பண்பொலி சேராற்ற தென்முலம் ஏகும் வீர வீர ராஜ வீர சூர தீர சூர வீர சோழ வீர சீரா ஞானம் வாழ வாழாய் வாழை சூர வீர ராஜ வீர சூர தீர சூர மாறா காதல் மாற போவோர் ஏங்குந்தி ஆயிரம் வேகம் போல போர்க்களம் சேரும் சோழ வீர ராஜ வீர சூர தீர சூர Thank you so much.
Check, check.
Hello, we are Dance Club and we will be performing on a variety of songs and showcasing a variety of styles including classical, Bollywood and hip hop. We hope you enjoy our performance. Thank you.
रोशनी से नूर के धागे तोड़ लाओ चांदनी से नूर के घूंघट ही बना लो रोशनी से नूर के
शर्मा गई तो आगोश में लो हो सांसों से उलझी रहे मेरी सांसें
बोलना हल्के हल्के बोलना हल्के हल्के होंठ से हल्के हल्के बोलना हल्के
बोलना हल्के हल्के बोलना हल्के हल्के होंठ से हल्के हल्के बोलना हल्के
रायबरेली में तू बीच बाजारी जब हुस्न दिखाने जाएगी होश उड़ाने वाली शौक नजर के जो पेंच लड़ाने जाएगी अरे बहन के इतना जेवर गहना तेज हवा से बच के रहना गिर जाए तो फिर ना कहना झुमका गिरा ले
What झुमका What झुमका What झुमका
Tonight
of you enjoyed the performances by our music club and the dance club. So let us all proceed for dinner now. The dinner is arranged in the BGH lawn. So we have arranged buses right from here to my on the right side. There are buses waiting to take you to the venue of the dinner, and those of you